I guess we're live, but you need to make
1 second. So it's first you, logistics. And this. Put. Should be fine. Ah, yes. Okay, this still works, right? Can we check it? Hello. Does it work? This one I'll take with me, because we don't want to probably get them confused.
uh, 8:55. Let's see. Did you download? Thank you. Thank you.
Okay. Is this? Okay, please. Okay, do you need anything else?
No, no.
You're good?
Yeah, you're good.
Okay, then always fix the presenter view.
Okay, yeah, yeah. Let's make sure. I do the panel, like creating controls.
Okay, I will try to join from my phone and see.
It's already.
Ah,
I think. Yes.
Sure. I think so.
Hello. You need to use Microsoft laptop again. Windows. Trust.
But I guess we'll connect it and
Yeah.
not any problems like last time. And yeah. How are my slides?
We have your slides.
The animation. Yeah.
Looks like that.
yeah. Seems okay. Support us for everybody.
Because this is the microphone.
Yeah, and that's why it didn't work.
Yeah, for my laptop it didn't work, but this laptop worked.
Whose laptop is this?
Nisa's. Even Mohammad
My
had an
old
issue.
laptop.
You can see that it's Nisa.
You're here, do you see?
I hope this is not me.
I'm not sure. Well,
Well, maybe that's true.
second part maybe.
Maybe both parts. You never know.
You hope the first part is not true.
You can never go inside deep enough.
Most of the microphone and
Yeah, both I think works. I will check the audio.
okay.
Maybe I'll.
Okay. Onur, should we get started or should we wait 1 or 2 more minutes?
Wait a couple more minutes.
Okay. Yeah, I guess I'll update the agenda, push Rakesh to the end. It should work. What about this? Let's start. Okay. Welcome everyone. Welcome to 4th edition of workshop on memory-centric computing today in HPCA 2026. So I'm Ismail. I'm a PhD student in software research group. It's been 2 years. Actually, this is my first day of 3rd year in PhD. Interesting. And I'm doing research in computer architecture, processing in memory, specifically processing using memory, and I also we're recently working on hardware security, memory robustness, etc. So here's the QR code. If you're interested, you can see the agenda, and I'll update the materials after the workshop, so you can get every materials in this workshop. So we have a couple of organizers. I'd like to thank all of them because it wouldn't be possible without them. And yeah, so the agenda is the first session will be until the coffee break until 10:30. So we will have, this is logistics, and we will have Professor Onur's talk about memory-centric computing. And then if time permits, I'll be presenting processing using memory in real DRAM chips. There could be some dynamic shifting in the agenda, but I'll update you about that one, and I'll also update the website. In the second session, we have the first invited talk from Professor Sogatagose about Mastodon, and then Dr. Joao will present, and then we'll have Rakesh. In the third session, we will have again 3 talks about offloading CXL, computational memory, then architectural system software support from PIM integrated systems from Dongjia, and then we will have some we will take a look at the security issues of PIM systems. And in the last session, we'll have a paper PIM-friendly from Kyungmo, and then Nika will give an overview of storage-centric systems for genomics and metagenomics, and then Dr. Konstantina will present an interesting paper about processing memory with, again, bioinformatics, and then we'll hopefully close. So, good news, we have some good news. We will have the 5th edition of this workshop in Asklos. It's in, I guess, 1.5 months. It will be half day, and the call for presentation is open. If you would like to give an invited talk, please consider us. And you can just apply directly from a Google form. And yeah, it will be on 23rd of March, Monday, as afternoon night. And we have another one. This will be the 6th edition of MCCSys in ICS, which will be held in Belfast, Northern Ireland, United Kingdom. This will be a full day workshop, and we will have proceedings on that. So we will invite people to submit extended abstracts, like 2-page ongoing works for your abstract. And yeah, we hope them to see in this edition as well. That's about it from my side, I think. If you have any questions, feel free to contact me during the lunch break, coffee breaks. And let's hope you'll have a good time. Oh, something happened. Again. Do you see it now, Nisa? Everything works.
Okay, thank you.
You should use this one.
No, it's a different one.
Yes.
No, it's okay. Okay, welcome everyone. It's good to see a lot of people up on a Sunday morning early. Some of you may be jet lagged like me. I think this is the 4th edition of MCCSys, but we've had many editions of the real PIM tutorial in the past. This time we're doing it as a workshop. And as Ismail said, we'll have more editions. So if you're interested in contributing to the workshop, we're happy to get contributions like invited talks. And as Ismail said, some short papers at ICS workshop as well. I'd like to definitely thank Ismail, Nisa, who's taking pictures over there, Mohammad, who have helped organize this workshop. And before I start, I'll also say that we may have something on ISCA as well. Let's see. So we're having these workshops because this is an important topic that needs to have a lot more investigation. There are a lot of papers clearly at top conferences, but we need to have some more channels to build a community around processing in memory, because changing the paradigm is not easy. And processing in memory tends to change the paradigm. It's not a processor-centric approach, it's a more memory-centric approach. And it's very hard to, let's say, change how people think without building a community. So I think it's good for people to participate in this as much as possible. And we may have some more initiatives in the future as people participate. Sounds good? Okay, so with that, I'll get into my talk. I'll try to stick to the time limit so that you can talk about some things. So I have some things that will foreshadow some of the talks that will happen later today. So basically, the summary is we have a huge memory problem in computing today, which really causes a lot of the other, let's say, evils that we need to deal with in our research, which is performance bottlenecks, energy consumption, robustness problems, monetary cost. You may be actually seeing this a lot more with DRAM prices skyrocketing. But even with DRAM prices, let's say, not being fair, in my opinion, which is low, this was a big cost. More than 50% of the cost of a big server was DRAM. Now it's going to be much more than 50% as DRAM prices get to a more fair place, let's say. And hardware real estate. I'm going to give you some examples of this. And this memory problem is becoming worse with more data-intensive workloads, and we have a lot more data-intensive workloads. We held the Architectures for Health workshop yesterday, which looks at issues like genomics, proteomics, life sciences, and there's a whole lot of data that can be generated in those domains. And clearly, machine learning has built on data that's generated. So I think solving this problem fundamentally, clearly we can patch this problem, and people have been patching this problem by adding more things to a processor and still moving things to the processor from faraway places where data is generated and stored, storage, sensors, memory. We could keep patching it, or we could do a fundamental rethinking of the system, saying that we have a clear memory problem. Can we actually redesign the system, rethink the system, so that we don't have this problem, basically. That's the premise of this workshop, essentially. How do we design memory-centric systems that do not fundamentally get bottlenecked by data and memory? And in this talk, I'm going to look at two aspects of it. One is the technology scaling. And technology scaling has been making the memory problem a lot more difficult going into the future. We've been having a lot of robustness issues, energy issues, latency issues because of technology scaling. And we can actually solve a lot of those issues with a more memory-centric approach by putting computation near memory, by enabling memory to autonomously managing itself. And the second part I will examine is more scaling at the application and system size. Application and systems are not scaling well because even though they may look like they're scaling, we're actually wasting a lot of energy. Hardware, sustainability issues may be caused by trying to scale our applications. I believe that we're not scaling things very well, and this is because of the memory problem mostly. And if you can enable memory to perform computation, maybe there's a much better way of scaling systems into the future. So hopefully this gives you a both bottom-up perspective, which is technology scaling, and top-down perspective, which is application and systems. And I will argue that we're kind of squeezed in the middle. We really need to do something to solve problems that are pressing us from the bottom, as well as pressing us from the top. Does that sound good? Okay, with that, let's jump into the talk. I think this computing is really bottlenecked by data, as I kind of said earlier. And if you look at applications that we have, they're all data intensive. They require rapid and efficient processing of large amounts of data, and data is really increasing. We can generate more data than we can process in many domains. Again, life sciences is one example. Genomics is a huge example. AI is clearly a huge example also. And we need to, in fact, with AI, people are generating, automatically generating data, right? Synthetic data. So real data is huge. On top of this, if you add synthetic data, there's a lot more, basically. And we want to perform more and more sophisticated analyses on more data so that we can have more capable workloads, right? And clearly, in machine learning, AI, we've been seeing this. This is a picture from Cerebras. These guys are building large wafer-scale chips to tackle essentially the memory problem. They're putting a lot of SRAM on the same chip with a lot of compute. Unfortunately, this is a very good effort. I think people should be doing things like this. But it's very difficult to have huge amounts of memory by using SRAM. So SRAM is very interesting. I'm not going to talk about that in this talk a lot, but it's good to have efforts in any kind of memory technology. But if you look at this picture, the neural network computation requirements have been growing exponentially, as well as memory requirements have been growing exponentially. And you may argue that this is not good, and I kind of agree. Maybe we should be looking at different paradigms and algorithms in AI and ML so that we can reduce these requirements. And I agree, but at some point, you cannot really reduce things because you need to deal with large amounts of data. You need to learn from that large amounts of data. Okay, so as I said, genomics is another area where data is growing exponentially. If you're interested in this, we've been doing a lot of work on bioinformatics, genome analysis, and there will be some talks later looking at processing in memory and processing in storage for genomics workloads, which is a fascinating area. And this is happening because we have devices that are very capable of generating data at high throughput, low latency, and very low cost. This device, the nanopore device, you can buy for $1,000 or so. And you can actually generate a lot of data, a lot of interesting data. And again, if you're interested in this, I'll invite you to the Architectures for Health workshop. The proceedings are all online on YouTube, and you can come to the next edition. Okay, basically the problem is we have a data access problem, also a storage problem, but data access is really the major performance energy bottleneck. And our current design principles are not really designed to deal with this nicely. Basically, we move the data from the sensor, storage, main memory, to the on-chip memory, to the register file. And we cause a lot of energy waste because of this data movement. We also cause a lot of performance loss because moving data has latency and bandwidth impacts. And I put this in parentheses because we realize the performance loss much more than we realize the energy waste. And we try to overcome this performance loss with many, many techniques that have been designed over 60, 70, 80 years. For example, caching, prefetching, out-of-order execution, many levels of multi-threading. So we complicate our systems to overcome the performance loss as much as possible. And complicating our systems actually compounds the energy waste. And those techniques that you add to overcome the performance loss, sometimes they work, sometimes they don't work. In some applications, many times they don't work. If you have random access, for example, a lot of those techniques fail. And they actually compound the energy waste. So you go into a vicious cycle. You keep complicating your systems to overcome this performance loss, but then you keep expending more energy because everything you add to the system actually increases the energy cost of the system. And also it increases the hardware complexity. It also increases the sustainability impact because you're adding a lot more silicon or hardware. So we want to break this cycle basically. Well, why is this cycle caused? Whenever you have a vicious cycle and whenever you want to break it, you need to figure out what is the really fundamental problem, right? And here the fundamental problem is we're very processor-centric in everything we do. All data gets processed in the processor at great system cost, even though there's so many other resources that we build in our systems. This is my cartoonish picture that I drew in 2008 when I wrote one of my proposals to NSF. This picture is still similar. I like it. That's why I don't change it. But if you look at this picture, what this picture shows is a modern processor-centric system. And the red parts are processing units. The rest and processing units can be cores, heterogeneous accelerators, whatever you process data with. And the remaining parts are all caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, main memory, other interconnects, and storage. So if you do the calculations, more than 90%, 95%, depending on what kind of system, 99%, and depending on what you include in this picture, of the hardware real estate of a single node is dedicated to storing and moving data. And I think if you want to change the paradigm, it's good to take a very critical view. And usually people who take critical views try to have a blank slate in their thinking, right? So my favorite example of this is a maybe 8 to 10-year-old kid. Give this picture to an 8 to 10-year-old kid and say that I'm designing this system. I'm dedicating almost all of my resources to storing and moving data. Should this be my bottleneck? They will tell you this should be your bottleneck because you're dedicating all of your resources, right? That's basically, I think, very simple thinking. Unfortunately, our bottleneck is still data movement and storage, which is memory. It's good to think about this basically. We keep complicating our systems and our bottleneck still keeps being memory. Why are we discussing the memory bottleneck for 80 years? Okay, so that was hardware real estate. Let's take a look at performance. This is data from Google in their nice paper from ISCA 2015. They showed that on a state-of-the-art processor, executing, according to them, all of their data center workloads, the processor spends most of its time waiting for memory. The processor does what it's doing, what it's supposed to be doing, what it's designed to do, which is finishing instructions only 10 to 20% of the time. That's the green parts over here. Again, take the perspective of a 10-year-old kid. Give this picture, throw this picture at them, and ask them, I designed the system. The goal of the system is to finish instructions. It's finishing instructions. It's doing what it's supposed to do only 10% of the time. Is this a good system? They will be honest with you, and they will say, this is a terrible system. Go design something else. And I think we should be doing that. Of course, there are business implications to this. So not everyone will be like the 10-year-old kid. 10-year-old kid doesn't have the $1 trillion investment into the thing. But again, maybe the bigger investments will come down in the future if you actually rethink the system. Okay, so that was performance. Let's take a look at energy. This is data from Bill Daly from NVIDIA, essentially. Again, the data is a bit old, but the trends essentially remain. The disparity remains. If you look at a complicated arithmetic operation, it's relatively cheap. 64-bit double precision floating point operation. It's an expensive arithmetic operation, actually. In terms of energy, it's 20 picojoules at the time with some assumptions. A DRAM read or write is 16 nanojoules. There's an 800x difference. If you optimize the system, you can get to 150x or so, optimize the memory access. 150x is still 2 orders of magnitude disparity. Then the question becomes, I have this really cheap, energy cheap operation. Do I really want to move its operands from the memory to the processor and expend 3 times 800x in this picture to do that operation? This is actually an optimization problem in the end. It's not dogma. There's no dogma here, right? The optimization problem is, when does it make sense to move these operands to the chip to overcome the energy differential that we see over here? And if you do the calculations, you will figure out that the reuse that you need to have for those operands need to be on the order of thousands, etc. Of course, it's not as simple as a single operation, because there are other operations that may actually use the data that's brought in. But people have done these calculations. For example, Professor Wenmei, who has nice talks where they describe how many times you need to reuse things, and it's on the order of thousands to overcome the energy differential. Okay, and energy differential keeps becoming worse because we don't want those complicated arithmetic operations. I think machine learning people have discovered this finally, which is essentially they don't want these 32-bit floating point operations. They want 8 bits. They want actually lower. They want integer. They don't want floating point. And they don't want 8-bit integer. They want 4-bit integer. And ideally, they want to get away with 1-bit integer. If they can do away with less than 1 bit, that'd be even better, right? And I think the goal should be doing that very simple computation. And as you make computation cheaper, in this case, you look at a 32-bit integer addition, again, from a paper by Bill Daly. A 32-bit integer addition is 6400x less energy than a DRAM read or write. And again, optimize the DRAM, maybe this goes down to 1000x, but that's 3 orders of magnitude we're talking about. Again, take the picture, and we're not talking about storage yet. This is still main memory. If you go to storage, add another 10x, an order of magnitude, maybe more to that. Again, take this picture, throw it to a 10-year-old kid, and say that I have this disparity, and I keep moving data. The 10-year-old kid would probably say, "Are you crazy? Why do you move the data?" Right? Okay, you can try that experiment. Okay, so we tried to quantify the energy and performance impact of data movement on real systems. And this is, we did several works. This is one of the works that we did with Google about, in ASPLOS 2018, we published it. It basically looks at the energy and performance impact on mobile devices of data movement. And it does an analysis of where does energy and performance go in important workloads at the time, like TensorFlow of inference, Chrome browser, video encoding and decoding. These were the 4 workloads we focused on because we thought they were important for mobile experience and mobile devices. And this is one result from this paper. Basically, we show that more than 60% of the total system energy on average use cases, these are not the worst case use cases, on average use cases is spent on moving data across the memory hierarchy. In the worst case, there are more intensive applications. This number increases. And more recently, we repeated the study on machine learning accelerators that are designed at Google again. And we looked at the energy spent on edge neural networks that Google uses on their edge TPU, essentially, that's in mobile devices like Google Pixel phone, etc. And we found out that more than 90% of the total system energy is spent on memory in large machine learning models. This is before LLMs. With LLMs, things become actually worse in many cases, especially if you're doing on-device LLM inference. If you look at this, for example, at the time, we looked at LSTMs and transducers, and you can see that most of the energy is really spent on DRAM and off-chip interconnect. And if you do processing in memory, you're going to reduce that, as we will discuss when we get to it. So this is real data showing a lot of impact of energy, performance, and application level. So basically, the fundamental problem is we're moving data a lot. Processing of data is performed far away from the data. And as a result, we're wasting a lot of our resources that we deem important. How do we fix the fundamental problem? As I said, we need a paradigm shift. We need to enable computation with minimal data movement. We want to compute where it makes sense, meaning where data resides or where data is generated as much as possible. This means that we should really think about computing architectures to be more data-centric as opposed to processor-centric. And if you think about it, our thinking is very processor-centric. The processor is the king, and it gets all the data to process. And memory is not important. Maybe that'll change with the memory prices, but let's see. Okay, so and there are many places where we can process data, actually. If you look at this picture, it's a mobile system. You have this SRAM-dominated chiplet, and you can actually process data at all parts of it. Today, we're restricting ourselves to compute units, but why not in big caches, for example? That's the SRAM part. Why not in main memory? Why not in storage? Why not in sensors? So there are a lot of places where we can actually process data and distribute the computation capability across the system, as opposed to restricting it to a very small fraction of the system. In the rest of the talk, I'm going to talk about memory as an accelerator. There's actually a broader model where you can actually have a distributed computer where everything is equal, and you distribute the computation, and you have a model of execution and programming such that there's no central processing unit. That tends to be even harder to think about. So our step is, because we know how to design accelerators in most of our systems, and we keep adding new accelerators, some of which have somewhat similar challenges to accelerator that you would add in memory. Why don't we actually have accelerators near or inside the memory also? This way, potentially, you can adopt the conventional programming models more easily because you can extend the accelerator-based models. And there are many questions over here. This is easier said than done, even with an accelerator-based model. Basically, the processor needs to have mechanisms to communicate with the accelerator, query the memory and storage to ask, can you do this computation function for me? Or can you execute this application for me? Or can you execute this instruction for me? Even this question that I just discussed is a granularity question, like what do you offload, for example? How do you communicate? And then the memory and storage somehow does some computation, and there could be different ways of doing this computation, and then returns a result. Over here, how do you design the memory and the controllers to enable different types of computation? Are they specialized computations? Are they general purpose computations? How do you design the processors and communication units to enable this? And how do you rethink the processor once you actually have computation capability on the memory side? Maybe you get rid of a lot of, let's say, complexity in the processor because you're offloading memory intensive portions to the memory, and the processor can actually be relieved of dealing with memory. It could be much more specialized for compute-intensive tasks. So it could be an accelerator for compute-intensive tasks as opposed to a general-purpose processor that tries to deal with everything, right? That will change how we actually distribute our hardware resources. And this is actually at the core of the business problems of changing the paradigm, right? Because processor manufacturers don't want to give up that part where they're doing everything. And if you actually give up some part, you're going to lose some revenue. So there are business implications of this paradigm. But again, I think if you want to change the world, you cannot solve all implications immediately. We're going to get back to that later on. How do you design the hardware and the software interfaces to enable this? And then, of course, once you have those, how do you design the system software, compilers, and languages to make this sort of offloading or computation in memory easier for the masses? And how do you actually design your algorithms to match the computation capability of hardware? Because the computation capability that you have inside the memory and storage may be very different from the type of computation that we're used to on the processor side. And we're going to see examples of this later on today. And I think this is really very interesting because now you can rethink your algorithms to match the hardware. And finally, there's a theoretical foundations part, which is my favorite, but which is the least intensive efforts that we're seeing right now. The question is, if this is such an old idea, why do you examine it again, right, today? And I think, are you there? Looks like you saved it. Hopefully. Okay, yeah, these are the papers that I just mentioned. And I'd recommend people to look at these papers. They're relatively short papers, but they're visionary papers, in my opinion. And a lot of people kind of ignore these papers for some reason. I don't know why. But it's not good not to ignore these papers. Okay, please move this window away from, what is that? I cannot even see the window. We will talk about robustness. So robustness of processing and memory is also important, but robustness of everything is important in general. Okay. We're having Wi-Fi problems. Oh, there's a cable also? Okay.
No, there's a cable being brought up to solve the problem.
Oh, okay, maybe. Okay. Yeah. Thanks. Thanks, Steve. No problem. Yeah, I think we're back. Thanks. Okay, I'm not going to touch anything. Okay. So this is the paper. This is one of the papers, and this is, well, no, I cannot. Okay, this is the other paper. And I recommend people to look at these papers. These papers look at processing near memory, which is different from processing using memory, and I'll distinguish between them. Processing using memory has been taught more recently, in my view, and we'll talk about that. Okay, so why re-examine this sort of idea today? Basically, what I said earlier, we are having a huge push from applications and systems. I've given you examples of this. And today also, we are very interested in improving not only performance, but also energy, also sustainability. At some point, cost was one of the major measures. And if you read those papers, they talk about cost a lot, actually. And then performance is important, of course, always. Energy came to be important more recently. Sustainability is becoming more important, hopefully to those trillion-dollar companies who waste a lot of our resources also. It will become important at some point, as opposed to just something said at its face value. So basically, I think with over decades, people have changed as well. It's not just applications, but the requirements that people have on computing systems have also changed. We want no trade-off between performance and energy. We want to improve performance and energy at the same time, energy efficiency. And we don't want to waste sustainability. And I believe by changing the paradigm, we can improve all of those metrics. And we're also having huge problems with memory technology. Memory technology scaling is not going well. And I'm going to talk about this, as I said, about robustness. This is causing a lot of robustness problems. So, and this has not happened for many, many years in major technologies that we've been designing our computing systems with. DRAM, SRAM, Flash, they're all having scaling issues, although DRAM is probably having the most scaling issues because it's the largest, it's one of the largest memories. And we're going to look at that. These scaling issues demand more intelligence in memory, and you can actually solve some of these problems by being much more memory-centric. And there's some also emerging technologies that can enable new functions in memory. And it's good to look at them with technology scaling. Okay, can I do something? No, okay, I'll not touch it. This is Windows. And I think our designs are squeezed in the middle. So we have no, in my opinion, we have nowhere to escape if our goal is to truly improve performance, efficiency, and sustainability. Okay, so let's, yeah. So this will be my message to students and like critical thinkers over here. If you really want to solve fundamental problems, defy business as usual. Because business as usual may say, okay, let's keep patching the system, right? And maybe that's a good thing for making money in the short run, as we have seen. But if you really want to change how things should be done, let's say for optimizing some metrics that we really care about, I think you need to change. You need to defy the business. And a 10-year-old kid is a good example of this because they don't have that much investment or interest in businesses in general. They really want to do what they want to do. Okay, so let's talk about memory technology scaling because this is something that we've been working on for some time. And this is actually memory approach. So we built a lot of infrastructure to understand technology scaling issues, especially with DRAM and flash, but I'm going to focus on DRAM over here. This is our DRAM vendor infrastructure where we can test DRAM chips. And this is the HBM infrastructure. We gather a lot of data to understand the technology scaling issues and also latency issues, energy issues, performance issues, etc. We can change the timing parameters. We can get rid of refresh. We can change a lot of parameters using this FPGA-based infrastructure because we have a soft memory controller that's on the FPGA. And we built a lab. This is the lab we have at ETH, where we can test hundreds of these chips concurrently. And Ismail can tell you all about that because he's adding more things into that lab. And these are his pictures, actually, Ismail and Nisa's pictures. So we have various versions of these infrastructure, and we've done a lot of studies. This is the one at CMU that Sogata is very familiar with. He can tell you about it. It was in a cage in front of my office. Is the cage still there? I don't know. Okay, I guess not. Yeah, basically, we did a lot of rowhammer experiments over here. And we wrote a lot of papers. This bottom one over here was the earliest infrastructure that we had. Okay, this is all open sourced. SoftMC was the original one. DRAM vendor is the more recent one. And if people are interested, we'd be happy to support a lot of work in this area. And we're having a workshop on DRAM vendor and Ramulator in ASPLOS. So one of the things that I will talk about that demands more intelligence in memory is the rowhammer issue that we've been examining for essentially more than 14 years or so. The problem is you get bit flips in real DRAM chips by doing perfectly legal access sequences. And if you look at memory, it consists of two-dimensional arrays of cells. And if you access one row, you need to activate, if you want to access one row, you need to activate the row, meaning apply high voltage to that word line that contains the cells you want to read from. And if you want to access some other row, you need to apply low voltage to that row, meaning you want to lower the word line and pre-charge the array, essentially close the row. Now, if you keep doing this repeatedly, perfectly legally, high voltage, low voltage, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge in DRAM, it turns out if you do it enough times before the cells get refreshed, some cells, some vulnerable cells in physically adjacent rows get disturbed and they lose their charge little by little, and eventually they get corrupted. You will not be able to read the correct data out of those cells. Now, this is called the rowhammer problem. Essentially, we call this the hammered row. We call these the victim rows. And we basically showed that essentially all DRAM chips, all DRAM chips today are vulnerable to this problem. And this is happening because technology has scaled. We want to scale technology to reduce the size of the DRAM cell so that we can pack more cells and reduce the distance between the cells also. We can pack more cells so we can store more data in main memory. And that has enabled huge amounts of data to be stored in main memory today. But that has come at a cost, which is cells are too small and too close to each other. As a result, when you access one cell, you're causing electrical noise in physically adjacent cells, and you're causing this sort of data corruption problems. Clearly, this should not be happening because those victim rows may contain data that doesn't belong to you, may contain system critical data, may contain really important data that you should not be corrupting, right? So this is actually a robustness problem and also a security problem. And this problem has become much worse over time because cells are becoming smaller and closer to each other. And the number of activations you need to do to induce a bit flip has reduced by more than 100x. So when we first did the studies in our original paper in 2014, we reported the number of activations to be, this is the original paper, by the way, we reported the activation count to be more than around 139,000. Today, if you know what you're doing, you can actually induce these bit flips with 70 or 80 activations with some other effects that we will discuss also. So a lot of benign applications can do that actually, if again, designed in some way. Okay, so basically, when we wrote the rowhammer paper, we said that this is a robustness problem, but it's also a security problem. Essentially, we should not have memory isolation between different rows to be broken, because we don't want unintended side effects on data stored in other addresses when we're accessing one address. And we said that someone can hijack your computer, and these good folks from Google Project Zero essentially showed that. I'm not going to go into a lot of details of the security attacks, but essentially, over many years, people have shown that, researchers have shown that you can exploit rowhammer to take over a system like Google did. You can exploit rowhammer to read data that you don't have access to. You can break out of virtual machine sandboxes. You can corrupt important data like ML model parameters, such that your ML inference is essentially useless because it's so inaccurate. It becomes so inaccurate because of Rowhammer. You can steal some secret data that doesn't belong to you, like cryptographic keys or machine learning model parameters. These are all probabilistic attacks, but these are all doable in real systems with some effort. And actually, there was, in Usenix Security last year, there were 7 papers on Rowhammer. One of them was actually looking at how to do this attack on GPUs, for example, to render machine learning inference useless, inaccurate. Okay, so we've written many papers on this. This is, if you want to get started on Rowhammer research, this is one example of this, and we've written retrospectives. The issue is, this is just one example of technology scaling, and we've discovered some more examples of technology scaling, like RowPress. Very quickly, this is in 2023, essentially 9 years after we wrote the Rowhammer paper, we discovered a different read disturbance phenomenon. And here, the phenomenon is different, fundamentally different, actually. Instead of activating a row at the maximum rate, we activate the row, keep it open for some time, and reactivate it again. And if you do that by keeping the row open, you're inducing a different kind of disturbance in adjacent rows. And again, I will not go into the details of devices. There are actually fascinating device level studies that are happening in this area. But this way, you can reduce the number of activations to induce a bit by 1 to 2 orders of magnitude. So these are real effects. Essentially, all memory chips are vulnerable. These are 3 major manufacturers in DRAM: Samsung, Micron, and Hynix. And they occupy more than 95% of the DRAM market. And they're all vulnerable. You can see that these are real chips. These are real chip studies using the infrastructure. Okay, why am I telling you all of this? Basically, this sort of issues are coming up. They're going to become worse and worse. And maybe other issues will be discovered. I'm going to talk about that. And Ismail is going to talk about that later on today. So how do we solve this problem? There are many potential solutions that are being examined. But I believe a fundamental solution that we've always argued is really important is to design a more memory-centric approach, meaning have more intelligence on the memory side or the controller side. And this is what we argued even before we wrote about Rowhammer. This is our IMW paper in 2013. More recently, we updated this paper. If people are interested, you can take a look at these papers. And the good news is industry, I think, is finally following this approach. This is a paper by SK Hynix. It's the first paper from a major DRAM manufacturer that acknowledges Rowhammer at ISSCC 2023. And that describes the issue, etc. And that says basically to solve this problem, we put an intelligent controller inside the DRAM. I'm not going to say this is the best solution to this problem, but this is a solution with the right, let's say, perspective from my perspective, which is putting intelligence inside the DRAM chip. You have some computation capability inside the DRAM chip. Next to each row, you have a counter that counts the number of activations. And if the number of activations are greater than some threshold, the chip takes some action to fix the issue by refreshing adjacent rows. They don't give a lot of detail, but that's the gist of the idea, essentially. This is now standardized as the per row activation counter solution in JEDEC. And it's very difficult to change something in JEDEC. This is JEDEC has 390 plus companies, and they fight with each other to do nothing in DRAM as much as possible. I'm joking, of course, right? I mean, they do something, but very business as usual things. This is not a business as usual. Putting a controller inside the DRAM, if you went to JEDEC 10 years ago, they would kick you out of the room. I know because I went to them. And they didn't listen, let's say. They didn't kick me out of the room. They were nice. But basically, a lot of folks in industry said that this is the biggest change that has happened to DRAM over the course of 30 years, putting a controller inside the DRAM. Okay, the question is, are solutions good? This is one solution to a problem. You don't need to be a 10-year-old to think that this is not a good solution to this problem, right? So it's good to evaluate these solutions. So we have written papers to evaluate these solutions to show that you need to do better, essentially. You can be safe, but if you're safe under some attack conditions, these solutions, even under some less attack conditions, the solutions impose a lot of performance overheads. Okay, again, I won't go into a lot more detail. The question is, how do you actually do better than the solution? Have even more intelligent memory controllers. And if you actually are adding this sort of intelligence to the DRAM chip, why not also add some other computation capability, right? Because if you think about it, the solution that's added to the DRAM chip is adding some metadata with each row. That is currently not exposed to programs. But if you could actually think about the future, maybe you can actually do a lot more things with that sort of metadata that's added next to each row. Okay, the question is always, can we do better, basically? I'm going to talk about one thing and tell you a story also about this thing. This is basically a solution that we have devised. We call it self-managing DRAM. I believe this is a very principled solution. And the principle is, don't be processor-centric in managing DRAM. Be a little bit more memory-centric. And the question we asked was, what is one of the minimal things that we can do, at least to the best of our thinking at the moment, to be more memory-centric to manage DRAM? Basically, what happens today is the memory controller manages everything in DRAM. DRAM chip has no breathing room. It cannot even say, I want to refresh myself. Forget about it. That doesn't happen. Memory controller needs to put the DRAM chip into self-refresh mode. Memory controller needs to send a refresh command every 7.8 microseconds on 3.9 microseconds, or even lower if your temperature is higher. So a memory controller manages everything. DRAM chip has nothing, cannot do any maintenance by itself. So this is how processor-centric we are. It's really, DRAM chip is really a slave, basically. It cannot do anything by itself. So we wanted to change this, basically. Can we actually give some breathing room to the DRAM chip such that DRAM chip can do some of these operations like row hammer protection, refresh, and also memory scrubbing, etc., that we believe truly belong to the DRAM domain, because DRAM manufacturer really understands how they can optimize all of these operations, and memory controller has no idea. We actually worked on enabling the memory controller to have an idea about these operations, but you need to do a lot of profiling to figure that out. But the DRAM chip has a lot of information internally. So how do we partition the work between memory control and DRAM chip such that we're more equals, let's say, without going completely memory-centric? And the idea is very simple. Basically, give some breathing room to the DRAM chip. When the memory controller requests something to the from the DRAM chip can say, no, I cannot do it because I'm doing something important in this area that you're trying to access. So try again. It's a negative acknowledgement. It minimally changes the interface. And once you change that interface, you enable the DRAM manufacturer to implement operations internally because they can negatively acknowledge. And this single interface change can actually enable a lot more progress in the field because now DRAM manufacturers can independently improve the DRAM chip by being more memory-centric, if you think about it, without having to go through the JEDEC to actually change the interface every single time they want to do something. Sounds good, right? So that's the idea, basically, self-managing DRAM. And we've shown that DRAM refresh can be improved, row hammer protection can be improved, and memory scrubbing can be improved. I believe processing in memory can be improved with this sort of approach also. Okay, that's the talk. So this paper, this is the story I won't tell because there are graduate students over here. Probably you get rejections. You're not alone, don't worry. I have a story about the row hammer paper also, but I'll refer you to my micro keynote talk for that one. This was rejected 6 times, two times each from major architecture conferences. Okay, I don't mind rejection if it's reasonable, but the question is, are the reviewers asking the right questions? Can I actually answer these questions? For example, what are some business impediments of this approach? This was one of the reasons for rejection. It changes the business too much. First of all, I don't care. As a researcher, I think we should be decoupling ourselves from business a little bit, right? If you're always concerned about business, then we will always do the incremental things that will enable business as usual, right? Yeah, we should do some of that also. I'm not against that type of research, but we should be in our scientific communities, we can be much nicer and much more open to new things without making such comments, right? Even if you make some comments, you can be accepting, right? That's what I argued in my keynote at Micro, said, why don't we accept a lot more ideas so that we can enable more faster scientific progress as opposed to limiting that progress. Okay, done, thank you. You're dealing with this Wi-Fi. Okay, so I think these were some of the slides and else. Okay, so the question is, there's more to come in this, and there's probably more to come on this reviewer discussion later on, but it's fascinating that there's still a whole lot we don't know about DRAM. DRAM is a technology that was invented in the 1960s by Bob Dennard, and it was patented in 1968. We're talking about 60 years of history. This is old technology. Some people were saying when we were working on DRAM, we were also working on PCM and other technologies like STT-MRAM. They were saying, why are you working on DRAM? This is going to die. We're talking about 2010, 2009 or so. It's not going to die anytime soon. It's actually stronger than any of those technologies, I think. And it'll evolve into the future. Like Flash has evolved. It'll become 3D, etc. But it's good to investigate what we don't know about these things. And we're still discovering a lot of interesting things. For example, Rowhammer becomes worse with aging. This keeps me up at night. Aging, right? How do these chips behave with aging? There are still questions open over here. Just last year, there are 3 effects that we have discovered using our infrastructure, variable read disturbance. This is basically the read disturbance threshold of a row changes randomly and unpredictably over time. So how do you actually adapt this? How do the solutions work in the field if this is the case? Right? How do you configure your solutions? And that's the paper. Ismail is, well, I'm not going to talk about this, but there are other issues like that are different from Rowhammer. This is a column disturb paper that we've discussed at Micro that Ismail presented. And this basically shows that a single row activation can flip bits across thousands of DRAM rows because of the perturbations caused in the columns. This is not a huge issue as Rowhammer today, but it's a scaling problem because we showed that it's becoming worse. And Ismail is going to talk about this. If we actually do processing using memory, as I will briefly describe, read disturbance becomes much worse, and these effects need to be somehow solved. Okay. And you can say that emerging memory technologies may be a solution. I will say that they are a solution to some things, but not this sort of things, because emerging memory technologies unfortunately have scalability problems from the get-go, or endurance problems, or robustness problems. For example, we've been working on phase change memory, STT-MRAM, for a long time, and we have essentially, if you look at some of these technologies, they have endurance problems from the get-go. They have wear-out problems, so they need an intelligent controller from the get-go. And none of these technologies have scaled to the levels, to the feature size that we scale DRAM into. And when they scale to those really small feature sizes, they will start seeing these issues. And there are actually papers that model this. They show that read disturbance, write disturbance are real issues in these memories, among other things. Okay. So that's why we keep building our lab to really understand what's going on inside memory. So if people are interested in actually building their own lab, we'd be happy to support it. This is a recent PhD thesis from Giray, who's my student. And they're actually, the good news is the community is a lot more open to these things. I think we should be even more open. There are a lot of read disturbance sessions, for example. This is just restricted to read disturbance at major architecture and security conference. I'll just flash these. And we organized the DRAMSec last year. You can watch that online also to see how industry thinks about these things. And at HPCA, we have also 3 read disturbance papers that are coming up from different groups. And as I said, there will be a DRAM vendor and emulator tutorial that Nisa, Ismail, Ataberk, and Haosong are organizing at ASPLOS. So if you're interested in using these tools, we'd be happy to help. How much time do I have? Zoom has eaten some of the time, so okay. Okay, I'll try to go quickly because some of these things will be covered by some other folks later. So that was the technology scaling part. Essentially, technology is not scaling very well, which is demanding more intelligence in memory. And I think we're going to see more and more intelligence on the memory side. Now, if we add intelligence, why don't we actually exploit it from the system level? And what kind of intelligence do we add? What kind of computation? When I say intelligence, is a computation capability. It's not this artificial or the general intelligence that people are talking about. We're very far away from that. I think we should not talk about that. Computation is intelligence in this case. We're very primitive, right? If you think about it. And because memory cannot even do computation, how can it be intelligent after that? So basically, there are two types of processing in memory. And this refers to the nature of processing in memory. I think people confuse terminology a lot in this area, in my opinion. I use processing in memory because people use logic in memory in the past. Logic is also okay, actually. So you can actually replace processing with logic in this case, and it works still perfectly fine, in line with 1960s papers that I just showed you. But let's use processing. Processing and logic are similar. But there's terminology confusion, huge terminology confusion. In my view, a PIM taxonomy consists of the nature of how you implement computation, where do you implement computation, that's a location, and what type of technology do you use. So nature, location, type, essentially. It's a tuple of those things. I think people mix those tuples. Nature and also location are mixed a lot, and we get a mess of, let's say, terminology here. So let's talk about just nature. There are only two ways of doing computation in memory or processing in memory, in my opinion. And I'm open to ideas. Maybe there's a third way that I don't know. It'd be great to see that. So I classify that as you have logic, you have memory. And today you have very different ways of implementing in logic and memory. Right? They're completely different. There are very different processes, especially if you look at DRAM technology. Fabrication processes are also different. So processing near memory says implement logic and memory separately, completely separately, as you do today, but put logic closer and closer and closer and closer to memory. It doesn't say exactly where. This is the nature, basically. The nature is logic and memory are separate. Now, if you think about where, it could be in the memory controller. The logic could be in the memory controller. The logic could be inside the DRAM chip. It could be next to each bank. It could be across banks. It could be next to each cell. But logic and memory are separate. Basically, that's the key over here. Processing using memory is completely different. Logic, memory, forget about logic. I don't have logic. I have memory. I have a memory process. I'm going to use the analog operational principles of memory to implement logic. I'm not going to implement logic separately. I'm just going to use those operational principles. And any memory has operational principles that enable it to do computation. And this is very different from what people have imagined in 1960s. In 1960s, people wanted to put logic near memory. This is more recent. In 2010s, people have started looking at it from the memristor perspective, in our case, DRAM perspective, and other technology perspective. So this is relatively new, processing using memory, I would say. And in the end, these have different characteristics, and I believe they need to be combined so that you can get the best approach. Because with logic, if you implement logic separately from memory, you can actually make very complicated operations than the logic, especially with the logic technologies that we have today. Whereas if you do processing using memory, you're more restricted to the capabilities of the technology, because any memory can also do computation in addition to storing data. The question is, what kind of computation can you do? In DRAM, we'll see some computations. In phase change memory or memristors or resistor RAM, you can actually do a matrix vector multiplication in the analog domain, for example. It's very difficult to do that in DRAM. You need to change the DRAM a little bit to enable that. But even how to change the DRAM is not clear to enable that sort of thing. Okay, so using memory can be much more efficient because you're not implementing separate logic. You're really using memory to do the logic computation. It could be very highly parallel because every single cell can be doing computation, but it may be more limited in terms of the type of operations that you do. And this also has potential implications on the programming model, etc. But that could also be abstracted away, as we will see in later talks. Okay, the good news is processing near memory has a lot of, let's say, example prototypes today. People have looked at implementing, for example, we worked a lot with the UpMem company and their chips. They're bought by Qualcomm recently to understand the type of processing near memory engine they built. They essentially have DRAM chips. Next to each bank, you have a multiple instruction, multiple data, multi-threaded processor. That's general purpose. It could be programmed using some sort of C++. They have a compiler. And you could actually relatively easily port applications to it. And we've looked at the performance and energy implications of this. We have a lot of work that I'm not going to talk about on that topic. But if people are interested in continuing that sort of research, we have access to a lot of UpMem resources now. So feel free to contact us. And there are also other companies like Samsung, SK Hynix, Alibaba. They produce their own DRAM chips, prototypes at least, to do computation near each bank to accelerate more specifically matrix operations. Okay, I will not go through this in detail, and there's more happening in industry to offload computation using CXL-like interfaces, which is good to develop more efficient interfaces to actually enable offloading of computation. There will be a talk by Ada later on today. Yeah, and I think emerging technologies are also very important. Again, looking into the future, it's good to look at technologies that can integrate logic and memory nicely to look at processing near memory. So in this particular case, we're looking at a 3D stacking technology. It could be hybrid memory cube, which is old, now high bandwidth memory. But essentially, you have a logic layer underneath memory layers, and you have high bandwidth, low latency, low energy connectivity between the logic and memory layers. Now you can actually put any type of logic inside those memory layers. And when we initially started doing this work, this sort of 3D stacking work in 2010s or so, the logic layer was terrible. Now it's becoming much, much better because people are developing the integration and fabrication technologies in a nice way. And HBM4 will hopefully have a true logic layer where people can customize that logic layer. And there are also other like further looking true three-dimensional technologies like monolithic 3D integration that are under development that will make this even better, in my opinion. But I'm not going to talk about that. So if you actually have this sort of technology, you can accelerate a lot of applications. I will not talk about these in detail. Maybe there will be talks. But this is one of the works that we've done with SNU folks in 2015 to accelerate graph processing applications on a distributed accelerator that consists of multiple of these 3D stacked near memory logic chips. And there are a lot of interesting issues over here. I think of these as maybe when we were doing this work, we should have focused on machine learning because the existing machine learning systems pretty much resemble this sort of accelerator actually today. Okay, and we have a retrospective of that paper at ISCA. So accelerating ML inference is something we looked at with Google. I'll briefly talk about that. You can actually use 3D stacking technology. And this is what we envisioned in that paper, this Google neural network models for edge devices paper. So instead of designing an edge TPU that's processor-centric and monolithic, that's trying to cater for very different type of models and layers, why not design a heterogeneous accelerator that consists of some data-centric accelerators that are in the logic layer of 3D stacked DRAM that are customized for different data flows, and also a compute-centric accelerator that handles the compute-intensive parts of the program. And the question becomes now, how do you distribute the different layers and different models to different accelerators? So that's a profiling, dynamic or static profiling mechanism. So this is this heterogeneous accelerator, we called it Mensa, and this combines essentially more data-centric and processor-centric at the same time. So this way you can cater to very different characteristics of different models. These are characteristics of some of the models that are proprietary that were used at Google in edge neural networks. And you can see that there is a huge variation in the characteristics. On the x-axis, you have the parameter footprint. On the y-axis, you have the arithmetic intensity, flops per byte. And there's a orders of magnitude variation across different families of models. Some of them are much better fit for data-intensive or data-centric accelerators. Some of them are much better fit for compute-centric accelerators because they don't have a memory problem. So that's the idea, designing processing near memory accelerators for some layers and identifying which layers should go to the processing near memory accelerators and distributing them to the right place buys you a lot of performance. This is a picture that I showed you earlier. Essentially, you can improve energy consumption significantly compared to the baseline edge TPU. It can also improve performance significantly. Again, I will not go into this detail, but you can read the paper. We've also more recently looked at using near memory processing for accelerating LLMs. Clearly, everybody needs to be working on LLMs these days, right? I'm joking, of course, not everybody needs to be, but it's important to consider them, at least as a workload. That's what I tell my students. Even if you don't like LLMs, it's good to show some workloads, right? But in this particular case, we wanted to accelerate. We wanted to show how to accelerate things. And the basic principles in the end tend to be similar. So the Google Neural Networks paper had a heterogeneous accelerator. Here we have also a heterogeneous accelerator. The idea is there are some layers fully connected layers, for example, that are so compute intensive that they should be executed in a TPU or GPU because they're not that memory bound. There's a lot of arithmetic complexity there. There are some fully connected layers that are much more memory intensive, so they can be shipped to a near memory processing DRAM chip. In this particular case, we didn't use 3D stacking, but we used actually 2D DRAM with bank level processing. But here, the computation intensity near the bank needs to be higher. You need to have much more computation capability. And there are some layers like attention layers that are so memory intensive in terms of both capacity and bandwidth that you can actually decouple them. And you can have put them in a interconnect that's far away, let's say disaggregate them. And you can also have a near memory DRAM chip that can actually have less arithmetic computation capability for them. And then the question becomes, how do you identify the layers and how do you ship them? For that, you need, again, some profiling heuristics. So if you think about it, these two papers are conceptually very similar. They're really designing heterogeneous accelerators, one for edge neural networks, the other is for LLMs, even though they were developed by completely different people. I think I'm the only intersection between them, let's say. But I think, hopefully, in my opinion, this sort of acceleration is important. We need to have near memory processing components and also compute intensive components because a workload consists of heterogeneous things, right? You cannot just have near memory. You cannot just have compute. You really need to combine both. Okay, and then there's one last thing that I will talk about in near memory compute before I go into processing using memory. This is another paper where we wanted to really get rid of GPUs. This actually doesn't have very intensive compute units, or actually it embeds them somewhere else other than the GPU. The idea is to really exploit the CXL technology so that you can accelerate LLMs without having extremely high computation density somewhere. And here we actually use some DRAM devices. In this particular case, it's similar to SK Hynix's GDDR6 PIM that can do some intensive computation, matrix computation. And those computations that cannot be handled by those devices, let's say more sophisticated computation that are not matrix-like or more control-intensive computation. There are some processing near memory units that are inside the CXL device. And these CXL devices coordinate with each other with some communication primitives that we add to essentially do LLM computation. In this particular case, we were able to eliminate the GPU, and compared to the best prior GPU system, we were able to get significant throughput and hardware cost reduction. Throughput improvements, hardware cost reduction, and TCO improvements. Again, I'll refer you to the papers, and the source code of this is openly available. There are many more examples of near memory processing that I will not go into because I'm going to go into something a little bit different. And you can find them in this paper that we have written. It's almost 99 pages now. But we need to update it because the last update for this was February 2025. But this is probably a good example that covers a lot of the recent work. And we're open to feedback on this. So if you find some work that we don't have here, because it's very hard to keep up with all the work in this area these days, which is a good thing, I think, for the area, we'd be happy to include it and also improve things that may be wrong in the paper. Okay, let's jump into processing using memory. I'll spend some time on it so that I can foreshadow the upcoming talks, because we're going to talk about processing using memory in this workshop. And then we're going to talk a little bit more about processing near memory in the later part of the workshop. But in the end, as I said, these need to be combined. Processing using memory, as I said, you exploit the operational principles of memory to do computation without adding special logic. You could also add special logic also to ease the effort. But let's take a look at without adding special logic. And we're going to focus on processing using DRAM. And this is a fascinating area because it's an area of discovery from my perspective. You can discover, you can think about, this is how DRAM operates. And if this is what I know about how DRAM operates, can I do some logic function to it? This is a theoretical perspective. And there's also a practical perspective. This is the lab I have. I have an FPGA where I can violate the DRAM timing parameters. Based on what I know about the theory of how DRAM operates, can I abuse DRAM, meaning violate the timing parameters to show that you can actually do computation and real commercial off-the-shelf DRAM chips without changing anything? And Ismail is going to talk a lot about that, for example, because he's done a lot of work in this area. So we have shown that both theoretically as well as practically you can do bulk bitwise operations. You can do bulk bitwise copying, initialization, and or not majority nor NAND. You can do true random number generation, physical unclonable functions. And if you want to do a more complex computation, you need to add some support for lookup table-based computation. And I think these are all very interesting. I'm especially, I mean, all of these are interesting, but we need more development on the lookup table-based computation that happens in DRAM, because DRAM has a lot of capability for lookup table-based computation. And most of these come at low cost. Use the analog computation capability. And the primitives are essentially activating multiple rows, either sequentially or concurrently, performs either data movement or computation. That's it, basically. Lookup tables is a little bit different, of course. And this happens even in commodity off-the-shelf DRAM chips. That's the fascinating part, I think. Okay, and you get significant performance energy improvements. So let's take a look at one example. I'm going to take, basically, I'm going to take some of the early examples, and Ismail is going to build on some of these. Let's take a look at in-memory copy. Let's not even talk about computation yet. What if you want to copy this white row to this gray row in DRAM? How do you do it today? Basically, today you have to go through the processor, right? Byte by byte, you bring the data to L1, and if you know what you're doing, and if you have done your, let's say, homework, you can do it. You don't need to pollute the caches. You can do it through the DMA engine, through the memory control. But you have to go through the processor chip basically today, and do the copy through the processor chip. Basically, you consume a lot of bandwidth, latency, energy, etc. Again, let's take the picture of a 10-year-old and set up the problem for the 10-year-old. Say that I have these two things, white and gray. I want to copy the white to the gray, and they're really next to each other in memory, in this place. How would you do it? Probably they will say, just do this. They wouldn't come up with this processor-centric solution. And again, you can test this, probably. Maybe I should teach a psychology class where we test this on people. Hopefully, they will not come up with this terribly convoluted solution that goes through the processor, right? If two things are next to each other, just do it over there. And that's what we're proposing. That's not a radical idea from my perspective. So this is low latency, low bandwidth, no cache pollution, no unwanted data movement. And if you actually do this in an unoptimized way, you get, well, you can optimize even further, basically. You get significant energy and performance improvements. This is the idea of row clone that we have published some number of years ago. So if you look at how to do it in DRAM, this is the DRAM subarray, a bunch of rows, and there's a row buffer over here. So essentially the sense amplifiers. You first activate the source row, which brings the data into the row buffer. This is how DRAM operates. And then we activate the destination row in quick succession, which deactivates the source row and connects the sense amplifiers to the destination row. Basically, we use the sense amplifiers or the row buffer as a temporary buffer to move the data from the source row to the sense amplifiers and the sense amplifiers to the destination row. 2 consecutive activations. Negligible hardware cost. In our original paper, we did this theoretically, meaning with circuit simulations. And we showed that you could do this with negligible hardware cost. And you get significant performance and energy improvements, as you can see over here. And this is the original paper in 2013. So, and more recent work has shown that you can do this in real DRAM chips with almost perfect accuracy. Ismail is going to talk about that a little bit more. Let's talk about computation. How do you do computation? So this is 3 DRAM rows. I'm showing you only one cell in each row. These are the capacitors, and these are the access transistors. This is the bit line. Imagine we could do this on 8,000 cells in a row. And imagine we could do this on thousands of subarrays, so millions of cells concurrently doing the same operation. If you concurrently activate all these 3 rows, A, B, C, this is called triple row activation. All these 3 cells share their charge with the bit line. And if at least 2 of these cells are charged in an ideal circuit, you'll get the charge state at the end in the sense amplifier. If at least 2 of these cells are discharged, you get the discharge state. At least 2 of 3 is a majority function. So this is essentially a bitwise majority function computation, as you can see. Bitwise majority is nice. If you ask Donald Knuth, he has a very nice chapter on this. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Nice. Now we have some logic functions without adding any logic. All of this is happening inside the DRAM. Well, we add some logic to do triple row activation, and the implementation is in the paper. We're happy to talk about it, but I'm not going to go through the implementation. The question is, this is not functionally complete. So how do you make it functionally complete? You need to have a not clearly, in addition to an AND, or not and majority. That's also functionally complete. And to be able to make functionally complete, we propose something that's not easy to implement, which is basically connecting. So if you activate one row, the complement of the data is on the other end of the sense amplifier because it's a cross-coupled inverter. This is the sense amplifier. You can basically connect this back to this subarray. And that's not easy to implement. It's a bit expensive. That's okay. People have developed better methods of implementing it. A paper doesn't need to solve all the problems in the world or all the problems with an idea. It doesn't need to be immediately implementable. The good news is it inspired other people to figure out how to implement this. And there needs to be more work in that area still. But basically, assume that you also can implement this inversion function, which is not. Now you can actually rethink your algorithms to map to this bulk bitwise computation model that's functionally complete. And there are many algorithms that are also already naturally fit for this because people have been designing bitmap indices that do bulk bitwise computation, databases like that, web search engines, DNA sequence mapping, encryption algorithms, etc. And in this paper, we showed on databases that are designed for bulk bitwise operations, you get significant performance energy improvements. This is the Ambit paper from 2017. I have another story for this. This was rejected 4 times before it got accepted, but but I really like this paper. Not because it's my baby, it's really Vivek's baby, but anyway. So how do you actually generalize this framework, make this more programmable? Because clearly you have this bulk bitwise execution model and you can throw it at the programmer and the programmer deal with it. Some programmers will deal with it, but most programmers cannot even think about it, let's say. So we actually designed a framework to take advantage of it that I'm not going to talk about. Maybe Ismail will get to that a little bit more. The idea is basically any function can be expressed as a hardware circuit that uses AND or NOT. You express that function, let's say convolution or matrix multiplication. You express that as a hardware circuit. We use electronic design automation tools to optimize that circuit, turn it into majority inverter graphs, and optimize the majority inverter graphs to reduce the latency. And then we have a pass that actually compiles it down to triple row activation and row clone operations. And this way you can integrate that function as an instruction in your sequential programming model. And when that function is invoked in your program, that gets shipped to the memory controller that executes the microprogram that consists of triple row activation, row clone, etc. So that's the idea. In a sequential programming model, an instruction gets shipped to the memory controller, which is executed as a microprogram using DRAM commands. Again, I didn't expect to talk about this, but maybe you'll talk about it a little bit more. Now, the question is, how do you make this better? This is more recent work by Geraldo, who's one of my recent PhD graduates. And one of the issues with bulk bitwise is the length of the vectors is very large, 8 kilobytes. And existing compilers cannot even exploit this large vector length. So if you really want to take advantage of existing compilers and compile into exploiting this bulk bitwise operations in DRAM, you need to also change the DRAM such that you do these operations at a smaller granularity in DRAM. And the idea is we actually use fine-grained DRAM where we isolate some mats from others by segmenting the word line. This way you can activate a smaller fraction of the row. And this way you can actually do some operations on some of the rows or some of the mats while doing some other operations on some other mats. So you can actually schedule different types of operations on different mats. That's why we call this multiple instruction, multiple data. Different data is operated on using different instructions. And there's more in that paper that I'm not going to go into, but we actually released the LLVM pass that actually does that compilation. And to enable this, you really need to have some sort of fine-grained DRAM support, which is actually good for energy efficiency anyway, for other reasons. Okay, I'm going to skip these because we don't have a lot of time, but maybe you're going to talk about some of that, maybe not. So there's the compiler support. Geraldo organized a lot of these processing in memory tutorials and workshops in the past, so he talked a lot about that. If you want to learn more about MIM DRAM, you can look at, I guess, the one that was organized at Micro, for example, in 2024. So basically, transparently to the programmer, the compiler extracts SIMD parallelism and constructs the processing using DRAM program. This way, the programmer doesn't need to do anything. Of course, one downside, if the programmer doesn't need to do anything, you're really restricted to the compiler. And unfortunately, compilers today, even today, are not very good at exploiting or automatically vectorizing programs. So in my view, this is a good approach, but we should also be using programmer support that people have done for GPUs, for example, to actually get the programs to a point where the compilers can actually compile nicely with vectorization. So here we actually looked at applications that were more amenable to this. There's more work to be done in this area to enable much more irregular applications to execute on this sort of substrate. And for those applications that are very good fits for this, that's a really important thing, you get significant performance energy efficiency improvements compared to CPUs and GPUs. If it's not a good fit, then you'd better execute them on the CPU. But this is also a research topic. How do you actually partition the work between this sort of execution model and a CPU or GPU type of execution model, for example? More recently, we've looked at making this better because it turns out, depending on the complexity of the operation, depending on the bit width, different types of addition and multiplication algorithms and different types of data representations could be good. For example, 2's complement may be good, 1's complement may be good, or redundant binary representation can be good for doing different types of operations. And in this work, we actually have a library where you can dynamically identify the bit precision and decide what kind of arithmetic algorithm to use in processing using DRAM. So this is actually one of the state-of-the-art works, which is very interesting, I think. There's a lot of interesting thoughts in it, and there needs to be more work in this area. How do you rethink how you do arithmetic and how you even represent the data, given that you have this sort of computation capability inside the DRAM, which is different from how you do addition in a processor-centric world, right? Here, the addition is bit serial because you're operating a lot of bits concurrently, but each operation needs to be bit serial. But again, there can be trade-offs over here. How do you do parallelism in that case, right? You don't have a multiplier. You're doing multiplication using DRAM, right? Okay, this is also as an interesting story. This paper was rejected from ASPOS after satisfying every single revision requirement. That also happens. I talked to another person who was rejected the same way. You can talk to Sogata about this. Do you agree with this? Yeah, he agrees with it. Yeah. And it was also rejected from other conferences, you can read over there. Okay. Maybe I'll let you talk about this. So basically, one of the fascinating things is existing DRAM chips are already quite capable. Maybe I'll talk about PyDRAM. Are you going to? Okay. So we have built infrastructures that show that you can do row clone and true random number generation in DRAM, and PyDRAM is one of those infrastructures, at least a more recent one. It's also an open source one. When we did the true random number generation in DRAM, you violate the timing parameter in real DRAM chips and you get random numbers, but which is actually fascinating. We did that on LPDDR chips. PyDRAM replicated that. And in PyDRAM, you can run an end-to-end application on a DDR3-based system. The application executes on the RISC-V processor on the FPGA. And we have the memory controller that is soft. We modified it. And when the application sees a page copy, there's also some operating system change that enables the copying, the destination of the copy to be allocated in the same subarray in DRAM. And that page copy gets shipped to the memory controller. Memory controller violates the timing parameters, and it knows exactly which rows that page copy is mapped to. It violates the timing parameters, activate to activate timing parameter, 2 consecutive activates, such that a page is copied from one row to another row in DRAM. And this happens essentially in real DRAM chips, because violating that timing parameter in real DRAM chips enable the copy. So it's not only theoretical. In real DRAM chips, if you violate the timing parameter activate to activate, you get a page copy. And we have shown in this work that you can actually build an application on top of this with some effort, of course. And these are some micro benchmarks. You actually improve. These are the real micro benchmark running on this real system that shows that you can improve data copy initialization throughput significantly. Now, the reason these improvements are much larger than what we have seen is because the processor that we have on the RISC-V, processor that we have on that FPGA is very wimpy. It's like 50 megahertz. It doesn't have any latency tolerance mechanisms. There's more here. And again, we're happy to support people who are working on this. It's not an easy infrastructure to work with, but I believe there's more work that needs to be done in this area also. And Ismail more recently showed that DRAM chips are already quite capable. I'll let Ismail talk about that. He has shown that essentially you can get NAND, NOR, AND, and OR operations, but he will talk about that right after me. This is fascinating. And essentially, he's validated with real DRAM chips using our lab. And multi-row copy, for example, is very, very reliable. And NAND, OR, and NOR is not as reliable, but still, it exists. So you can actually do a NAND in DRAM in a bulk bitwise manner. I'll let him talk about how to do that. So there also always this question, what else can we do using commodity memories? And this is a good question to ask. That's one of the things that this sort of FPGA-based infrastructure and lab enables. And I think Ismail keeps asking this question. One of the things that we know is true random number generation. By violating the timing parameters, you get some rows that fail randomly. And there's actually very good random number generators. And we worked on this area for a number of years. This is DRange, Quark TRNG. And more recently, Ismail published a paper. And Nisa has done work on system level end-to-end design of these true random number generators. I'm not going to talk about these, but there's more to do. Lookup tables are also important, as I said. I think there's more work that needs to be done in this area, because in this work, we've actually looked at different ways of doing lookup table-based computation, but there's a lot more that you can do. And with some more creativity and thinking, maybe you can do actually much more simpler approaches than this. Flash memory also has a lot of these operations. Later, Rakesh will talk about some of these. And if you can actually exploit some of these operations, Rakesh will also talk about doing homomorphic encryption using flash memory. This is, again, processing using flash, which I don't have time to talk about. So I covered both of them relatively quickly. There's a lot more in this paper that we need to update, and in some other papers that we've written. One of the key issues in processing in memory is adoption. It's already difficult to change the paradigm, change the hardware. Getting it adopted is even worse, even harder. I think this is actually important. Late Arvind, who was at MIT, he gave a keynote at ISCA in 2005. And his keynote was on data flow, of course, because he's a pioneer of data flow. And he said that data flow is, we talked about data flow. It's a nice idea, a great idea. Of course, he's clearly passionate about it. And he also reflected on what they could have done better in data flow. And the key thing he said was, we should have focused more on software, meaning enabling this hardware. And the key takeaway I got as a graduate student from his keynote was, okay, you can design any hardware, and it could be beautiful. But if you actually don't get it adopted, then it's very difficult to make a case for that hardware. And we've seen that in a lot of hardware also, that people have actually designed. IBM cell processor is another example, for example. So there are a lot of issues in adoption of PIM, and a lot of them are software and system level issues, actually. Applications of software, how do you enable those? What applications benefit? How do you make a case for it? Ease of programming. How do you actually make it easier for the masses to work with this so that they don't need to deal with the details? This is what GPUs have got mostly right, let's say, at least NVIDIA. Interfaces and compiler and hardware support. How do you actually enable system and security support? There are some tough issues over here: coherence, synchronization, virtual memory. Runtime and compilation systems. How do you enable data mapping that happens transparently to the programmer? And infrastructure to assess benefits and feasibility. That's why we've been developing a lot of infrastructure: DRAM vendor, Remulator, etc. So these are difficult. One of the most difficult things is a change of mindset. I think this is also potentially coupled with some of these things, but our mindset is very processor-centric. Our education is very processor-centric. A lot of people, all people as far as I know, when they take a computing course, it's very processor-centric to begin with, right? Okay, so we need to have a much more memory-centric mindset, I think. So one of the, Geraldo, who was organizing this workshop for more than a year, actually, he's organized 6+ incarnations of this workshop. Before there was one, but Geraldo did a thesis that solves some of these challenges across the stack. He looks at programming models, system support, as well as hardware support like MIM DRAM. So we've been doing these tutorials. If you're interested in the history, you can take a look at it. It started as a real processing in memory tutorial with Juan. And more recently, we've done with Geraldo PIM tutorials. And there's more that's going to come up. Well, this is today, I think. There's more in SPLOS and ICS, and we plan to organize more. But I think I would also recommend people to go to the DRAM vendor and Remulator tutorial, because it's very tightly coupled. We decided to do this tutorial to enable, let's say, more progress in these areas. And if you're interested, you can also look at the keynote talk that I mentioned. A lot of things that we're going to discuss over here will be open source that I already discussed. You can find them online, and papers are all online. Let me conclude. So I think changing a paradigm is not easy, especially ingrained paradigms. We've seen this in science many times, like Copernican revolution. People did not believe that Earth was revolving around the sun for many, many years. And clearly Copernicus was not able to succeed in this. It took a lot of smart people and hundreds of years to go against the current, right? I'm not saying that this revolution is as hard as that one, but they weren't fighting trillions of dollars. Here we're fighting trillions of dollars also. So there are actually some interesting things. They were fighting even worse things maybe. Their lives were at stake because you're going against some very powerful structures, right? That defended how science should not be done. Okay, so basically long-standing and entrenched dogma had to be overcome. I feel like we're kind of like that in how we design systems. Because we've always done it this way, we should be doing it this way. And it becomes kind of dogmatic at that point. And sometimes in their use, you see that actually. You propose something and you get, this will never be adopted. Okay, why? Okay, basically we need to change the processor-centric paradigm because this can enable many benefits, some of which are not even quantifiable or predictable, but this will not happen overnight. And memory, in my opinion, we should be thinking of memory as a combined computation and storage substrate. And once we do that, I think this can lead to orders of magnitude energy and performance improvements. And unmodified DRAM chips are already capable of computation, as Ismail will go into a little bit more. And if this is the case, if this thing that's DRAM, that's designed as memory, is already capable of computation by abusing it, why not do more? Right? Because if you didn't do anything to enable this computation, and we've shown that you can do computation, why not do more? Right? Now imagine what you can do if you can actually go and design this chip a little bit more to do computation. Now you can unleash a lot more capability. So I think we have a lot more exciting research to do and efficiently enable. We need to do research and design across the computing stack without ignoring adoption issues. Not all papers need to deal with adoption issues. A good idea should be published regardless of adoption, I think, because adoption can come later, right? A paper doesn't need to be implementable tomorrow. In fact, if it's implementable tomorrow, then maybe that's not extremely forward-looking research in at least computer architecture domain, right? Okay, so with a proper, but we need a proper mindset and infrastructure shift. So this thing is a computing device. You can argue against that, of course, but it does computation. And it also does communication and storage. And it does it in a way that's tightly coupled in some way. And we don't quite understand it. And I don't claim to understand it. And most people who work in the area don't claim to understand it also. But it does in a very different way than the way we design our systems. But it does in a very energy efficient way also. I'm not saying we should design exactly like this, but we should take some of the principles as inspiration. And if you want to design intelligent systems, which I believe a lot of people are trying to do, maybe we should think about how intelligence is also done in these other systems. And it's not done in a processor-centric way for sure. Since we're in Sydney, how many people have gone to the Sydney Opera House? Okay, that's good. I'd recommend you go to the Sydney Opera House. It's an architectural miracle, let's say. There are no miracles, but architectural, let's say, masterpiece. But this architectural masterpiece came to be because there was a champion reviewer for it. This guy, how many people know this guy? Eero Saarinen. Well, okay, so Gata knows. How do you know? What? Okay, you had real architecture. Okay, that's good. Have you visited what he has done? Yeah. There you go, yes. And IBM TJ Watson Research Center. Are there people from IBM here? Okay, anyway. But perhaps most importantly, this guy was the champion for the Sydney Opera House. Basically, he was crucial in the selection of this. So there was a committee that actually got proposals for the Sydney Opera House. It was a small committee. And a jury discarded the architect's design that you have seen, or that you should see when you're in Sydney. But this guy said, argued for it, and he was a champion. He said basically, we should get this. We should enable this to be built. And that's why you see Sydney Opera House as it is, as opposed to something that's maybe less aggressive. It was not easy to build. This thing took, I think, 10+ years, plus a lot of money. But you can see it stand. And this person who was a champion was the architect of the Gateway Arch in St. Louis. You can also go over there. The good news is I think this person was an enabler also, right? I think we should be enablers to enable ideas and better things in our community, as opposed to disablers who try to find all the bad things in an idea that would otherwise make a difference. Because clearly, if this guy didn't exist, you wouldn't see this. Okay, anyway, maybe you would see something else. Okay, so I'll acknowledge a lot of people, most importantly, my group, and you will hear some talks from them. This is our most recent newsletter. You can take a look at that. I'm happy to take questions if there's time. If not, Ismail, it's your turn. Okay, questions. Okay, wow. Yeah, any questions? Feel free to ask. Yes, please.
Memory-centric computing. Do you think it will replace GPU or NPU in the future?
Yeah.
How many percent field or application it will replace in how many years?
Yeah, okay, that's a tough question. You know, I cannot answer that. Replace, I think replace is tough, even though in one paper we argue that you could replace, because I think the future is very heterogeneous, basically. Memory-centric will be a part of it, but clearly there will be extremely high compute-centric approaches like CPUs and GPUs. But assuming that memory-centric approaches come to be, I think how a CPU and how a GPU looks like will be different also. Certainly the memory hierarchies will be very different. In my opinion, they should be much more specialized for computation without having a lot of memory on them. So GPUs also have huge memory hierarchies today. Maybe we can remove a lot of that in future GPUs. But completely replacing it is tough, in my opinion, because it's, I think the major reason, unless we have a huge leap in technology, which is, let's say, it's very difficult to integrate memory and logic perfectly today. 3D stacking is one approach, but 3D stacking has its limitations like thermal, etc. So it's easier to do compute only to get the highest compute bandwidth and compute capability. So I think in compute-intensive portions of programs, it's very difficult to replace something like a GPU or TPU. I'm not arguing for that either. Yeah. I would also not say that. I mean, this could be very general purpose. But again, if things evolve nicely, each application will be distributed across multiple accelerators. Some of them compute-centric portions or compute-intensive portions will go to a CPU or GPU. More memory-intensive portions will go to, again, this is a very rough classification, but more memory-intensive portions will go to more memory-centric accelerators. Similar to what we have described with Google neural networks and also the PAPI works.
Okay, if you design a system, what's the ratio between the general purpose the computing intensive and
Yeah. Yeah, I mean, that's if you design it today, you have existing components. There needs to be more research to do that. I think the system also needs to be flexible, right? You need to be able to actually add more components and remove more components as well.
Okay.
Yeah.
Thank you.
Sure, you're welcome. Other questions? Or are people ready for coffee? I have my coffee, so I have an advantage here. Okay, maybe people are ready for coffee. Okay, we'll continue after the break.
Yes.
Is it 11 or
11.
at 11 a.m.? Oh, there's a question? Okay. at 11 a.m. All right, see you soon. So is the problem solved now with the cable?
Yeah,
Yeah,
it wasn't disconnected at all, so.
that's good. Yeah.
Yeah.
Okay. Yeah, it was annoying.
Fine, I guess.
Yeah, well, that was not the plan, but fine. Backup plan, yes. Plan B. Hey, Mohammad.
Exciting.
Yeah, that's good to hear. Yeah. We need more sleep, but. Oh, thanks.
I celebrated with some cake.
I already have a banana cake, but is that better?
This is the one we had yesterday.
Oh, okay. Maybe I'll take a small piece, not.
There is a small piece indeed.
There is? Okay, that's good.
Issues,
Because I didn't taste that
we
one.
don't
I
really
didn't.
have utensils.
That's okay.
So you can just take it and bring back, like,
Oh,
because
okay.
there's plates. And,
Maybe I'll go get utensils from downstairs.
Yeah.
They might have something right now.
Yeah, there's like
Yeah,
coffee.
okay.
So.
Okay, I'll get.
yes,
Yeah.
The cake is here.
Okay, thanks. Yeah, I'll come and get it from you. Hello, how are you?
Yeah, good.
Good to see you.
Yeah, it's very nice organizing the workshop.
Oh, thank you. Yeah.
And sorry, I bad news and good news for you.
Yeah.
The bad news, there are big reorganization inside Huawei.
Oh, really? Okay.
Yeah,
In
probably
Europe or everywhere?
everywhere.
Okay. Wow. Okay.
Probably we will cancel the talent fund.
Okay. Really?
The
Oh, okay.
decision,
That's too bad.
decision from the high level.
I see. Okay.
And the good news, Dr. Du will come back.
Oh, okay. He'll come back.
Du will come back.
Yeah. Okay.
He will be the president again. The
Okay.
president of European Institute.
Okay.
And then I think we can discuss with him to
Okay.
for the other solution.
Sure. Yeah. Yeah. Looking
I'm so
forward to
sorry
it. That's
about
okay. I
that.
understand. Yeah. I mean, it's not in your control,
Yeah,
Yeah.
that's the order from the boss.
Sure. No problem. Yeah. It's
Yeah.
okay.
Then if the company has some pressure, then we have to reduce the investment.
No, really. In Europe?
Not totally.
Totally. Really?
Yeah. So many product line and labs now have pressure to explain the investment value.
I see. Yeah.
So sorry for that.
That's okay. I understand. Yeah. Yeah. Cool. Yeah. Good to see you. Yeah.
I think we can definitely, find other new
Sure.
opportunities, and probably we will have some cross.
No, sure. There you go. Yeah.
Test audio, test audio. Ah, it's not on Zoom. Test audio. No, it's not muted. Hello. This is good. Okay. This one. You heard me, right? The audio is fine. Okay. Slides are also moving, right? I heard him. He's come. Yes, he arrived. Yes. Okay. I can start directly, I think. Okay. Hello, everyone. I hope you get a good coffee in the break. So today I'll discuss processing using memory and real DRAM chips, especially 3 works that I'll focus on, the latest 3 works that we did. So again, a brief self-introduction. I'm Ismail. I'm a PhD student in software research group under the supervision of Professor Onur Mutlu. I'm interested in general computer architecture, processing in memory, specifically processing using DRAM. I'm also interested in DRAM robustness, safety, security, and reliability issues such as row hammer, row press, and column disturb. And in this talk, I'll be focusing on these 3 works. The first one is functional complete Boolean logic in real DRAM chips. Other one is simultaneous manual activation of the shelf DRAM chips. And lastly, pot hammer, which will be an experimental analysis of the read disturbance effects of this processing using DRAM operations, which could be interesting to some folks. So let's get started with the first one, functional complete in Boolean logic in real DRAM chips. This was published 2 years ago in HPCA 2024. So the motivation, everybody knows that processing using DRAM can alleviate the performance and energy bottlenecks caused by the frequent data movement between main memory and computing units. And prior work such as compute DRAM, prac DRAM show that existing DRAM chips, the off-the-shelf DRAM chips, can perform 3-input majority and 2-input and OR operations inspired by the Mbit paper. So, but the problem is this proof of concept demonstrations on off-the-shelf DRAM chips do not provide functionally complete operations. You only have majority or 2-input and OR operations. And they don't provide NOT operation, and they can only perform and OR operation with only 2 inputs. So in this study, we test a total of 256 DDR4 chips from 2 major DRAM manufacturers, SK Hynix and Micron. Samsung. And the key results are we observed that off-the-shelf DRAM chips can perform NOT and 2, 4, 8, and 16 input AND, NAND, OR, and NOR operations with a relatively high reliability. I'll explain this success rate metric later. And we also observed that data pattern and temperature of the DRAM chip only slightly affect the reliability of these operations. There's almost like less than 2% change in the reliability metric that we have. So before we go into this processing using DRAM operations, let me refresh your minds with the DRAM organization. So this is a DRAM module, a typical DRAM module, and each black square is a DRAM chip. Inside the DRAM chip, we have many DRAM banks, and within each DRAM banks, we have many subarrays, 64 to 128, and in between each of them, we have sense amplifiers. And when we take a closer look to some parts of this subarrays and sense amplifiers, so the subarrays are 2-dimensional array of DRAM cells. And a row of DRAM cells called DRAM row, and they're connected through word line, and a column of DRAM cells are connected to sense amplifiers via bit lines. So there's an important, let's say, feature that we will leverage in DRAM. So there's a thing called DRAM open bitline architecture, which is to achieve high density in DRAM chips. What it does is that it connects two subarrays, two physically adjacent subarrays via sense amplifiers. Here it's a, let's say, zoomed in version. As you can see, there's a one sense amplifier here, and there's one bit line coming from the upper subarray, and there's a bit line bar coming from the lower subarray. So whenever we perform a DRAM operation such as activation, once we activate a row in, for example, upper subarray, the lower subarray's bit line will serve as the reference for the sense amplifier, whether to understand if it's lower, let's say, lower than 1/2 or higher than 1/2 to understand it is 0 or 1. So, and the sense amplifier is actually two back-to-back NOT gates. So when you have after a successful activation, the bit line and bit line bar will have a complementary voltage as the sense amplifier that consists of two back-to-back inverters. And data is internally accessed in a row granularity in DRAM. Let's take a look at the three important DRAM operations that we will focus on. The first is activate, which will fetch the row contents in the sense amplifier. And then column accesses are serviced from this sense amplifier, such as read and write. And finally, the subarray and the bank actually needs to precharge to get ready for the next row activation. So in this study, we experimentally demonstrate that off-the-shelf DRAM chips can simultaneously activate up to 48 rows in two neighboring subarrays in the same bank, and can perform NOT operation with up to 32 output operands, and can perform up to 16 input AND, NAND, OR and NOR operations. So in order to test this, validate this, we have a FPGA-based DDR4 testing the structure developed from DRAM Bender that enables us to have a fine-grained control over DRAM commands, timings, and temperature. And in order to test many instances of modules and everything, we have a laboratory to understand the memory. And in this study, we test a total of 256 DDR4 chips from two major manufacturers, spanning many die densities and die revisions. So let's take a look at the first observation. So the key observation here is that activating two rows in quick succession can simultaneously activate multiple rows in neighboring subarrays. So here is a pictorial example. We have subarray X and subarray Y, and they are physically adjacent. And let's assume row A is in subarray X, row B is in subarray Y. So this is our key command sequence. So what happens when you do activate row A, precharge activate row B while respecting the timing parameters? You will only activate a single row at a time. However, we observe that if we greatly violate these timings, what happens is that you actually trigger many more intermediate signals in the row decoder circuitry, because the first activate will activate the row A, for example, and then you issue precharge, and then you immediately issue another activation. What happens is that you prevent this precharge circuitry to work correctly, so that you will still have multiple signals activated in this row decoder circuitry to decode the row address. And as a result, you will activate many more intermediate signals. And this will result in activating not just two, but multiple rows. So the key results that we observe is that off-the-shelf DRAM chips have two distinct sets of activation patterns in neighboring subarrays. So the first is that exactly the same number of rows are activated in each subarray. So we observe that we can activate up to 16 rows in each subarray, and total of 32 rows. And the other one is twice as many rows in one subarray activated compared to its neighbor subarray. Here we have, for example, we can activate up to 16 rows in one subarray while activating up to 32 rows in its neighbor, a total of 48 DRAM rows. So then how do we leverage this to perform NOT operation? So the key idea is to use this NOT gate in the sense amplifier. We will connect rows in neighboring subarrays through a NOT gate by simultaneously activating them or consecutively. So what the key idea is that you activate the source. For example, source is in the upper subarray and has a voltage value of A. And it will be sensed and amplified. And in the other side of the bit line, you will have the negated value, which is this connected destination. And if you activate the destination without deactivating the source, what will happen is that since you have the negated value over there, you will copy the negated value of the source into destination. Now let's take a look at how we can perform this NOT operation in real DRAM chips at a lower abstraction level. So here we have source and destination, which are in the different subarrays, and they're connected to the same sense amplifier, and they're essentially initially ground, 0. So what happens when we activate the source is that it will connect the source to the bit line. When we wait to the nominal timing parameters, it will drive its voltage to its bit line, and it will drive the negated voltage value to its in the bit line bar because of the NOT gate over there. And if we issue per charge and immediate destination, so we will prevent performing the per charge operation. What happens is that it will connect the destination to bit line because we issue activate the destination. But since we violate the timing and prevent per charge to perform its operation, the sense amplifier is still enabled, and the destination's bit line is still at VDD. So as a result, when you wait long enough, the negated value of the source, which is VDD, is written to destination. This is how we realize NOT operation in real DRAM chips. And to evaluate the reliability of NOT operation, we define a metric called success rate for a DRAM cell. And success rate for a DRAM cell refers to percentage of correct trials. We test a total of 10,000 trials and record the success rate for each tested cell. For example, here you see one example. It has 4 trials. Half of them is correctly negated. Half of them is not. So the success rate for this cell is 50%. And this analysis provides us 2 key takeaway lessons. First, off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows. And second, temperature has a small effect on the reliability of NOT operation. I'll show you the one result. So here in the x-axis, we have the number of destination rows, and the y-axis, we have the success rate. And we observe that there's at least one DRAM cell, which more than a DRAM cell, but that can perform the NOT operation with 100% success rate in every tested number of destination rows, which shows that off-the-shelf DRAM chips can perform these operations with up to 32 destination rows. So now let's move on to the last part, then how we perform 16-input AND, NAND, or AND NOR operations. The key idea is to manipulate the bit line voltage to express a wide variety of functions using this multiple row activation. So let me give the key idea by showing 4 cells here, X, Y, A, and B, 2 from each neighboring subarrays. So now if we activate these 4 cells simultaneously, the bit line at the bottom subarray becomes the function of voltages in X and Y. Essentially, the function is average, actually. And the bit line in the top subarray becomes the function of voltages A and B. So average of A and B in one bit line, average of X and Y in another bit line. So after the, let's say, the activation is done, sense amplifier will compare the voltages at the bottom bit line to the voltage at the top bit line to figure out which one is higher, and it will drive 1 to the higher one, 0 to the lower one. So let me show you the basic intuition to perform 2-input AND and NAND operation. So here for this example, we have 2 subarrays, reference subarray and compute subarray, each of which consists of 2 cells. And in the reference subarray cells store VDD and VDD over 2. As a side note, we can store VDD over 2 thanks to a prior work called FRAC DRAM in real DRAM chips. And in the compute subarray, we have X and Y. With this setup, if we activate all these 4 cells using activate per charge activate sequence, we will get AND of X and Y in the compute subarray and NAND of X and Y in the reference subarray. To simplify things, let's assume bit lines will have the average voltage of their corresponding cells voltage, such as reference bit line will have the average voltage of VDD and VDD over 2, which is 3 VDD over 4. And the compute subarray bit line will have average of X and Y. So let's start with iterate the truth table for AND and NAND operations. So here, in the first row of truth table, we have X and Y, our ground, which is 0 here. So when we activate all these 4 rows, 4 cells, what happens is that now the average of VDD and VDD over 2 is 3 VDD over 4, and the average of 0 and 0 is 0. So when sense amplifier compares the voltage on these bit lines, since 3 VDD over 4 is higher than 0, it will drive the reference cell as 1 and drive the 0 to compute cells. And in the second row of truth table, x is 0 and y is 1. Again, the reference bitline voltage is higher than VDD over 2, right? So what happens is the same as the first case. The bitline in the reference subarray will have VDD, whereas the bitline in the compute subarray will have ground. And in the third case, it's the same. The average of 1 and 0 is over 2, which is lower than 3 over 4, and we will have the same results again. In the last row of truth table, where x and y is both 1, what happens is that now the compute subarray's bitline has VDD, which is higher than 3 VDD over 4. As a result of this, you will get VDD in the compute subarray while getting the ground 0 in the reference subarray. And this will change the, let's say, result of the truth table. And if you have a closer look, the compute subarray is actually the AND function of x and y, whereas the reference subarray is actually the NAND function of x and y. And we can realize all these operations actually by playing, not all these operations, but AND and OR operations, NAND and OR operations, by playing the reference voltage. You can check the paper for more details how we do that. And the key takeaways from this analysis in real DRAM chip is that off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, NAND, OR, and NOR operations. And they can perform these operations with high reliability. And the data patterns slightly affect the reliability of AND, NAND, OR, and NOR operations. I'll show you the result for the first two. So let's see the results. On the x-axis, we have number of input operands, like 2 input and 2, 4 input and 8, 16, etc. In the y-axis, we have the success rate. And each color, the hue, will show the operation. So here we see that there is some, let's say, reliability issues, but still, off-the-shelf DRAM chips can perform 2, 4, 8, 16 input AND, NAND, OR, and NOR operations. There's at least one or multiple DRAM cells that can perform this with 100% success rate. And once we go to do 16 input, the reliability is actually more than 94%. So the extended version of our study is available on arXiv, and you can check the link here. And the code is open source, but yeah, I don't have the slides. I don't know. Yeah, it's over GitHub. You can check it. And this was the FCDRAM, the first paper. Now I'll move on to a quick summary of the second one. So for this one, again, the motivation is processing using DRAM is a promising paradigm, and we have some little functionality here. Our goal is to understand, the computational capability beyond the prior works and robustness of these operations. And in this study, we test a total of 120 DDR4 chips from 2 major manufacturers. And we find that we can not just perform majority 3, but we can perform majority 5, 7, and 9 operations. And we can copy one row's data to up to 31 different rows at once, simultaneously. And we also observe that we can actually increase the reliability of a majority, like in DRAM operations, by storing multiple copies of the input data and activating them at the same time. And we observe that on average for majority 3, it will give us more than 30% of higher success rate. And we observe that for these operations, operating conditions such as temperature, voltage, and data pattern affects the robustness of DRAM operations by up to 11.5% on success rate. And this is also open source, and you can find the link here. So as a quick summary, we can perform majority X, where X is greater than 3. We can increase the robustness of majority X operations, and we can copy one row's content to multiple rows. So let me give you the key idea how we perform this multi-row copy operation. So our key idea, since we can activate many rows simultaneously, we can copy one row's content to other simultaneously activated rows. Let's recall the row clone example where we copy a destination, source to destination. In row clone, we first activate the source row, which will copy its content to sense amplifiers. And then we activate the destination row to drive the sense amplifier's content to destination row. which will enable us to copy one row to another row. For multi-row copy, now we have several destination rows, and we first we open this source, sense amplifier will have the data, sense it, and drive the bit line with the source value. And after that, we will activate the destination rows at the same time. As a result, sense amplifier will drive its content to this destination rows. And for the results, we see that it's actually very promising. On the average, we can perform this copy operation up to 31 other rows, more than 99.98% of success rate. It's almost 100, but it's not 100. So we conclude that off-the-shelf DRAM chips can copy one row's content up to 31 rows with a very high success rate. And our paper is available on arXiv. We have many more analyses like SPICE analysis to understand why do we observe this and that. And we have I think a good way of reverse engineering hypothetical row decoder circuitry and explain why we can activate more than 2, 4, 8, more than one row essentially. And the work is open source and artifact evaluated, and you can find it over GitHub. And if you have any issues, you can open any issues or contact with me for these both. And this was the two works of showing the capabilities of real DRAM chips. But there are some issues in DRAM already, right, with read disturbance, such as rowhammer that Onur already told us. So in this work, which is published in ISCA 2025 last year, we analyzed the read disturbance effects of this multiple row activation-based processing using DRAM operations, such as multi-row copy or majority operations or this AND, NAND, OR operations. So the executives, let's move on to executive summary. So again, the motivation is the same. We can perform many processing using DRAM operations, and they rely on multiple row activation, either in quick succession, such as row clone, or simultaneously, such as majority, etc. But modern DRAM is subject to read disturbance, like row hammer, row press, and column disturb. So repeatedly activating even a single row induces bit flip in unaccessed rows. So the problem is no prior work studies the read disturbance effects of multiple row activation, activating multiple rows simultaneously or quick succession. So we would like to understand, is there any new effect over there with this multiple row activation? And we conduct an experimental study on 316 DDR4 chips from 4 major manufacturers to study this effect, which we call pot hammer. So we observe that pot hammer significantly exacerbates the read disturbance, causing up to more than 158 times reduction in minimum hammer count, minimum activation count to induce the first bit flip. And we observe that pot hammer actually bypasses the in-DRAM row hammer mitigation in DDR4 and induces more than 10,000 times more bit flips than row hammer. And we try to mitigate this effect and adapt the per row activation counting, which is the latest industry solution to row hammer for pot hammer. And we observe that the adapted solution incurs an average system performance overhead of 48%. So in this study, we actually categorize multiple row activation into 2: consecutive multiple row activation, CMRA, and simultaneous multiple row activation, SIMRA. So consecutive multiple row activation is where we do row clone. And for simultaneous multiple row activation, SIMRA is where we do majority tree, this AND, NAND, OR, and NOR operations that we discuss. And unfortunately, even activating a single DRAM row disturbs the data integrity of other unaccessed rows, like row hammer. And what we ask is that, so no one investigated this disturbance effects of multiple row activation. And we would like to understand is the effect is severe, right? So instead of activating a single row at a time, what you do is you activate them either simultaneously or in a very higher frequency. So in order to do that, again, we use the same infrastructure that we have, and we test 316 DDR4 chips spanning for 4 major DRAM manufacturers. And we cover, again, different die revisions and chip densities. And let's move on to the first effect of CMRA, consecutive multiple row activation. So this is how we perform row clone in real DRAM chips. This is the command sequence that you do. In order to perform a double-sided attack where we sandwich a row between these two aggressors, what we do is that we copy a row, one row to destination row by sandwiching a victim row. For single-sided attack, what we do is that we just copy a far-away row, which does not sandwich a victim row. So in the characterization method, we carefully sweep many row addresses, timing parameters, and data patterns, temperatures to understand the effect. And in order to assess the vulnerability, we use a metric called HC first, the minimum hammer count required in this, the first bit loop. So lower is worse. Basically, one hammer count means one activation of these two rows. So for example, here, what we do is that one hammer consists of one copy operation. And in between each hammering, we respect the timing parameter. And then we record the bit flips in the victim for both Comra and Simra. So let's look at the results where we compare Comra and row hammer. So in the x-axis, you see the manufacturers, and on the y-axis, you see the lowest HC first observed by a manufacturer. So, and the color code will show which operation that we did. So here in the SK Hynix, what we observe is that double-sided Comra decreases lowest HC first by almost 14 times compared to double-sided row hammer. It was 6,000, now it's 447. And for other manufacturers, the case is the same. The trend is the same. The lowest HC first reduces in all manufacturers that we test. And in the next experiment, we investigate how much HC first changes when we perform Comra compared to the row hammer across all tested DRAM rows sorted by reducing HC first value on the x-axis. And each curve in this plot represents a different DRAM manufacturer. Now let me walk through what this plot represents. It's a bit complicated, I think. So in the x-axis, from P1 to P100 shows 99% of tested rows. From P50 to P100 represents 50% of victim rows. And similarly, HC first change of, so if the HC first change is negative, that means that Comra reduces HC first compared to double-sided row hammer. For example, HC first change of -50 means HC first reduction of 50%. For example, row hammer HC first is 100, while Comra's HC first is 50. So what we observe is that more than 99% of tested victim rows experience lower HC first, and more than 2 to 3% of them experience an extreme reduction. And we conclude that the double-sided Comra decreases HC first for a large fraction of rows compared to double-sided row hammer. And now let's take a look at Simra, which things will get a bit more messier here. So we did the same characterization methodology. And to recall, Simra means simultaneous multiple row activation, where we violate timings between activate the precharge to activate multiple rows. So let's take a look at the results. On the x-axis, you see the simultaneous activated rows. One means row hammer. And the y-axis, you see the lowest HC first minimum hammer count in this first bit flip. So we observe that Simra reduces HC first by almost 159 times compared to double-sided row hammer. And this is regardless of number of rows that you activate. As long as you sandwich a row while you're activating multiple rows simultaneously, the change is drastic, like 26, 48, 33, 81. And we did the same analysis as before. We didn't just check the extremes, but we checked all the tested victim rows. And as you can see, everything is almost less than, 75%, and at least more than 25% of tested victim rows experience more than 99% of HC first reduction. For example, if row hammer's HC first is 100, the Simra's HC first is 1. So we conclude that Simra significantly decreases HC first for a majority of rows compared to double-sided row hammer. So now let's take a look at the mitigating part of the pot hammer. I'll be relatively quick because we don't have much time. So we analyzed the effectiveness of DRAM row hammer mitigation that's employed in DDR4 chips against pot hammer. And then we try and learn another method to adapt row hammer mitigations to account for pot hammer. And we select PRAG, per row activation counting, the latest solution industry solution to row hammer. So for this one, it's called target row refresh. In DDR4, DRAM vendors equip their DRAM chips with a proprietary mitigation mechanism. And the key idea is that it will refreshes nearby rows upon a detected aggressor row. So for example, assume that the TRR-equipped chip detected row 2 as an aggressor. Whenever a memory controller sends a TRR-induced refresh, it will refresh the neighboring rows. In this case, it's row 1 and row 3. And here are the results. So the first result is that we have multiple access patterns spanning 1 to 10. And 1 to 10 means that number of aggressor rows that we use to trick the TRR. So this is without TRR. So this is what happens if you don't have any TRR for row hammer. And as you can see, we have more than 10,000 bit flips. And with TRR, there are still bit flips, but the effectiveness is reduced a lot. So we have, in the best case scenario, we have less than 60 bit flips. For COMRA, it's very similar. We have 10K bit flips. But again, with TRR, we still have bit flips a bit higher than 1.1 times higher than row hammer, but still the effectiveness is reduced. But once we go to CYMRA, since with 2 activation, we activate up to 32 rows, 16 to 32 rows. So even in the baseline, the bit flips are like 10, 20 times higher than row hammer. And with TRR, still, it's very effective. We still see some reduction, but the bit flips that we observe is more than 180,000. So CYMRA concludes CYMRA induces more than 10,000 times more bit flips than row hammer on average in the presence of TRR. And the second case, since the TRR didn't work for us, we try to adapt row hammer mitigations to account for pot hammer, and we use PRAC for this one. So in the naive approach, what we did is that we reduced the row hammer threshold to CYMRA's lowest observed HC first. For example, we observed that the lowest HC first was 4,000 for row hammer, but for CYMRA it was 20. So we lowered the threshold to 20, and we just issue preventive actions in every 20 activations to a row. But other one is weighted counting. We increase the counters, the activation counters, based on the vulnerability caused by the operation, differently row hammer, COMRA, and CYMRA. And for this one, we use Remulator 2, and we evaluate a bunch of workloads, and here are the results. So from left to right, the intensity of pod operation increases. For example, 125 means, and the x-axis, DRAM performs processing using DRAM operations in every 125 nanoseconds. And the y-axis, we have normalized weighted speed up, normalized no row hammer mitigation. So if you naively reduce the row hammer threshold, you get a lot of performance penalty. However, with the weighted counting, a bit more optimized version, it greatly outperforms the naive until 2 microseconds. And once you go to the right, it incurs a lot of performance overheads. Essentially, it's the same as the naive version because we are almost just performing CYMRA operation. On average, it induces a performance overhead of more than 48%. And there are a lot more things in the paper. I just show you 2 results, but I think in the paper we have 25, 27 figures. So you can check that. A lot of sweeping, a lot of analysis. And we also check the combined read disturbance effects of row hammer with pod. So what we do is that what if we do first row hammer a bit, and then CYMRA, and then COMRA? And we observe that it's also effective compared to only row hammer induced row hammer access pattern. And we have more details and analysis on mitigating on pod hammer. We discuss how can we modify DRAM chips to help mitigating pod hammer, more details on PRAC adaptation, and challenges on this, such as the area we need to maybe find a way of area efficient solution or performance efficient solution, and so on. So the paper is available in archive and its extended version. And this concludes my part. And so to summarize, we extensively studied the interaction between read disturbance and multiple row activation-based processing using DRAM operations. We characterized many DDR4 chips, and we observed that pod hammer significantly exacerbates the read disturbance vulnerability and bypasses in DRAM row hammer mitigation and still effective on inducing bit flips compared to row hammer. And we adapt Prague for pot hammer, and it still incurs more than 48% performance penalty. And we hope that our findings guide system level and architecture solutions to enable with disturbance resilient future pot systems. Thank you for your attention. I'm happy to answer your questions. It was a bit rushed, but yeah. Yes, please.
I'm very interested in the processing DRAM part, which is very delightful. I have a quick question about like how much you can calculate. For example, we all know that DRAM activation takes around 10 nanoseconds to 15 nanoseconds. So but SRAM usually takes less than 1 nanosecond. So when you try to actually do some high performance computing, what would be the maximum talks in like processing DRAM?
I think that so as Onur discussed in SimDRAM and MIMDRAM show that a lot of performance, let's say, gains. So the good thing about DRAM is that you have one row is consists of 64,000 bits, and you have tons of rows and tons of subarrays that you can operate at the same time, and tons of banks that you can actually again operate at the same time. So I think once you do the, let's say, even in the naive performance gains like the teraflops or petaflops, or so the throughput is very high if you do the, let's say, the operation that is suitable for processing using DRAM. For SRAM, maybe the latency, the first latency is lower. Here is higher definitely because we need to like activate a huge row and huge arrays. But I think for the throughput case, since we have the huge parallelism, I think in throughput case, we have a lot of throughput in DRAM.
So speaking of the MIM DRAM as a case, so you suggest to like operate all the different banks with different instructions at the same time to the maximum the number of operations?
Yes, I think in MIMDRAM paper, there's actually even a study that we operate different subarrays at the same time, even in the same bank. So you can actually parallelize number of subarrays times number of banks you have, number of ranks, it goes to that part, yeah. Thank you.
Thank you for the talk. I have three questions. I'm wondering, is there any attack of DRAM power clusters, such as overactivation window, multiple simultaneous activations, reverse many activations in DRAM chips?
Yeah, it's a great question. So we actually, in the second paper, we analyzed that the power consumption. So as you said, instead of like activating a single row in a subarray, you activate 32 rows. So there should be some penalty of power, right? So we did we measured the power using like high frequency oscilloscope, and we observed that compared to normal activation, it's higher a bit. But when you compare with the refresh, which is a power hungry operation that's parallelized across banks and everything, it's lower, 20% lower. So it's still in the DRAM's power budget. And interestingly, we observed that if you keep it in the same subarray, the number of activations doesn't add up that much. So for example, activating one row is 40 watts, activating two rows is 42, but 32 is 48, for example, because we hypothesize that because the power hungry way is like sensing the subarray sense amplifier part more than the other parts of the subarray. I guess that's it. So yeah. We can move to the second.
but I don't know what I share. Pardon, it's fine. I'm fine either way, so it doesn't matter.
So the next talk is from Professor Sadrosadati from University of Memory-Centric. So the talk is Mastodon, enabling early-stage cross-stack simulation for processing using memory systems. So Sadrosadati is an assistant professor in computing and data science at University of Memory-Centric, and where he leads the Arcana research group. His research interests include data-centric computer architectures and systems, new interfaces between system software and hardware architectures, and architectures for emerging platforms and application domains. He holds MS and PhD degrees from Cornell University and 2 bachelor's degrees from Binghamton University. Among his awards, he was named an Intel Rising Star, has been inducted into the Ismail HPCA Hall of Fame, and was a Wimmer faculty fellow while at Carnegie University.
All right, thanks, Ismail. Can everybody hear me okay? Great. So today I'm gonna spend a bit of time talking about this tool that in many ways my group built out of necessity. And, Ismail was talking about processing using DRAM, and there's been, in large part, thanks to the efforts that these guys have done, modeling frameworks for, DRAM-based PIM. We've been looking at trying to expand that to other types of non-volatile memory systems. And so Mastodon represents kind of our effort to make that work. And in many ways, this is a culmination of something like 6 years worth of effort that we put together on this. So to start, and again, this comes a little bit from my experience, so maybe take that with a little bit of a grain of salt. But if we want to look at how you can take a new non-volatile memory and try to make it work for PIM, right? There's actually a long, drawn-out, sequentialized process that comes into this. Okay? Device physicists, they work in their labs, they do nanofab, they make 100 devices, and maybe a few of them work because it's tough to get these things to work correctly in the lab like that. So what do? They find a couple of what we call hero devices, the ones that work fine, that hit all the objective targets they're looking for, and they say, great, we're going to publish a paper in IEDM about this, and it shows some nice functionality for this device with a lot of assumptions on what can actually happen. Now, an architect like me comes along and says, hey, I was not minding my own business. I went to an IEDM paper and saw this nice table that says, hey, this device can do X. And so I say, wait, that might work for PIM. I put it together and I come up with what ends up being a very fanciful hypothetical device, right? Because it assumes that this hero device, that I can make thousands, if not millions of them. Inevitably, this is where a number of people stop. But if you don't, you start realizing, oh, wait, there's real world problems trying to make this a reality and actually trying to fabricate this. And then years later, the architects and the device physicists and people across the stack, if you're lucky, start working with each other to actually iterate on problems that each side needs to solve. Okay? To me, this is a very, very drawn out process. And what we're ultimately trying to do is find ways where we can actually break this cycle so that we can actually look early on as device physicists are building these new types of memories and figure out, are they viable for PIM? If so, what are the types of architectures that they can sustain? How do we explore the architecture early on at the same time that the device physicists are working on things so that not only can we figure out the cool new thing to do, but we can go back to the physicists and tell them, hey, focus on this, not that. For example, focus on wear out, not voltages. There's these types of things that we don't know because we operate in our own bubble. And you might say, okay, Sagata, great. This is what SPICE is for. SPICE has existed for decades to do exactly this. But the problem is, while SPICE is really accurate, it is extremely slow. And this becomes problematic when you're thinking at the architecture level, when in reality, you want to be looking at, something on the scale of a chip. And if you do this with SPICE, it can take potentially months to simulate one instance of a design. And so if you want to try to do this architectural exploration, you could be talking about years upon years of simulation time to get this to work. Okay? It might work at the scale of a single memory array, but it really doesn't scale up to the types of problems we're interested in solving with PIM. And so what we're trying to do is come up with a new design flow for, in my talk, I'm going to focus on digital PIM, Boolean PIM, bitwise PIM, kind of like what you saw with Ismail's talk, these idea of Boolean complete operations that you can do in memory. Okay? And what we want to do is figure out how can we model this in a way that actually is tractable to do design space exploration. And so it was from that impetus that we created this tool, which we've now open sourced, called Mastodon. Mastodon does what many memory simulators hope to do, right? It gives you performance numbers, it gives you energy numbers. With a little bit of finagling, you even get some estimate of the area of the architecture to understand not just the arrays themselves, but also what are the costs of peripheral circuits, front-end controllers that we often tend to overlook when we're designing these PIM architectures. But we had a few goals here, and we've been working, as I mentioned, for several years to try to make this be flexible to the different needs that our research group has. And so some of this includes being able to model potentially any type of memory device, right? For example, if there's a new type of device that we haven't seen for long, I don't want to have to wait for years for someone to hard code that into a simulator. Okay? And so to that extent, we actually designed Mastodon to be able to directly take in the device and circuit models that device physicists and circuit engineers have been working with, these Verilog A models that are sort of their lingua franca for defining these models. We simultaneously want to be able to explore many different architectural configurations, right? Because as you've probably seen, there are many different papers on PIM these days, each of which looks different at the data path level. And while we're going to focus on PIM today, we can also see the potential for this for conventional memory simulations as well, because not every emerging technology is going to end up being a good fit for processing, but it can still be useful for I/O. And a lot of the tools that we're developing here can be reused to just gauge its fit for simple I/O. And so I want to start by giving you sort of a high-level overview of the features that we have and why we've chosen some of these parameters in the simulator to model. The first is that on the architecture and microarchitecture level, our goal is really to be able to take higher level code, things that you'd actually be able to write, in theory in LLM or genome sequencing, and be able to actually run that on models of these devices. And so we can actually take that, map it down to the architecture and microarchitecture, and then able to be able to translate that into operations that happen at a device level. This includes a number of things that have honestly been a pet peeve of mine that I feel like we've often overlooked as we've been focusing on improving data paths, which is, where do you keep binaries for this thing? How do you read instructions to send to a PIM architecture? How do you actually manage the state of the data path to execute instructions in real time? These are things that a real chip has to have. And we often focus so much on getting functionality to work that these end up being afterthoughts, or we say, well, it'll be someone else's problem in a future paper that unfortunately never comes. Okay? We look at a very hierarchical simulator to try to model different types of architectures, and I'll show you that in a few minutes. But we allow this to be able to work with pretty much any PIM architecture that can look like a SIMD interface. Okay, so one of the things you see often is that vector instructions interfaces are kind of the popular way to manage these types of architectures. We could potentially do other things, but we haven't supported that yet in here. Okay? We also want to be able to support the fact that there could be many different memories within a single node, right? There could be many different arrays. There could be many different tiles of mats of memory in those arrays. There's a whole wide range of organizations here that we, again, aim to support, because the goal is to let us do comparative studies and to be able to explore what makes sense here. And we also want to have support for flexible networks that connect these nodes with each other. So a node you can think of it as sort of an independent entity that's capable of controlling execution for some set of the memories. It's almost never going to be the entire chip. And so you're going to have many of these nodes coordinating with each other, sometimes communicating data operands, much like you would see in a multi-core, many-core system. And so we've actually been able to provide support to model an on-chip network and all of the overheads of that. And we'll also explore different topologies of these networks. At the circuits and device level, we actually provide two sets of models. The first are what we call these fast fixed device models, which more or less take that IEDM papers table. You can put in whatever parameters you want, and it'll be able to give you a reasonably fast execution of a simulation that can, maybe have some ideal assumptions that are being made for the models, but can get you a pretty quick answer as to how good or bad this architecture is. But for the cases that you need something deeper, we actually do low-level transient modeling of devices. Like I said, taking in those Verilog A models and actually capturing the properties of the devices as they're operating and constructed. Today, we have support for a number of different memories. Not all of them are supported in the detailed Verilog A model yet. But we do have a number that are, and we also provide a parameterized device model that you can try to configure if you don't have a specific Verilog A model already implemented to roughly approximate any type of two-terminal memory device at the moment. And as I mentioned, we also look at multiple levels of interconnect within a node, within the arrays, and look at the structure of interconnects and understanding how their properties at a circuit level, things like parasitics and capacitances, come into play when you construct these architectures. And so to make all of this happen, we have this sort of top to bottom flow where we start by having programmers write these files in the format that we call ERC. And it goes through this proto-compiler that we've built. If you've ever looked at other works, for example, we have a work that Onur talked about earlier called MIM-DRAM. That tries to take LLVM and allow you to generate code without really just writing anything other than C++. We opted to give a little more control here. It's entirely feasible to take an LLVM flow and add it on top of this. But as you're doing research on architectures, you sometimes want to know where you're placing the data and have much more granular control. EasyPIM in the ERC format lets you do that without forcing you to struggle with writing individual micro-ops and assembly instructions like we've had to do in the past. And I'll show you some examples of that in a few minutes. EasyPIM can take what we think is a relatively easy to write snippet of code and expand that into something that can actually model an entire chip's worth of execution. And then that binary that gets generated can be sent into our Mastodon simulation at runtime, where we have multiple nodes, where each node consists of multiple lanes of execution. And each lane is backed by a vector register file. And if you remember, we have those two circuit models. The vector register file's underlying implementation can be either one of those. You can configure at runtime which of those two modes you prefer to see. Are you willing to take a little bit more time to get precise behavior, or do you just want to get some quick numbers off the bat? And when you look at this sort of node lane vector register file hierarchy, we chose this intentionally because we saw that across, we sort of did a cross work study to sort of look for these common attributes that we see across PIM architectures. And we found that it actually maps pretty well to a wide range of different behaviors that we see. For example, a few years ago, we wrote a paper on optimizing ReRAM-based bitwise PIM called Racer. It has a very hierarchical design that allows you to amortize circuitry, that allows you to create these independent clusters that we call them and scale them up and down easily for the various needs that you have. In this model, we actually map a node not just to one cluster, but to multiple clusters to capture local versus global communication. We assign a cluster to a lane because that's the independent level of control for issuing a series of instructions. And then we have register files corresponding to one group of data that would interact with each other. Looking at a different architecture, if we go to MIM-DRAM, it looks very different as a microarchitecture because it works with DRAM instead of resistive RAM. It works at the level of DRAM mats. But you can take that same idea of nodes, which we map to an entire chip, lanes which map to the processing engines, the individual processing engines that can run different programs in MIMD-RAM. And then we assign the register file abstraction to the mats. And so we find is these different abstractions actually work really well to be able to capture all of the essential behaviors that these architectures would have without requiring the programmer to have to rewrite large portions of the simulator. So, as I promised, that all sounds great at a high level, hopefully, but it must be a nightmare to have to write for this. And so it was, and one of my students actually decided, okay, this is painful. Let me come up with a way to make writing assembly for this, especially at scale, a lot easier. And so this led us to develop this, what I've been calling sometimes a proto-compiler or an advanced assembler, which we call EasyPIM. And the idea is that we can generate some sort of ISA for these architectures. They can either be a shared ISA, which I'll actually talk about on tomorrow afternoon, or you can use a custom ISA for whatever this architecture has. And you want to be able to take a wide range of data parallel programs, some that are simple to express, some that are pretty complex with control flow decisions and with a lot of different parallel tasks being executed. And what we try to do is combine that ISA with some meta instructions for control and use our proto-compiler to map those applications in a way that can actually run on the node, lane, vector, register hierarchy. And in order to do this from the perspective of the compiler, we essentially treat the vector register on back as just a generic memory tile. Now, this doesn't actually map to physical memory tiles. It's simply just the lowest that the compiler needs to know about, because we've abstracted away the actual underlying details in the way we set the simulator. And so we use the vector register file because, again, as I mentioned, this seems to be the common interface that we've observed in the majority of these Boolean PIM architectures these days. Many of them perform operations on entire columns of data at once to amortize the high latencies of doing bit serial computation. So we support being able to generate code that can actually operate on these column-based vectors at a given time. Okay. And we support a sort of RISC, like MIPS-like format that essentially has a bunch of operations, and they specify which vector registers, which columns you want to take as inputs, where you want to put your outputs. We can support both destructive and non-destructive versions of these depending on the type of devices and microarchitectures people have built. And because we want to be able to express parallelism in a reasonably efficient way, we actually look at adding in control meta instructions that can choose which lanes and which register files within those lanes you can run this kernel, if you will, this microkernel on. And so if, for example, we have this memory tile, which represents lane 0, register file 0, we can add a compute block that says, compute the following code within this defined microkernel on this lane and this register. And you can have however many SIMD instructions you want to execute on there. Of course, the specific instructions depend on what ISA you're using in the simulator. We've provided a baseline starting point for that if you want to just use that. One of the nice things here is that you can actually use this to support parallel SIMD execution across different lanes as well. So if you have a kernel that can actually execute in parallel across many different tiles at once, you can simply just add those to your definition of your compute block. Now, one thing that's intentional here is that we're not saying this has to be parallelized, because that would, again, force programmers to have to think about low-level hardware decisions that we don't necessarily want them to. So all this is saying is that this kernel has the potential to be parallelized, that it would not create any problems for correctness if you were to go ahead and parallelize this. Okay? And then it'll be up to whatever microarchitectural logic you choose to implement or ignore about how you actually go about parallelizing that execution. And that can take into account hardware constraints, that can take into account thermal issues, a number of things that can come into play as you're trying to model these effects at the scale of parallelism. We can also support things like data movement between kernels to make that communication, actually take up time, energy, make sure that it's being accounted for correctly, because often data operands don't fit within a single tile. And in the interest of time, I'm going to skip through this example, but if you're interested, I'm assuming these slides are going to be available afterward on the workshop website, and you can take a look at how we actually map a simple example of matrix multiply to make this work. Okay. Now, all that gets through what I'd argue is basic functionality. But with what I presented, that just sounds like a nightmare to have to scale up to write a program for an entire chip. So what we've done, and there are going to be people like us who will look at this and probably still think of this as a simple interface, given that there's work on real compilers that can be done here. But to be able to control this in a way that to us seems manageable when you're doing this hardware exploration, we've come up with a number of simplifications, if you will, on the easy PIM side. So for example, we've provided support for macro variables so that you can increase or decrease problem sizes. You can change the which rows and which columns you're using in tiles, so that your code doesn't have to be completely programmed to a specific microarchitecture and a specific variant of specifications. And EasyPIM, just like any other assembler, will automatically handle micro substitution for you on that side. We've added support for expressing for loops in this assembly that EasyPIM will look at the target microarchitecture and expand to generate the full code so that you as a programmer don't have to write each individual iteration of a loop, which is unfortunately a lot of the state of the art for these simulators today. Okay. And so this, again, piggybacks off of our macro type of support, and you can have loops with, like a for loop with an iterator defined, and you can use the iterator to substitute for column and row variables. Okay. And we can go one step further with this, and we can actually generate function macros. And so you can take kernels, you can use them as sort of semi-portable functions, and then you can express these in EasyPIM so that you don't even have to worry about having to rewrite this code or copy it back and forth. Okay. Now, again, this isn't what a real compiler would do, because a real compiler would do this in a way that reduces the binary footprint, right? It would do this in a way that allows you to reuse different segments of the binary. Our goal here is not to reduce binary size. Our goal is to make it easier to write a program to test your architecture to begin with. When EasyPIM works, it's still going to generate the bloated binary for you. You just didn't have to write that bloated binary by hand. But if you look at a function like what we have here for doing a general matrix multiply, you can simply just have this macro with the starting address, and then you can keep calling this over and over again with different offsets, and it'll automatically do the correct shifting, the adjustment for all the offsets that you'd have for your code. And so now we've seen a number of different ways which this can reduce effort. These are sort of simple numbers here that you can see where ERC works. We have seen cases where we've been able to pull down the size of binaries by 90 to 95%. So that you're only writing dozens to maybe hundreds of lines of code, and that's going to expand to binaries that are tens to hundreds of thousands of lines. So the goal here is to make it a lot easier to be able to do that type of simulation. At the microarchitecture level, we wanted to be able to, as I mentioned, express many different types of data path designs. And so our code base is intentionally designed to mirror that stack photo that I showed you at the beginning. We have our RC files that come in after being assembled by EasyPIM. We have a top level that handles binary storage, binary distribution, all of our control of meta instructions for turning on lanes and managing parallel execution. We have a middle end of our simulator that actually models the different microarchitectural designs that you would want to do. Here we're using Racer as an example, just in this diagram. We've provided Racer and MIMD-RAM as a starting point. You can take this and really be able to map any kind of middle stage that you would want to represent any kind of architecture that can use a vector register to do bitwise PIM. And then on the bottom part of our hierarchy is effectively everything that is device specific. So how do you take an instruction like an add and expand it into the micro operations that a ReRAM device or a PCM device or a DRAM device can do? How do you model transients for this type of behavior? How do you capture energy consumption? How do you deal with thermal hotspots? All of that is being handled in this lower level that's fully dedicated to device specific, so that everything else on top doesn't have to worry about the device behavior at all. And so we've designed this to try to be a fairly modular approach to constructing different types of architectures. Again, in the interest of time, I'm not going to go into too much detail here. We have a tutorial that we've posted online that goes into this in much more depth. But one of the things you can do is you can load in an application's data to pre-populate the values within the memory. This serves two purposes. One is you can see what happens with different input variables if you want to start at different places, but it also allows you to be able to checkpoint execution so that you don't have to assimilate entire applications if you want to just model certain parts. So you can save the snapshot of all of the data in a file, you can load it up, and you can pick up where you left off. And one of the things that we do, so I skipped through this in the interest of time, but we basically have your typical simulation loop that can iterate through all of the modules in the simulator and make sure that all of the events are being tracked, cycle to cycle. But then one of the big things that we've introduced here is this idea of a control path and actually monitoring execution state and dispatching binaries. And so in that top stage that we have our simulator, we actually have a binary that's being stored, and that gets fetched in based on what program counter value you're on now. And we can pass it through a precoder, which determines if this is a meta instruction or instruction that needs to be passed down to the data path. Now, let's say we have a small binary here. We have a meta instruction that comes through. That meta instruction is going to be handled by our top level. And for example, here, what we're doing is we're turning on certain lanes for execution. So we have a lane activation board that's monitoring which parallel units get to execute at any given time. You can issue however many of those are in your kernel. And then when execution starts, we're going to take those compute instructions and pass them down to the middle end of our architecture. And now that's going to pass through Racer, in this example, Racer, but the decoder of the data path. That data path decoder is going to go to the bottom part of the simulator and retrieve what we call a recipe, essentially the sequence of micro operations that will enable this add instruction for the microarchitecture and device that's currently being modeled. And so the nice thing about this is I can keep the Racer microarchitecture the same, and I can model it for ReRAM. I can model it for SRAM. I can model it for STT-MRAM. All I need to do is change the bottom level configuration. Going back down to the bottom level configuration, as I mentioned, you have a choice on whether or not you want to model the fast version of the devices that can basically overlook most of the lower level transients and parasitics, or we can go to the actual detailed behavior of what's going on, starting to sort of take a page out of what SPICE is doing and emulating that with reasonable accuracy. And so in order to do that, we've actually built a multi-stage model for the devices that starts by, if you have a Verilog A model, it'll actually parse that Verilog A. We can do this for pretty much any arbitrary two-terminal device at the moment. We'll convert it into C++ code to make sure that the simulator runs at high performance. We'll use that to then build up a model of the cell that includes the device itself as an RC model. It'll include the wires within the device to include their parasitics. Then what we'll do is we will, based on what you, using the simulator, have told us, stamp out those devices in whatever array topology you want. So you can have large arrays, you can have small arrays, rectangular ones. If you want, you can even try to make a trapezoidal array if you really care to, which power to you. But you get to choose how the model gets set up. And then what we're going to do is we're going to model transient behavior across that entire tile. And then finally, we're going to take those results and we're going to feed them back to the execution stage. So this transient behavior will be modeled every cycle. This is cycle accurate. So when you issue a micro-op, that micro-op will actually run through these transient and parasitic calculations. And the goal here is for us to be able to provide device level and circuit accurate analysis of what's going on here. Okay? We also want to be able to evaluate reliability. How likely is this operation to actually succeed? How likely is this program to actually get the results you want based on the real world behaviors of this device? One of the big things, as I mentioned at the beginning, is that we want to be able to make it possible to cooperate with the devices world and with the circuits world so that we're not just operating in isolation. To me, this is really important as we're doing more and more cross-stack modeling. And so we have 3 optimizations here that allow us to shortcut a lot of the inefficiencies of SPICE for this particular setup. Because SPICE is really designed to be an arbitrary equation solver. We don't need it to be fully arbitrary. You would assume that this device has at least been tested in a lab, some behavior of its function that the device physicists come up with. And so we can rely on a closed form version of transient modeling that makes us much more scalable to model. We actually use memoization tables so that we don't have to keep replaying similar behaviors across an entire chip of maybe 1 billion different cells. We actually make that variation aware so that we can actually have distribution models of the variability across each circuit. And as a lot of contemporary EDA tools have done, we actually look at the response curve and we use that to figure out how we can implement dynamic time stepping so that you're not wasting a lot of time modeling small time steps when the behavior is pretty known over, let's say, a straight slope of a curve. Putting all this together, we've actually compared this with Cadence Spectre X, which is sort of a state-of-the-art industry class SPICE tool. What we found is that we can keep our accuracies, and not just bit accuracies, but accuracies of the end voltage and resistance state of each device to within 2% of what SPICE can do. And we can do that with a speed up of anywhere between 31 to 600x, depending on what granularity of detail you're looking for. And we can also cut down the memory usage by hundreds to thousands of x to try to keep this in a much more tractable form. And this is where we get the wins of being able to assimilate these devices in hours and days as opposed to weeks to months that you would normally need at this chip scale. Wrapping up, there's one last thing I want to talk about, which is how do you build this into an entire system? Okay. Now, again, we often work in isolation. We say that a PIM device, we're just going to model the data path in the arrays, and that's already a big achievement. But in the real world, as Onur mentioned in his introduction, we are going to be an accelerator potentially that's interacting with other accelerators, with CPUs, with GPUs, with many heterogeneous resources in the computer. In reality, it would be nice to actually be able to see how that system interacts as opposed to just looking at the data path in isolation. And so what we've done is we've actually leveraged SST, the Structural Simulation Toolkit, which is a flexible modular simulator that has many different components built into it. And we've actually added Mastodon in as one of those components. And so we can create a multi-node version of Mastodon, which leverages SST's built-in Merlin support for on-chip networks, which has detailed router models, detailed internet models. And again, you can have that map into any topology and any flow control and routing policies that you want it to. We can instantiate however many nodes we want as direct top-level modules in SST so that they can talk with each other and that they can talk with CPUs and GPUs. One thing that we're in the process of doing, and we've done it for a slightly different variant of this, is that we can actually have this take advantage of the RISC-V ROXY interface. So you can actually compile code to both a CPU and offload to these PIM devices to see how they work together on different phases of a program. And we've leveraged MPI as our communication protocol for now, mainly because that's what SST does. There are certainly opportunities to optimize this that we hope to come back to in the future, but at least you can actually model what's happening when you send data packets out. You can actually see, configure the packets themselves and see what's happening as you route them from one node to another. So with that, as I mentioned, this code is available today. We do have version 2, which is actually hopefully coming out in the next couple of days. But this version, everything I've described here, except for the circuit model, is already available on GitHub under the MIT license. As I mentioned, we did a tutorial on this a year ago, so there's much more detailed information there. If you want to learn more, we have a bunch of Jupyter notebooks that can walk you through various demos, so you can get the hang of things a bit. And like I said, this has been a great playground for us to be able to develop a lot of advanced ideas. One of the things that I'll be actually talking about tomorrow at HPCA at 3:50 is an abstraction for PIM, a front end that can allow you to build a software stack that has no care about the microarchitecture and the devices. And we've been able to show how we can actually build that using Mastodon as our starting point and still be able to understand the low-level device and circuit implications that this has across the many different architectures that something like the MPU is compatible with. Of course, I'm just the figurehead for all this. The bulk of the work that I've talked about is really a result of 4 of my students, none of who unfortunately could be here today, so I just want to acknowledge them. There are many other students in my group who've worked on this as well, but the bulk of the work that you've seen is from Min, Arjun, Yicho, and Ryan. And I also want to thank our funding sources for this, because as many of you know, simulator work is not easy to get done, and a lot of people don't care for it. So we are appreciative of the fact that they've let us get this far with stuff that people are often allergic to. So just to summarize, as I mentioned, we've built this cross-stack simulator that tries to model top to bottom, the different parts of the hardware stack that we'd be concerned about as we're trying to design a chip and explore that design through early stage iteration. So with that, I'll stop now and I'll be happy to take any questions. You can use that QR code to download the code if you want, and thank you, everybody.
Thank you. I'm glad to see you have a universal PIM simulator. Great and very helpful. I have a few questions here.
Sure.
So first is, why are we using variable A as a model circuit language, also model compared to other PIM-specific simulators like AI hardware kit and PIM? Are these models from ideal or real data?
So let me start with the first thing. We use Verilog A because that seems to be what the bulk of device physicists end up using, right? So this allows us not to have to make them convert something as they're iterating, because ideally, if we do have to convert to, we want to do it once. But if they're in the middle of developing their device, they're iterating on this Verilog model over and over across a series of months, if not years. And this allows us to be able to take that work as it's in progress and input it directly. You don't have to do that. For example, we also have support to take in C++ models directly of any, that they can express a certain interface that we have here. And in fact, we've been working with Shalu Rakeja, who is an EC professor at Illinois, whose specialty is these device models, to be able to look at other ways besides Verilog A that we can express this. How this compares against, let's say, a hardware kit or cross-sim. In fact, I completely left it out in the interest of this, but we've actually been working with the Sandia folks who've been building cross-sim. And you can see this in the tutorial. We have actually integrated cross-sim into this flow as well. So SST, Mastodon, and cross-sim can all work together. Cross-sim is really great at the analog side of things and capturing analog non-idealities. It doesn't capture timing. It only has a little bit of energy information in it, and it doesn't, unfortunately, work for the Boolean bitwise PIM that we're targeting here. So that's why we end up sort of combining the two together. And in fact, with Mastodon, we were able to take cross-sim and actually add the timing information and actually have real-time feedback on data errors and how that's influencing the program in ways that Mastodon sort of does that cross-sim does a quick and dirty approach to that. AR hardware kit, is basically custom coded to have some sort of a resistive model, right? You can parameterize a whole bunch of things. And you can, again, take like an IDM paper like table and plug that in and play with around with a whole bunch of parameters. But that doesn't really work well for capturing real world transient behavior, right? If you look at a hardware kit underneath, it's essentially just replaying that table a bunch of times, which is good if you already know that your device works and you know how the device scales, which folks at IBM can do because they're building entire chips. you don't know that if you have a device that you're building in the lab at the moment, right? And so this allows us to be more cautious about the things we're modeling without assuming ideal behaviors. The last thing about real world data. We haven't provided any real world data on this. We have been using measurements from other groups that we've been putting in here. We've tried to, are working to try to get some data from that with fabs such as New York Creates, where they've been building chip scale real models. And that would simply just be a matter of plugging into the models with the variability that we already have. We can already take that variability and express that variation across a wide range of real world devices. So we're ready to go with that. We don't have that data yet to be able to plug in at the moment.
Right. Also, I checked you have applied some commercial tools like SpectraX. You have also the question I'm not quite clear here is how's the simulation level in terms of circuit level? Is this cycle accurate? Transient? Do you have RTL support as well?
It is cycle level accurate for transients, right? So those error rates that we showed were actually every cycle seeing what the difference is between what we're reporting and what SPICE is reporting. So that's not an end result, that's actually a per cycle result. And that per cycle result is staying within that, I think the worst we've ever seen is a 5% variation, and our average is under that 2% mark. We don't support RTL at the moment because that would be a whole separate beast in itself. So everything here is still C++ based, kind of like a simulator like Gem5 would be. But we're certainly open to looking at ways to add that in if there's enough interest. Mm-hmm.
There's no problem. Yeah, thanks for this nice talk. It's great that you're working on this sort of infrastructure. Mm-hmm. This is definitely good to have that cross layer. I agree with all the goals.
Yeah.
Not easy to accomplish, but
thanks.
Good to try. Did you publish this somewhere?
Not yet.
Okay.
So we have pieces of it that we've been working toward submission. But at the moment, we wanted to release it early because we wanted to get people to start using it and get feedback from it as well, so we could improve on it. But we have a couple of publications that we hope will come out of this in the next, depending on how the reviewers are kind or unkind to us, the next N years.
I think reviewers should be encouraging of this sort of infrastructure work because this should not be work that doesn't get appreciated.
Thanks. But
this is hard to do work. It's not easy.
Yeah, I know you know this stuff, but yeah, we'll see if they take to it as kindly.
You can always send an abstract to our ICS workshop if you're interested.
Sure. Mm-hmm.
That doesn't preclude publication of longer minutes.
That's right. Mm-hmm.
I have one question related to the modeling. You have some abstractions like the register file, etc. Does that accurately model every architecture that is out there, like MIM-DRAM? Or can you break those abstractions internally easily?
So
I don't know if that register file construct is
right.
a real construct there, or is it breakable?
It is breakable. In fact, as you know, like MIM-DRAM doesn't technically have this same idea, right? There are corollaries to that work for MIM-DRAM, and that's actually how we were able to make that modeling happen. So the answer is it's all breakable, right? We just provide that as sort of the framework in which, as long as you break it in a way that still works with the interfaces between the middle layer and the bottom layer, let's say, you can get that to work however you need it to. So it's a starting point for people who want to work on these things.
So, for example, if you want to model without that register file, do you have mechanism to do that right now, or people need to modify the simulator?
It depends. So for something like MIM-DRAM, we've provided that because we, of course, had to break it already. We haven't provided something that's more flexible beyond that at the moment, so it's kind of up to people to implement. We're certainly, one of the constraints for that is that, well, A, the students built this when they needed it. They didn't need something like that yet. And B, it's one of those things that we're not sure what the better step for that is. So we're always open to ideas if you or anybody else has them to see how we could expand it out.
Sounds good. Thanks.
Thanks.
Thank you so much. So, very nice work. I just want to understand how does the different stacks interact with each other. So the results that you showed is the comparison to this spectrum, right? So
yes,
which is extremely low level.
Mhm.
But then if you kind of make this up to the architecture level,
right.
how does this, how detailed is the architecture level solution then? Is that instruction accurate, cycle accurate, or?
It is cycle accurate. So we are iterating every cycle, and we are actually, we're not doing it in an event-driven way, so there's some inefficiency in the way the code is currently written for that, but we are essentially at each module, at the top level, all the modules in the top level, all the modules in the middle level of the data path, and all the modules in the low level, we're doing this cycle by cycle to see how the interactions work. Now, a cycle is a little bit of a weird thing here, right? Because we have the sort of the digital clock cycle that all of that gets synchronized by. And then at the low level for the transients, we have a cycle that is made up of multiple time steps, right? And this is sort of akin to how like an RTL simulation would work in like, like let's say model sim, right? Where you have many, many granular steps, you're figuring out what the end result would be, and that end result is what gets reported back up to the middle and top layers. So within a cycle, the only things that are operating at a finer granularity are in that bottom layer, and that's because the transients are being done at probably, I mean, it's variable because of the dynamic time stepping, but on the order of 100 to 1/100th to 1/10,000th or 100,000th of that cycle time.
Okay, I do have a few of the questions, but I guess I'll keep checking if you do that much.
Sure. Thanks, Asif.
One question.
Sorry. Yeah, you can.
What? Like 20 minutes? Right. You can shorten one, it might be efficient. Right.
Okay, in the next one is a Geraldo from Sadrosadati, fault injection framework or processing using memory architectures. So Dr. Joe received bachelor degree in computer engineering from the Federal University of Santa Catarina in 2017, followed by master's degrees in 2019 and a PhD in computer science in Federal University of Rio Grande do Sul in 2025. He is currently a postdoctoral researcher in the chair of compiler construction, research and development code optimizations for emerging AI systems as part of SCA in Dresden Leipzig Center. His main research interests include processing in memory architecture, system design, hardware, software code design, design automation tools, compilers, reliability evaluation, and fault tolerance methods. On the application side, he is particularly interested in efficient methods for machine learning algorithms through memory-centric optimizations that are compiler-driven and enabled by domain-specific tools for energy efficiency.
Thanks for the intro. So hello, everyone. I'm going to be presenting fault injection framework for processing using memory architectures. I guess this work connects well and it has some synergy with what Ismail presented earlier and what Sagata also presented. And my premise here is that even if we get to the point that the memory array is going to be reliable enough, still we're going to have some unreliability playing around, and we have to deal that when running our applications. So instead of going to purely architecture simulation, what I'm going to present here is a fault injector that tries to be faster or faster enough so you can have like thousands of runs for getting a good estimate of how well your application is going to perform in terms of accuracy or result output quality, right? So I'm going to go through this agenda. I think I don't need to explain right now for the sake of time. Some overview of processing user memory and reliability, and then present existing fault injection tools and our work in progress. Right, so for more than a decade, people have been interested in how to resolve this computing energy problem, right? And has been a major challenge in this period. So during this time, we have the processors have become much more efficient than the memory, and this gap has motivated the processing in memory research in general, right? So this has inspired many researchers to work across many layers of the computer stack, from algorithms to architecture, circuit design, and so on, and material design. So because of this, we have seen many proposals for memory systems from both academia and industry. And these include near memory and in-memory processing, as presented previously by previous talks. And in addition to, and they can be done using mature technologies such as SRAM, DRAM, and flash, or by emerging memory technologies such as RAM, STT, MRAM, and so on, which are more exotic devices, I would say. Right, so we can group processing using memory architectures into two main categories. First, charge-based ones, such as DRAM and SRAM. And in this, we have a similar basic principle. So two or more memory cells, we share charge with a bit line, and the sense amplification fundamentally is going to decide whether the output is 0 or 1. In the second category, the resistance-based memories can be further divided into non-stateful and stateful logic. In stateful logic, we rely on the sum of currents through a resistive device, and the sense amplifier is going to compare the readout current to a reference current to produce an output. And in non-stateful logic, such as magic and imply families, we are going to specify voltages to the device representing the inputs, and as a result, the voltage drop across the output device, we are going to produce the result of the computation without the need of a supporting sense amplifier. Right, so from the programmability perspective, we can identify two common processing memory primitives here. The first one is simultaneous multiple row activation, as presented before, and the second one, consecutive multiple row activation. Right, so the simultaneous SIMRAM works well for represent how DRAM-based PIM works, and also how memory-based or MTJ-based also work. And the second primitive here is more for copy and not operations. My opinion, it is more applicable here only to the DRAM-based. Right? So, and based on those primitives, one can implement arithmetic and more complex operations using majority synthesis in DRAM, for instance. So with this circuit representation, the full adder, we can generate microcode that corresponds to memory commands, and we loop over it many times as many bits we have to get a computation, for instance, of a vector addition using integers. Right? So, and that's basically how vector addition in this example works in SIMDRAM, a paper that Professor Onur mentioned earlier. Right, so now we come to the reliability issues in memory. First of all memories, regardless of if you're using as processing memory as substrate, they are going to have reliability issues, and they are going to become more evident with the scaling. So in chart-based memories, most of the problems come from process variation. These include variations in cell size, bit line impedance, and sense amplifier voltage threshold, for instance. We're also gonna find manufacturing defects and design-induced variations. For instance, a varying distance between cells as a simplifier. In the resistance-based ones, in the resistance-based PUD designs, we gonna observe not only the same from the previous ones, but also some intrinsic device level variations, which makes things even more complicated or like less reliable. So in many metal oxide memories, for instance, we are going to find cycle-to-cycle variation, device-to-device, stuck-at faults, limited endurance, and read noise and retention drift. So how the reliability actually affect PUD? Well, you're going to expect that the output is incorrect, right? So there's a bit flip happening in the memory. So first of all, why they happen? So we can say that because we are operating out of the specification, in case of, for instance, Ismail work, we are intentionally violating the standard DRAM operations. And there's no guarantee that the operations are going to behave exactly as expected. And in the end, it is an analog operation going on there. Second, when we perform multiple activation, we also notice that some columns are more prone to errors than the others. And third, there are some fault modes that are data dependent. That means that the input pattern that is going over in computation might have a different effect on the success rate, right? And finally, as Mo presented before, beyond a single operation, when you have multiple operations, you can introduce additional disturbances, which is going to worsen existing problems such as row hammer in this case. Yeah. So in resistance-based memories, the cells, the resistance of each cell doesn't have a single fixed value. Instead, it follows a statistical distribution. And when we use multiple row activation, for instance, in this example is an experimental device of a fabricated chip performing majority. The readout current also follows a distribution. However, with a certain probability, those distributions that should correspond to logic 0 and logic 1, they will overlap. And when the readout current falls in this overlap region, we cannot guarantee that the computation is correct. So that's where we're going to also see bit flips. So this, right. So even with this level of unreliability, in this case, for instance, as you can see in this plot, it can go, the error probability can go from 10 to the power of minus 13 to very severe as 10 to the power of minus 5. So under this level of unreliability, we have to pose a question, right? So can we actually use those devices? Can we actually use those substrates for anything? Like, and how will the application behave? It'll be acceptable for performance and output quality, right? So our focus in this work is basically evaluate if these error rates or operation fidelity, how they are going to translate into application correctness and quality of the result. So in the past, again, it's out of necessity, we were studying techniques to mitigate those reliability problems, and we realized that there was no good tool that was fast enough for processing thousands of runs and on data-intensive workloads. So there were a couple of prior papers where we were evaluating application level accuracy and quantifying them in task-specific metrics. For instance, in ML work, we were we wanted to know how top one accuracy was going to exchange. In scientific workloads, what the numerical error bounds that you can guarantee, right? So in image processing as well, and so on. For each type of application, we were analyzing how those fault probabilities were going to impact application accuracy. So in general, application level reliability assessment methods can be grouped into 3 categories, such as fault injection methods, analytical methods, hybrid methods. For the sake of time, I'm gonna speed up this. Here we are interested in fault simulation, because fault simulation is not really applicable here, and irradiation even harder, right? So what are the pros of fault simulation? We can get a low design time and fast execution with a high-level software implementation. For instance, people have done this before with ML frameworks and injecting faults in the framework. Second point, it requires no special facility. You can do with HPC or even with a server class setup that you have at your university. And you can rely on open source frameworks or extend it at least to meet your goal. The problem is that still there is a high time complexity to achieve a sufficient confidence level, and often high-level software implementations will lead to inaccurate results or not realistic results. So if you are going to do a software-based fault injection, how do we start? We start with obtaining the fault model, which typically comes from SPI simulation or experimental characterization. And then we go to an injection model where we want to, for instance, calculate the fault probabilities of arithmetic operations or fault probabilities in arithmetic operations out of the gate primitive that you can obtain in characterization or SPI simulation. Third, then we perform multiple runs of our application using Monte Carlo sampling. And based on this, we collect observations and perform some statistical analysis. At this point, an important question arises. It is, how do I instrument my code to simulate it, simulate PIM faults? Right, so Priya works in fault injection, very known in ML community and also in hardware security. You have at least those 3 ML-based application level fault injectors. So they all leverage Python frameworks for efficiency because they already have good kernels, gem kernels implemented, and programmability. You don't need to change your code for that. And they typically only model a single bit flip. So over thousands of runs, what they are doing is actually choosing a position to flip the bit and then see the effect of the output. And there were a few fault injection for processing memory, such as FLIN and XFault. The limitations of them is that they are framework specific and application specific. By framework specific, they are based, for instance, in TensorFlow, and application specific, they were only doing BNNs for crossbar, for Memory-Centric crossbar fault injection. The second problem of using existing tools is that we are restricted by the high-level programming abstractions of ML framework. So even though we could use PyTorch operations, which are general enough to write, let's say, our database kernels, it sounds off, right? And probably not going to be able to rewrite your whole application using PyTorch. And in the end, because you're not going to be using those optimized kernels, the simulation time is going to be even longer than if you have written in C, for instance. So in this table, there is still one more work called LTFI, which has never been used for logic in memory or processing using memory. So, and the purpose of this work was only for simulating software-based fault injection, simulating radiations, for instance, or process variation-induced bit flips. The good thing about this is that programmability is very high. Like they can support C code and MLIR code. I mean, here, as long as you have an LLVM IR input, they can support it. The problem is it is not really a fit to processing using memory as of, let's say, 6 months ago. Because our work in progress called Scribble builds on LTFI and also a Python library to try to cover this fault simulation for PIM. So Scribble stands for Scalable Cross-Layer Reliability Assessment for both bitwise logic and memory, and it is composed of those two main components. The first one is a Python library based on NumPy that enables accurate gate-level modeling of operations. However, due to the level of detail, it is going to be relatively slow or very slow. And the second component is the Scribble LLTFI fault injector. And this component operates at the instruction level. It requires no code modification and provides substantial faster execution. So from here, you can see that the fault probabilities that are informed by SPI simulation or real hardware evaluation, they can be forwarded to either the Python library or the Scribble LTFI. First, we use the Scribble Python lib not only for simulating small kernels, but also for generating operation level fault probabilities that you can then give as input to Scribble LTFI. One example, DRAM, you can estimate what is the fault probability of a single adder in integer 32, for instance. And as you have that exactly operation in LLVM IR, you define what is the fault probability for integer 32 addition. You could also use the raw fault probabilities of majority and not into Scribble LTFI, as long as you have a library that is implementing those operations. But then you wouldn't be as fast as doing the instruction level analysis. Right, so here, first of all, I'm gonna give a glimpse of how the Python lib works and what is in there, right? So we extend a NumPy here by supporting bit flip configuration and fault injection functions. Of course, that's the most important part of a fault injector. And we provide technology-specific fault model. That means that for different family of logics, you have different implementation. And then we have function overriding for creating a high-level simulation. Okay, so and the example of input is like this, as I'm showing here. You have the operation, the data pattern, and the error probability. Okay, so one small example, let's use a vector addition again. So in NumPy, you would write like this, and how actually the simulation is going to happen, like how the core is implemented, is that we are overriding the add operation and doing unpacking of bits and then calling majority carry adder. And this majority carry adder then has this, the calls to the majority logic. And the majority logical then has the injection of bit flips in it. Okay, so if you want to use that for simulating small kernels, how good is going to be, or how fast is going to be? You can see here, for instance, times per run and total time for 10K run. Notice, for instance, in the last rows that it doesn't scale very well for very standard, very small sizes of matrix multiplications. But still, you can get some analysis of, for instance, numerical error across those small kernels like addition, multiplication, and vector addition with the constant, right? Or simply you use this library for giving you the fault probability of one addition. Right, so then we go to the LLTFI component. And here, the compilation flow of LLTFI is going to use ONX and TorchMLIR for lowering machine learning models down to MLIR and then LLVMIR. And it is at the LLVMIR that the instrumentation happens. We're going to add functions before and after the region of interest, or the instruction of interest. So here, what we had to do to support logic in memory was basically to include multiple bit flips and stuck at fault. We also have this dynamic or like runtime random bit flip specification, which was not present in the tool before. And we also have this region, the annotation of region of interest, so you can kind of annotate which kernels are going to the memory, and that's where the tool is going to inject fault. And fault probability per instructions, of course, because prior to this, there was only a single bit flip in the whole execution, right? As I mentioned before. So how an application would look like now, imagine here, for instance, filtering by key. What you have to do is just place some annotation before and after the region of interest. And also you have to provide some compilation compilation and fault injection configurations here. For instance, here you can see what is the number of run, what are the bit probability, and what are the instructions to be included and the ones to be excluded, for instance. Right, with that, how fast can it be, right? So there are two overheads. The first one is the profiling overhead, which is a single run per kernel, a single run per application. It doesn't matter that much, right? So here, the overhead that I'm presenting is for running on the CPU. So imagine that this application filter by key would take 1 second. Now we are increasing by 50% for profiling, and we are increasing by 1.7% for fault injection. And this is the actual, the overhead that matters for us because we want to run thousands of runs, right? And as expected, the overhead is proportional to the fault probability. The more bit flips you have, the more you're going to preempt the usual flow, and you're going to include bit flips. So yeah, the higher the probability, the lower it is. Right, so beyond that, we also inheriting from LLTFI, we can support vision and NLP models. So here we are talking about models that not even the CPU it would fit. We can also do bit flipping using the GPU backend. And one of the ongoing works that I've been working here is also to support quantized models, because PUD is likely to work only with quantization, right? With integers quantization. So some additional work has to be done here, right? So just to, I'm already almost wrapping up. I just want to show one use case of Scribble. First, for protection and reliability research. So we were interested in analyzing how much redundancy mechanisms like triple module redundancy and ECC can provide, can protect execution. And for instance, in this example, we had a BERT model and a DNA read mapping algorithm under different configurations, right? So this is a paper that I'm going to be presenting tomorrow, count to multiply, tomorrow in the afternoon in the processing in memory session. So one second example here is that when I wanted to do research on data representation and unconventional arithmetic for processing data, yeah. So for instance, if you want to test data formats, redundant data representation, or unary coding, we've tried this in the past with different flavors of unary coding, and we did some fault injection on it as well. Right. So to wrap up, this is an effort along the line of providing tools for processing memory, right? And here we are targeting reliability assessment for comprehensive analysis of processing using memory, and also for a more systematic integration, investigation of software and hardware improvement techniques. So Scribble, the proposed tool, has these two levels of fault simulation that I explained before, and still there are some limitations. For instance, as you can imagine, because it is not an architectural simulation, you cannot play with data data mapping dependent fault probabilities or consequences of data mapping. Yeah, that's it. But with that, I conclude my talk, and I would be happy to take your questions.
Thanks for the call. I have a few quick questions regarding to the process. First is when you do them, actually the first step is doing a multi-color simulation. So for that, is like device level, or you have to like have a large like already placed and working device to do a multi-color simulation?
It is not device level. So the part that is device level comes before any of those simulations, right? So for instance, when I presented that example, that let me get that. This one. In this plot, it is experimental data, right? But now imagine that this is not experimental. Imagine that is a Monte Carlo simulation. You could build somehow a similar figure. And with that similar figure, you obtain the fault probabilities. So the Monte Carlo simulation that we do is in the application run, is to decide when I should, in which cycle of my application, I should flip a bit, and in which position I should flip a bit. That's where you need to sample.
Right. So my understanding is when you run this multi-color simulation on like one cell, and then you can use the data as a model to do a simulation.
The simulation is all on the cell.
Well, the simulation
is not on the cell. No.
Another question is about the whole process. You did all the fault injection with the processing memory, focusing on resistance-based PIM. I'm also wondering if you have all the kind of APPG process and fault detection process studies with it? You have something related to the fault detection process?
No, no. Yeah. Thank you.
Thank you very much.
Thank you.
You'll be back in 40 minutes.
What did I do both time?
The time that you want. Oh, hello.
Nice to meet you, Amanda.
I'm Ismail.
Nice to meet you.
Would you be okay presenting here?
Yeah, I wanted to just try that.
Could you send?
I was just trying to, I need to
Okay. Story. Okay, cool.
Okay. Mm. Oh, that's too long.
Oh, okay. Where should I start?
Just say the first 2 sentences.
Until use cases?
Yes, and then maybe just go and like something or research supported by.
Okay, research supported.
Yeah, I'm just I think like somehow just shorten it. Otherwise, yeah.
It should be fine. People will come during the
That's okay. Yeah, I think like the first couple of sentences and the last. It's
okay. First couple of sentences and then the support.
Yeah, maybe something like that.
Okay, let's start. Welcome everyone for the first session for the lunch. Here we have Professor Nisa from Georgia Institute of Technology. So Carlos is a professor in the School of Computer Science at Georgia Tech. Her research is focused on designing systems for emerging technologies, and she develops new systems and offers solutions in response to new hardware application and use cases. And her research has been supported by NSF, the Department of Energy, the Semiconductor Research Corporation, and by multiple industrial boards, including from Cisco, HPCA, IBM, Intel, Intercontinental Exchange, LexisNexis, VMware, and others. She's currently a PI and system software co-lead in the SRC DARPA Center for Processing with Intelligent Storage and Memories, PRISM for short.
Thank you so much. I appreciate the introduction. So this work is work that jointly with several of my PhD students, we've been doing as part of the PRISM Center that Ismail mentioned. In addition, part of the work that I'll talk about involves industry collaborators, particularly from SK Hynix. And as I said, this has been supported by the Center for the SRC DARPA funded Center for Processing with Intelligent Memory and Storage. So within the context of this PRISM Center, the emphasis is on developing new device technologies, architectures, and system software for next generation memory and storage. And a lot of what's the topic of this workshop is precisely these new capabilities of integrating computational capabilities with memory and storage. The work that my group has had in the context of PRISM has been more from an end-to-end perspective. Given these kinds of emerging capabilities, what do we need to do in order to adequately integrate these kinds of components in end-to-end systems? And so particularly the observation's been that there are new APIs, new control mechanisms, new system support for coordination that's needed, that just currently in a CPU-centric world where we have CPUs that run the core system software components and control the use and allocation of memory and storage resources, that it just doesn't map adequately to this new environment. There are three main thrusts that my group has been pursuing in this space. And what I will spend most of the time talking today will be this work on exploring this question of what do we need in order to effectively offload to the kind of PIM or near memory processing near memory architectures that are coming out of the work like what's presented here today, when we have the sort of CXL based computational memory components. And if I have time, I'll kind of touch on the other pieces. But the main, just to let you know, the other two main dimensions are looking at kind of what is the necessary control support, system support that needs to be integrated at the level of distributed frameworks. We used graph analytics as one driving use case, but there are other AI and HPC workflows that some of the other students are looking at. And then a third direction is looking at specifically how do we integrate these new capabilities at the level of the orchestrators, like the Kubernetes and similar. Okay, so the main topic for today is offloading to CXL computational memory, and we take a look at CXL as an interface to near memory processing, PIM, PNM type models. There have been two main models how CXL computational memory is going to be integrated, and this has been explored at some level in related work. One of the works that in particular we leverage is work that was published at Micro. They contributed open source simulation infrastructure that allows you to sort of independently look at the host processing and the host processing stack, as well as the CXL attached near memory processing capabilities and their interface. Now, when it comes to CXL as an interconnect, it exposes both, it allows you both to interact with the attached devices in a device-centric world via CXL.io and a memory-centric world via CXL.mem. This M2NDP work that was published a couple of years ago, but last year at Micro, it was arguing for, it leveraged the CXL.mem interface as opposed to the prior work that used the CXL.io interface, which eliminated substantial overheads of the IO path. So in this context, there's substantial number of works that have looked at many different classes of applications. And in the context of these classes of applications, they performed analysis over, on one side, what is the near memory acceleration that's necessary in order to better support these workloads, and then the other side, kind of how do you partition the applications so as to best benefit from specific near memory processing technologies. But majority of this work has really approached the space with the question of what do we need to offload, whereas from our perspective, we're asking, building on top of that work, but we're asking a slightly different question, and that is, what is the right low-level mechanism that we want to expose at the system software level in order to actually execute the offload? So to answer this question, we looked in more detail at some of the trade-offs between these for CXL, particularly devices, some of the trade-offs between the CXL.io versus .mem, sort of the device-centric versus the memory-centric view. And I'll put them in contrast and then kind of touch upon them. So in the device-centric view, we post a launch request, and then we configure the IO operation, which is basically based on polling of a remote memory location to find out when the memory, the CCM processing, the near memory processing completes. And then once that completes, then there is the actual data movement gets scheduled, and the host processing can continue. In the memory-centric view, interaction with the computational memory is using CXL load store operations, so CXL.mem. However, and so that's a much shorter data path that kind of allows, it justifies the offload of short memory operations because the this initial overhead can be amortized. And so that there is an opportunity for substantial benefits. However, it still exposes data movement in the critical path of the operation. So this is inherently a synchronous operation, and so when the kernel processing completes, then the data movement is exposed in the critical path. And so we for the different types of applications and benchmarks that I briefly showed earlier, we looked at both from a simulation environment as well as on real hardware, and of where time is spent during these offload operations. So on this this right-hand side, we have the couple of different kernels, different configurations, a couple of different applications, actually, different parameters. And then for these applications, there are specific steps that are offloaded. So it's not that the entire application is offloaded, but there are specific steps related, let's say in the graph analytics case, related to the traversal and the update of the graph. On the left-hand side, both of the for both of these cases, it's the same application benchmark, KNN, and these results are actually computed on real hardware. This is the SK Hynix X near memory accelerator, which accelerates some of the KNN processing. So a couple of things. So first, we use this real hardware infrastructure to validate some of the observations that we make in the simulation case. And second, we were able to instrument and sort of capture the breakdown along several components. So there is the actual time that's occupied by the processing near memory, but there are additional data movement components as well as host movement, as well as host processing operations. So there's some application classes where the fact that the primary focus has been purely on accelerating specific portion of the applications, that's very important because there are some workloads for which there is a dominant component of the end-to-end processing that really, that these workloads will see a lot of benefit from just accelerating this CCM-based component, this near memory component. However, there are many other workloads in which both the host processing is still important. This is not something that will be offloaded. And then this data movement component is also important. And this is the case both for the sort of the device-centric as well as the memory-centric view of the system. So this is what really motivated us to kind of revisit that there's some benefits of both of these modes, but in reality we need to figure out how to reconcile them. And in particular, and if we take a look at the two models, if we take a look at accelerating, so the CCL the memory-centric model has just really much lower protocol stack latency, which makes it desirable. But even with this model, there are a couple of components that need to be a couple of opportunities. So first, from when we invoke the operation from the host perspective until the data movement completes, there is a period of time that by default the host is idle. This is the host idle time, right? And so for workloads where there is host side processing that can occur, this is important to be able to leverage it. In addition, this data movement, once the host side processing, the CCM processing completes, there is still a portion of time where the CCM is idle because there is a portion of time to notify the host to transfer the data. And then there's an additional data movement period that needs to occur. So both of these times lead to inefficiencies, and they're non-trivial. So if we compare the end-to-end runtime, so this last bar in all of these plots that are gathered both from the real hardware as well as from this simulation setup, if we take a look at the percentage of the time that the host or the CCM component were idle, this points to significant inefficiencies. And the breakdown of these is on one side, this is really due to the sort of data movement is the dominant aspect. In the other side, it's the CCM processing. We're waiting on the CCM processing. That's the dominant aspect. So then our goal was, well, how do we make it possible to kind of achieve retain the low latency overhead of the .mem protocol compared to the .io protocol. At the same time, enable asynchronous execution and make it possible to hide these additional inefficiencies both from the host and the near memory device. So the protocol that ultimately we designed is one which combines both the CXL.io and CXL.mem operations that are supported by the CXL fabric. And adds to their use of pipelining. So the core idea is to instead of to start invoking functions at smaller granularity, to basically stage the CCM invocation and to start backstreaming partial results before the complete CCM processing functionality is executed. What that is going to allow, it's going to allow some of this data movement to be overlapped with the host and CCM processing, in particular, to the extent that there are host side operations that can be executed, they can start getting executed concurrently with the CCM processing. So in order to achieve this type of pipelined and overlapped execution, there are several aspects that are important for us to in some manner realize. We need to make it possible to efficiently notify, so both efficiently notify the host that there are results that are ready, and to quickly make that data that was generated on the CCM side available to the host. So these are these two requirements. We need to be able to achieve this overlap for different types of runtimes, different types of schedule executions on both the CCM and on the host, and do this while making some guarantees about ordering and memory correctness. So to explain the components of how we address these four aspects, I'll start with so this is the model of the system that we're working with. There is a host side compute resource that there are multiple processors, multiple threads that execute on them, and then there's some scheduler that's managing the execution of these threads on the different processors. And then on the near memory side, on the CCM side, we have again multiple fine-grained threads that can be arbitrarily scheduled. these get the kernels themselves are launched using the load store interface, and the actual data that gets produced is stored in these like initial buffers in these this result data. In order to expose data quickly back to the host side unit, what we want to perform, we want to proactively DMA chunks of this data, of this result data, as it gets completed, to start DMAing back on the host side. So we're using backstreaming support that CXL.io provides itself. So basically, we're combining the CXL.mem and the CXL.io protocols. So for this, we're relying on the backstreaming support from CXL.io. And on the host side, we're maintaining separate memory pools, buffer rings. One where these chunks of data get pushed, and the other that basically just maintains metadata. So you can think of this as maybe like sort of like a rich pointer structure that tells you which chunk is ready next. On the host side, the actual consumption of these memory chunks that get delivered is really controlled by the completion of the metadata ring. So this gives you a way both to control correctness, ordering, and this also gives you a way to integrate with a different scheduler. The combination of the two components is what allows the fact that you can allow the processing and the backstreaming of the data chunks to be completed while you're overlapping that with execution of other threads that may issue additional operations. This is what allows for the asynchronous operation. And that's what allows us to maintain the pipelining. And then ultimately, the one important aspect is that this has to be also integrated with the low-level CXL-based flow control mechanisms, because this is maintained. There's a credit-based flow control that's maintained at the fabric level, and so you can potentially run into some additional inefficiency unless this is coordinated. So to show some concrete results, we looked at if we evaluated this implementation of the system compared to both the CXL.mem and the sort of the M2 NDP and the CXL.io based implementations. And from a metrics perspective, we looked at end-to-end time. We looked at the kind of impact on utilization of the host and the memory resources, as well as some of the parameters of the system. And then from a benchmark perspective, we used a suite of different benchmarks where it's not that the entire application is offloaded, but we're looking at some of the evaluating the performance metrics from the perspective of the end-to-end application under workloads. But what's offloaded is just some subset of the operations that are supported by the computational memory. So from an end-to-end perspective, the first set of results, we looked at a large number of applications, and we're showing the breakdown for the data movement, the host side processing, and the CCM side processing. And we also have a version of the system implementation, Axel, that's not polling based. That's based on interrupts. We have polling based and interrupt based version. So the few things that are easy to highlight is that the asynchronous backstreaming protocol provides benefits across most of these workloads. So that's the blue versions of the bars. I think I lost this, the laser pointer. The blue versions of the bars. They provide benefits that are for either one of the polling. So the three blue versions correspond to three different polling intervals. The gray version corresponds to a interrupt-based implementation. So the interrupt-based implementation is particularly harmful when we have kind of more efficient kernel implementations that where we have more lightweight tasks, so then the interrupt routine becomes a bottleneck. Otherwise, for these following graphs, even the interrupt-based implementation is sufficient, not just the polling ones. The second thing to highlight is if we take a look at the blue bars and compare them with this breakdown, with the bars that show breakdown between the compute and the data movement and the host, we see that these blue bars basically kind of match the dominant component in the sort of in the breakdown of the different tasks. So meaning that the execution of the different types of steps on the host and CCM side is nicely overlapped, and this really corresponds to that dominant component. Now, if we go all the way back here in the very last figure, we see that there isn't much benefit. And so to explain what's going on in this last figure, so this is really a case where where we have just sufficient resources on the CCM side to when all the kernels that are invoked from the host side to get executed in parallel. So when we have this kind of operation that this kind of situation that accelerating some of these or speeding up some of the CCM functions really results in a marginal benefit. There's really not much benefit that we can see end to end. Now, if we create a modified configuration where now there actually is a bottleneck on the PIM side, so then actually performing the staging really leads to a more visible benefit. So for the same application, but just changing the configuration of the system so as to create some bottleneck on the CCM side, that ended up showing a benefit in this case as well. The initial configuration of the system was modeled more closely to match what was presented in that reference paper that we used earlier. We looked at, from an end-to-end perspective, we looked at kind of the impact of this protocol on the execution time, on the idle time, so on the utilization of the resources. So there is both on average, about 50% reduction in end-to-end execution time. And if we take a look, we see that we see that there is a significant reduction of the idle time, both on the host side as well as on the CCM side, right? And so this is the primary reason where that end-to-end benefit is coming from. There are some parameters in the system, particularly related to the polling interval and how data is chunked. And they actually do contribute to, they have some real end-to-end impact on the benefits that you can see. This is a great opportunity for these knobs to get basically exposed in application runtimes in the system software stack and be leveraged for fine-grained tuning of the protocol implementation. So we are really excited about the opportunities from this project, and we're continuing with some additional steps on really integrating this into end-to-end memory management, memory allocators that are used by application runtimes, and coupling this better with the application programming model. I have a few minutes. I don't have time to talk about other aspects in much detail, but I'll just briefly mention. So some of this, I'll skip this. Some of this work was motivated by work that we did. I'm sorry, moved into the opposite direction. Work that we did on system support for graph analytics in particular, with computational memory, where you both want to sort of perform partial offloads, but where the execution is such that over time, this question of which portion of the computation needs to be offloaded versus executed on the host changes over time. So this was what motivated some of the work that ultimately led to us really thinking and what's the low-level interface for this offload. So I'll stop here and take a couple of questions. Thank you.
Any questions?
So I have one question about the programming model on this backward streaming. So as soon as you have like large block that you operate, like large data item, you're operating it, and then you're back streaming block by block. So when are those blocks visible by the host application? Do you need to change anything, or what if you have like any irregular access? How do you deal with that?
So the data that gets, when you trigger the function, right? When you trigger the function from the host side, that function gets executed on the PIM side, and we assume that there's some level of concurrency there, right? That's kind of the assumption, where each of those threads produces some chunks of data. So there's even already, if we take a look at the various PIM, PNM type of models, that concurrency, that ability to kind of have some partial results that get concurrently created on the memory side, that's there already, right? So we're not changing that. So we're basically like, we're building on a model that says on the computational memory side, we're assuming that there is some fine-grained thread support, fine-grained parallelism and that's where we're building on. Now, that now needs to expose. So what we want now, we want control over how that gets pushed to the host and how that interfaces with upper level applications, so that the application is not just blocked overall because on the application side, we don't want to see these chunks over here, like these individual partial results. So all of that gets assembled into these memory buffers that, these ring buffers that exist on the host side. This is akin to what happens with our network interface, right? Like we get packets, and these packets get pushed into some buffer rings, like some ring buffers, and there is some completion queues that also have some ring buffers. But what we want to see at the application level, we just want something to get triggered when there is a completion event for the whole context, right? So it's the same. This is where we draw the ideas from.
So you're expecting the chunks, but then once all the chunks are arrived, then you start with the application processing.
Yes, though there is flexibility whether that's what you want to do. So that's basically, this is like by default you would want to have some logic here. There's the scheduler that sees, okay, this next chunk is ready, so I'm going to call the thread that was waiting on this data item. We can handle everything in a FIFO way, but it's not necessarily. So we can have a FIFO scheduler, or we can have a scheduler that is scheduling the request out of order, right? So you can still ensure that by maintaining this metadata order, you still know which data was completed, which request was completed. But if your application, if you're allowing concurrent requests to be issued from different processes that don't have to be processed in order, the scheduler can allow that. Okay, thank you. Thanks a lot.
From KAIST, system software support for integrated systems. Domja is a third-year PhD student at KAIST, advised by Professor Mutlu. He received his bachelor's degree in electrical engineering from Korea University and his master's from KAIST. His research firm primarily focuses on system-level support for processing memory architectures.
Yeah, just a bit. Okay, hello everyone. My name is Dongjae Lee, and I'm a PhD student at KAIST. Today, I'd like to share my research on architectural and system software support for PIM integrated systems. As many of you are aware, the entire computing stack, from algorithms down to architecture, has been built upon a single foundational assumption that memory is strictly for storage. However, the emergence of processing in memory, so-called PIM, where memory handles both storage and computation, breaks this decade-old convention. To truly establish PIM as a first-class citizen in modern computing, we must now revisit and redesign the entire system stack. In our efforts, which refers me and my collaborators, to revisit the stack, our work focuses on characterizing commercial PIM-enabled systems, such as unmanned PIM. As illustrated in the figure, these PIM modules, highlighted in yellow, are integrated directly into standard DIM slots, coexisting with conventional DRAM modules within a production-grade CPU server. This physical integration allows the host CPUs to offload memory-intensive tasks to the PIM-enabled memory. By performing a detailed analysis of these commercial PIM systems, we can derive critical insights that guide us in designing more efficient, PIM-friendly architectures and system software stacks. This understanding is the key to bridging the gap between the theoretical PIM benefits and practical system performance. In this talk, I'll present two of my two core projects. The first, shown in the bottom, focuses on optimizing data movements by revisiting the host processor's architecture. And the second introduces a PIM-aware dynamic memory allocator, a work that will also be presented in detail during the main HPCA conference. Let's dive into the first project, PIM-MMU. Before I present about PIM-MMU, I'd like to acknowledge my colleagues, Bong Junhyun, Taehoon Kim, and Professor Min-Soo Roo. So let me introduce the research scope of this work. Unmanned PIM has a PIM core in each DRAM bank, and it is built upon a DIM form factor. Such PIM-enabled DIM is attached to the CPU along with conventional DRAM. And one of the biggest characteristics of unmanned PIM system is that it employs a separate physical address spaces for DRAM and PIM. As such, Current PIM programming model requires programmers to first allocate the input data in the DRAM address space and then explicitly copy the data to the PIM address space. However, our work has identified DRAM to PIM data transfer is a high overhead. According to our experiment, during DRAM to PIM data transfers, DRAM bandwidth and PIM bandwidth is only utilized less than 15% of its theoretical peak value. Now, you may wonder why current PIM systems employ a separate address space for DRAM and PIM. This design decision is due to the limitations coming from the existing DRAM-specific protocols, such as DDR4 JEDEC, which dictate a fixed latency behavior. Let's consider where both the host processor and the PIM core tries to access the same memory bank within the PIM device simultaneously. Since DRAM cannot handle both requests simultaneously due to structural hazards such as shared I/O bus within the DRAM device, one of the requests is delayed in processing. In the example shown in the figure, the DRAM bank access request from the PIM core waits for the host processor to finish accessing the memory. As a result of this delay, the access latency for the DRAM bank by the PIM core changes. Therefore, it cannot maintain a fixed DRAM latency. Consequently, PIM vendors have designed their system to prevent this situation by only allowing a single entity to access the PIM address space, either the host processor or the PIM core. For instance, if the PIM core is not operating, the host processor can freely access the PIM address space. However, if the PIM core is currently accessing the DRAM banks within the PIM device, the PIM library blocks the host processor's access by disabling the entire PIM address space. Since such approach prevents the host processor and the PIM core from accessing the same bank simultaneously, separating the address space can eliminate structural hazards. Through this section, I'll present characterization on unmanned PIM to root cause the underlying challenges of its DRAM to PIM data transfers. The DRAM to PIM data transfer involves three main stages. First, it reads data from DRAM, and the CPU or the host processor, so-called host processor, pre-processes the data, and it writes the pre-processed data to the PIM device. Our first key observation is that because the CPU is in charge of orchestrating the entire process of data transfers, it significantly taxes the host processor by launching multiple threads, leading to high power overheads. We measure active core percentage and increased system power during DRAM to PIM data transfers. The x-axis represents the timeline, the red line represents the active core utilization, and the black line represents the increased system power consumption. According to our experiment, CPU core utilization reaches to near its maximum levels and reach close to 70 watts of increased system power consumption. Our second observation is that PIM systems show low PIM throughput. I'll first explain the difference between DRAM access and PIM access. Memory mapping is the process of translating physical addresses into specific DRAM hierarchy, such as channels, ranks, and banks. By employing this, DRAM can exploit high memory level parallelism, so-called MLP, by partitioning the data across different DRAM subsystems in a fine-grained manner. However, PIM access is concentrated to certain PIM channels because PIM programmers explicitly designate which input data should be transferred over to which PIM core's memory bank. Thus, it shows lack of memory level parallelism. To overcome such limitations, unmanned PIM leverages thread level parallelism to maximally utilize available memory bandwidth. Unmanned PIM library launches multiple software threads for DRAM to PIM data transfers by having each thread to perform read and write operations, targeting different levels in the PIM channel. In the example shown in the figure, the host processor launches multiple threads solely for data transfer, with each thread handling data transfers to its respective PIM channel. However, such thread-level parallelism approach is highly dependent on operating system thread scheduling policy. Although the operating system schedules thread to prioritize fairness, it can lead to inefficient utilization of memory bandwidth because certain memory channels are preferentially accessed for a certain period of time. For instance, if the operating system thread scheduler prioritizes the execution of 3 PIM threads, transferring data to channel 0, and 1 thread transferring data to channel 3 during a time interval t, channel 0 will experience a higher concentration of data accesses. To maintain system-wide fairness, the scheduler may adjust the scheduling priority during the next time interval t+1 to allow more threads dedicated for PIM channel 1 and PIM channel 2 data transfers. While such scheduling policy better guarantees fairness, it can lead to inefficient utilization of memory bandwidth because certain memory channels are preferentially accessed for a longer period of time. We show the breakdown of data write throughput during DRAM to PIM data transfer and DRAM to DRAM data transfer, which I refer DRAM to DRAM data transfer as memcopy. The x-axis represents the execution time, and the y-axis represents the throughput ratio breakdown between the memory channels. Due to the concentrated data traffic to certain PIM channels, DRAM to PIM data transfer is not able to fully utilize memory-level parallelism. For instance, within a given time frame, channel 2 data transfer is concentrated, whereas other channels experience low bandwidth utilization. On the other hand, DRAM to DRAM data transfer shows high bandwidth utilization due to the help of memory mapping, which evenly distributes data traffic across all memory channels. Before I talk about our third observation of low DRAM throughput, let's recall back the previous presentation slide. As mentioned previously, current PIM systems separate the physical addresses of DRAM and PIM to prevent structural hazards. However, not only PIM systems separate physical address space, but it also modifies memory mapping to prevent segments of both DRAM and PIM physical addresses from being mapped to the same memory bank. As shown in the left figure, since the current memory mapping interleaves addresses across different devices in a fine-grained manner, PIM address space can be mapped to DRAM device, and DRAM address space can be mapped to PIM device. As such, PIM vendors change their memory mapping with the system to make sure that the physical DRAM addresses are mapped locally within the DRAM device, and PIM addresses are also mapped locally within the PIM device. However, when changing the memory mapping, it removes memory mapping performance optimization techniques, such as XOR hashing, which lead to low DRAM throughput. We measure the DRAM throughput of systems configured with modified memory mapping for PIM systems and compare it to systems using conventional memory mapping under various access patterns. Regardless of the memory access pattern, the DRAM throughput with the modified memory mapping is only 30% of what is achievable with conventional memory mapping. Now I'll introduce our approach, PIM-MMU, which efficiently transfers data between DRAM and PIM. PIM-MMU consists of 3 key components. First, to mitigate high CPU core utilization and power consumption, we propose an accelerator called the data copy engine. Second, to improve PIM throughput, we introduce a scheduler named the PIM-aware memory scheduler. Lastly, to enhance DRAM throughput, we present a heterogeneous mapping unit. I'll first explain the details about data copy engine. The data copy engine is placed within the host processor, which is a dedicated accelerator for DRAM to PIM data transfers. In our proposed system, PIM programmers can completely offload DRAM to PIM data transfers to a data copy engine, whereas the baseline system leverages multiple CPU cores to manage data transfers. Therefore, as a data copy engine can handle end-to-end DRAM to PIM data transfers without CPU intervention, it only requires low CPU core usage compared to the baseline system. It is also important to note that to maximize the throughput for data copy engine, it needs to optimally schedule memory requests. I will now explain our scheduler named the PIM-aware memory scheduler, which is implemented within the data copy engine. Our key observation of PIM memory transactions is that there are no true data dependencies across different PIM memory transactions. This is because before computation begins on the PIM core, the programmer partitions the input data, assigns each partition to specific PIM address, and transfers the partition data to the corresponding PIM core. To maintain the integrity of offloading process and to ensure that all inputs are transferred correctly, the programmer must carefully assign each segment of the partition data to a unique PIM address. As all of the transactions have unique PIM addresses, there are no data dependencies. With such freedom, PIM-aware memory scheduler can schedule PIM memory transactions in any order. For instance, if there are 4 PIM transactions, as shown in the figure, the order of scheduling these transactions do not change the result of the DRAM to PIM data transfers. Due to timing constraints, I will not go over the details of the algorithm. You can refer to the paper for a detailed explanation. Lastly, I will now talk about how heterogeneous mapping improves the DRAM bandwidth. Compared to the current mapping, where it only supports a single mapping function, heterogeneous mapping employs 2 separate memory mapping functions, each optimized for a different design objective. The physical address space reserved for PIM utilizes a locality-centric mapping, whereas the physical address space allocated for DRAM employs a throughput-centric mapping. With the help of MLP-optimized memory mapping functions for throughput-centric mapping, memory mapping scatters physical addresses of PIM across different DRAM devices, and it significantly increases the DRAM bandwidth. Now I'll present the evaluation results of PIM-MMU. We employed a hybrid evaluation methodology that utilizes both cycle-level simulations to measure the DRAM to PIM data transfers and measure the wall clock time measurements from our real unmanned PIM system to measure the PIM kernel execution time. And also, to simulate the cycle count of the baseline unmanned PIM's data transfers, we compiled the unmanned PIM's runtime library function, which handles DRAM to PIM data transfers and extract the instructions. And I'll explain how end-to-end performance changes with the help of PIM-MMU. The level end-to-end performance improvement PIM-MMU provides is obviously dependent on how critical the DRAM to PIM data transfer is. So for instance, if you see the breakdown here, if the red bar and the yellow bar's ratio is low, the performance improvement of PIM-MMU is decreased. Nonetheless, PIM-MMU provides an average 2.2 times improvement in end-to-end performance across entire PIM benchmarks. To conclude, this work consists of 3 main parts. This work includes a detailed characterization on DRAM to PIM data transfers within the PIM system. And we propose a harder software code design that enables fast and energy-efficient data transfers, demonstrating its efficiency over the existing PIM system. And now I'll talk about PIM-malloc, which is a fast and scalable dynamic memory allocator for PIM architectures. And I'd like to acknowledge my colleagues, Bong Junhyun, Professor Youngjin Kwon, and Professor Min-Soo Roo. I'd like to say that current PIM systems face a critical challenge. If you look at the software stack here, there is a major mislink in the runtime layer, especially for memory management. The absence of this layer places entire burden on developers. To address these issues, our goal is to design an efficient dynamic memory allocator specifically for PIM. However, this isn't just an engineering task. We need to tackle two key questions. First, what kinds of PIM workloads require dynamic allocation? And second, what makes memory management uniquely challenging in PIM-based architecture? To answer the first question, I'll explain why we need a dynamic memory allocator for PIM. PIM workloads such as graph analytics and LLM inference are highly memory bounded, but also dynamic. However, current PIM systems lack efficient dynamic allocation support, leading to significant performance bottlenecks. Today, I'll use graph analytics as a representative example to illustrate this issue. For more details about the LLM inference, you can refer to the paper for detailed explanation. Many real-world graphs are dynamic. They evolve over time. For example, in a social network, new friendships can form between users, as shown in the right figure. So updating the graph data should not become a performance bottleneck in graph analytics. This is where dynamic memory allocation becomes essential. Without it, programmers are forced to use static structures like compressed sparse row, which require rebuilding the entire array on every update, resulting in linear time complexity. With dynamic allocation, we can use pointer-based structures that only update a single reference, achieving near constant time performance. We demonstrate the performance slowdown as the size of the graph is increased from small to large. Note that the graph updates using dynamic data structures are implemented using our proposed PIM-malloc. When the graph is stored in a static compressed sparse row format, the graph update latency is proportional to the total size of the graph because its time complexity is linear. In contrast, the size of the graph has a negligible impact on graph update performance with dynamic data structures. So we've established that dynamic allocation is essential for PIM workloads. Now, let's turn to the second question. What makes designing a memory allocator for PIM uniquely challenging? Within the PIM module, each DRAM bank contains a PIM core as colored in blue, which significantly increases the aggregate memory bandwidth. While this PIM design effectively enhances overall memory bandwidth, each per bank PIM core can only access the data stored within its respective local DRAM bank. As a result, the PIM system must manage thousands of distinct memory address spaces, one for each PIM core. This leads us to the first challenge. To implement dynamic memory allocation for PIM, each address space requires metadata to manage its own heap region. As shown in the left figure, metadata bit 0 indicates a free block, while metadata bit 1 represents the block in use. However, managing thousands of these address spaces triggers a metadata explosion, leading to significant memory overhead up to gigabytes. This raises a key question. Should metadata be stored centrally on the host CPU or distributed across PIM cores? Now I'll explain about the second challenge. A PIM system consists of two distinct compute units, the host CPU and the PIM cores, which has fundamentally different characteristics. The host CPU shown on the left is a high-performance engine operating at several gigahertz with advanced features like range predictors and prefetchers. In contrast, PIM cores illustrated on the right are massive in number, but operate at much lower frequencies due to DRAM process limitations. This disparity leads us to a fundamental question. Which processor is truly optimal for executing a sophisticated memory allocation algorithm? This is a critical question, as it directly dictates the overall speed of memory allocation in our system. To address these design challenges, we can think of this as a 2x2 design space. Metadata can be stored on the host or PIM, and the allocator can be executed on the host or PIM. And this gives us 4 possible designs, ranging from fully host side to fully PIM side, with 2 hybrided approaches in between. With these 4 candidates in mind, let's see how they can perform. We evaluate how allocation latency scales with the number of PIM cores across our 4 design strategies. The x-axis shows the number of PIM cores, while the y-axis represents the total latency of our micro benchmark. Design 2 and 3 require explicit metadata transfers between the standard DRAM and PIM memory to execute the allocator. As we add more PIM cores, the metadata overhead grows proportionally, causing a significant bottleneck in system-wide allocation latency. Design 1, shown in gray, eliminates data movement between the DRAM and PIM. However, it faces scalability issues because CPU's compute parallelism is inherently limited. Next, let's look at the PIM metadata and PIM executed approach. Despite using relatively simple or so-called wimpy PIM cores, this method provides a high scalability because it allows each PIM core to process allocation requests locally and in parallel. Therefore, we conclude that this approach is the optimal design for a high-performance PIM memory allocator. This insight directly guides our design. Based on our design space exploration, we introduce PIM-malloc, a fast and scalable memory allocator. We propose 2 PIM-malloc variants. First, PIM-malloc software optimizes performance through software alone, making it ready for existing hardware. Second, PIM-malloc hardware software achieves even higher gains by employing a lightweight hardware software co-design. I'll explain PIM-malloc software in this talk, and later I'll explain PIM-malloc hardware software in tomorrow's main conference. As shown on the left, each PIM core has its own local memory allocator, which operates independently. It employs 2 hierarchical allocator design, as shown in the figure. The level 1 allocator is named the front end, and the level 2 allocator is named the back end. Now, let's look at why we designed it this way. Within the commodity PIM core, it supports multi-threading with up to 24 threads to maximize PIM core's performance. This creates significant contention when threads compete for shared allocator resources. Hence, we focus on eliminating thread contention. We achieve this by assigning a private front-end allocator to each thread, ensuring exclusive access without any mutex overhead. The front-end allocator specifically manages small-scale memory operations, covering requests under 2 kilobytes. Meanwhile, the backend handles requests over 2 kilobytes. While it is shared across PIM threads, our hierarchical design minimizes contention. This is because the front end filters most traffic, significantly offloading the backend. While PIM-malloc software performs well, PIM's unique constraints limit software-only optimizations. As you can see, memory allocation requires multiple metadata accesses, such as searching and updating, which is one of the primary allocation overheads. due to time constraints, I won't be able to deep dive into all the details today. So if you're interested, you can attend this conference, and I'll explain more about this. And thank you for listening to my presentation, and I'll be happy to answer any questions. Thank you.
Thanks for the great presentation. I'm Zhiheng from Shanghai University. So I have two small questions for the second work, the PIM malloc.
Oh yeah.
So I think years ago there was a work from David Brooks from Harvard University. They proposed a malloc accelerator.
You mean malloc? Yeah, it was Expo 2017, I guess. Yeah.
There's also several foreign papers, and I know that some industry they actually designed this kind of accelerator in their CPU SoCs. So what if you compare to this kind of accelerator rather than the CPU itself?
Okay.
The benefit of the PIM.
Oh, so you're asking about the architectural difference between the prior works and the PIM malloc hardware sub.
To the CPU, then PIM allocator is much better. If you compare to some dedicated accelerator for application, what are the advantage for the PIM allocator?
So I think the main advantages of the PIM allocator is that, as you also know, PIM core's computation throughput is highly limited due to DRAM process. So to actually further enhance the performance of PIM malloc, we need a dedicated accelerator. And also there are different characteristics of, there are some differences between the prior work and our work. So you can, I think I can explain more in detail after the talk. Yeah.
The second small question that is about future. So if the malloc is actually put on the pins, and we can imagine that there might be more and more system services. Because there's a lot of like memory management, scheduling, these kind of system services. Could they be also stacked on top of PIM in the future? If going that way, then PIM more like a CPU core, then might be a problem.
I think this is quite an open question, so I don't have a definite answer right now. But I think like this might happen maybe after 5 years or 10 years, and I think we need to continue doing our research, and I think we need to consider various options. And for now, I think it might happen, yeah, in my personal opinion. Yeah, thank you.
So how do you see this in a big picture of highly virtualized server systems? You have to find a way to share hardware, right? I mean, we built GPU in the early 2000s, and the GPUs were basically you own it or you break it, right? And it took years to develop virtualization support on these. And as soon as you split these all up into smaller pieces, I mean, 2 kilobytes, that's laughable, right? I mean, we're talking nowadays gigabytes, hundreds of gigabytes, even terabytes of RAM. So what is your view to carry this kind of toy concept up to real life?
Oh, so I think there are two questions mixed. So as far as I understand, how can we support virtualization for PIM? And the second is, why did I support a small allocation support for PIM malloc? Is that correct?
Not just, I'm talking about how do we integrate this concept of having PIM computing memory into a virtualized system?
Yeah, okay, thanks for the great question. So to integrate the virtualized system, I think this is orthogonal to our work, but I think we need a memory management unit. because we need to support isolation between different tenants and to provide security and isolation. So I think it's an interesting part of research, and I'm a big advocate for it. Yeah.
Have you looked into memory management systems within the CPU, in a real CPU, and how like page tables are managed in a bigger system, including keeping them synchronous and synchronized between multiple hardware CPUs?
Yeah, I was interested in looking at the memory management of like page tables. So yeah, I've looked at it in detail, and we also published a paper called UPinulator, and it also discusses about the case studies of memory management in PIM systems. But I think we need a further work and more researchers to actually make that happen. Yeah, thanks. If there are more questions, we can talk it offline.
Just to give a very quick question.
Oh yeah.
When you see the data copy engine you mentioned, that's the first part.
Oh yeah, yes.
What's the difference between data copy engine and DMA engine?
Oh, so you're asking about the difference between the DMA engine and the data copy engine, right?
Yes.
I think the main difference between the DMA and the data copy engine is that the data copy engine enables like PIM-aware scheduler within the data copy engine. And also, I didn't explain in the slides, but to actually transfer the data to PIM, we need to pre-process the data. So to pre-process the data, there's a pre-processor within the data copy engine. So I think that's the main difference between this difference compared to the conventional DMAs. Yeah.
All right. So in upland PIM modules, it's not just a memory map. And the modules you have to pre-process it.
Yeah, we need to. Yeah, we need to transpose the data because it's in a DIM form factor and it has some kind of unique characteristics going on. Yeah, thank you. Okay. Yep. 힘들다. 네, 감사합니다. 박스네. 네? just a minute.
For PhD student in software research at ETH under supervision of Professor Mutlu. She's growing interested in computer architecture and more specifically in security, reliabilities, and safety of memory systems, merging memory and computation paradigms, including processing memory architectures and designing effective and efficient solutions to address robustness issues in modern and future systems.
Okay, should I go ahead?
Yes.
Thanks a lot for the introduction. Hi everyone, I'm Nisa, and today I'm going to talk about one of our recent works called Revisiting Main Memory-Based Covert and Side Channel Attacks in the Context of Processing in Memory. This work was published in DSN last year, so it's one of the recent works that we did on PIM security that we haven't had the chance to talk about today, but now we will do a deep dive into it. So let me start with an executive summary. Processing in memory architectures alleviate data movement bottleneck by bringing computation closer to where data resides. And these architectures and techniques are being adopted in real products today more and more. However, no prior work analyzes and evaluates the security of PIM architectures against timing, side, and cover channel attacks. In this work, we make the key observation that PIM architectures create opportunities for critical main memory-based timing attacks due to two main reasons. First, these architectures and techniques provide direct access to main memory to user space applications, which is a key building block for high throughput main memory-based attacks. And second, defenses against these attacks are either highly costly or they're not applicable to PIM architectures. We introduced Impact, which is a set of high throughput in-memory processing-based timing attacks that leverage direct and fast main memory accesses enabled by PIM architectures. Impact provides high leakage throughput by first eliminating expensive cache bypassing steps used in many main memory-based timing attacks, and it leverages the intrinsic parallelism of PIM operations. We demonstrate impact with 3 case studies. We first built 2 high-throughput covered channel attacks leveraging different PIM architectures. And then we demonstrate a side channel attack that leaks private information of concurrently running victim applications with a low error rate. Lastly, we discuss and evaluate 4 different countermeasures against impact, eventually concluding that mitigating impact incurs high performance overheads, and this highlights the need for low-cost mitigations against impact for robust future systems. Impact is open source and artifact evaluated, and you can check our source code and data from this link. This is the outline of my talk. Let's start with the motivation and the problem. We talked about the data movement bottleneck, but to refresh your minds, today's computing systems are processor-centric, which means that all data is processed in the processor at a great system cost. In order to do a computation, we first need to fetch the data to the compute units and then do the computation. And then when we get the results, we send them back to the main memory. This leads to spending more than 60% of the total system energy on data movement. Processing in memory architectures alleviate data movement bottlenecks by moving computation to where the data resides. Such architectures can be implemented by adding logic near the memory arrays in what is called processing near memory, or by using the analog operating principles of the memory cells to perform the computation in what is called processing using memory. A set of these PIM architectures are already implemented in real products, and some of which are shown in the slide, and many more are expected to be adopted in the near future. Therefore, it is very important to investigate the security aspects of such techniques and architectures and implement countermeasures to avoid any potential widespread security vulnerability that their deployment can cause. However, no prior work analyzes and evaluates the security of emerging PIM architectures against timing, covert, and side channel attacks. In this work, we focused on main memory-based timing channels, where an attacker exploits the shared main memory states to leak information. An important example of this type of attack is DRAM row buffer-based attacks. Here we see a DRAM bank with multiple DRAM rows, all connected to one row buffer, which acts as an in-DRAM cache. In order to access data in one of these rows, for example, row A, we first need to open row A, which brings the content to the row buffer, and then perform the read and write operations. So an access to an open row is served from the row buffer with lower latency because the data is already fetched. In order to access another row, we need to first close this row and then open the second target row, which is much slower. And this is why an access to any other row is served with higher latency. This difference in latency creates 2 distinct states observable from user space applications. An attacker can exploit these states to, for example, send messages between attack processes by encoding each bit of this message with high or low latency, or to spy on other concurrently run applications, victim applications, in what is called cross-CPU attacks. In this work, we make the key observation that PIM architectures create opportunities for critical main memory-based timing attacks due to 2 main reasons. First, these architectures provide direct access to main memory, which is a key building block for high-throughput main memory-based timing attacks. And second, defenses against these type of attacks either incur high performance overheads or they are not applicable to PIM architectures. Now, let's talk about the first reason a bit more. Here we have our attacker in our system with a core and our main memory. And in this attack vector, the attacker leaks information by timing a memory access. To do so, the attacker reads data from the main memory, sends a read request, and then gets the data back. And by timing this sequence, the attacker can leak information of 1 bit, either high latency or low latency. To leak even more information, the attacker needs to repeat this process many times and get many measurements. And this is why high throughput attacks require reliable and fast access to main memory such that the attacker can do these accesses quickly and get many measurements. And high throughput attacks are difficult in compute-centric architectures because in between the core and the main memory, we have deep cache hierarchies. And these deep cache hierarchies either filter memory accesses such that they are served from the caches instead of the main memory, or even if they go to the main memory, they are going through the deep cache hierarchy, which incurs additional latency, which means that they are slower. In these systems, the attackers manipulate the caches to access main memory with a higher probability by bypassing the cache hierarchy with eviction sets, basically creating many accesses such that they go to the main memory instead of the caches. and by using cache flash instructions. And only after these steps, the attacker can access main memory and get those measurements. But this comes at the cost of a higher access latency because of the cache hierarchy. In processing in memory architectures, this is different because these architectures provide user space applications with fast and reliable main memory access. When we consider processing using DRAM, these techniques operate on the memory array itself, such that they bypass caches completely. When we consider processing near memory, let's say that we have some compute units near our memory banks. These compute units are very simple. They either have small caches or they don't have any caches due to thermal dissipation limitations, such that the attacker can offload their instructions to these compute units and have direct access to main memory by either not needing to bypass the caches because there are no caches, or by more easily bypassing them. Now, let's move on to the second reason. Defense against these attacks either incur high performance overheads or they're not applicable to PIM architectures. There are two existing defense approaches to main memory-based timing attacks. The first one is to fundamentally eliminate the timing channel itself by employing closed row policy or constant time memory techniques. This means that all memory accesses have the same latency, but it is often the worst case latency. And this is why these solutions based on this approach have higher performance overheads. The second approach is to restrict the use of the timing channel by restricting cache flash instructions such that the attacker cannot reliably access the main memory, or by detecting attacks based on cache statistics by saying, okay, I have a high cache miss ratio, which means that I might be experiencing a main memory timing attack. But these are not applicable to PIM architectures because, again, these architectures provide bypassing the caches completely. The introduced impact, which is a set of high throughput in memory processing-based timing attacks that leverage direct and fast main memory accesses enabled by PIM architectures. Impact provides high leakage throughput by first eliminating expensive cache bypassing steps and leveraging the intrinsic parallelism of PIM operations. We demonstrate impact with 3 case studies. First, we build 2 covered channel attacks on processing near memory and processing using memory architectures. And then we demonstrate a genomic privacy attack in processing near memory architectures. Before moving on to these case studies, I want to first talk about our evaluation methodology. We evaluate these case studies by simulating PIM architectures based on seminal works using a system simulator with these configurations for a modern system. And we compare our covered channels against the state-of-the-art covered channel attacks. And all of these can be found in our GitHub repo. Now let's move on to the first covered channel, which is impact processing near memory covered channel. For this case study, we assume PIM-enabled instructions as our baseline processing near memory architecture, which introduces compute units called PCUs on the host side and on the memory side. And the management unit manages these PCUs and decides where to execute an operation, PIM operation, similar to this instruction, based on its locality characteristics. So if the operation benefits from deep cache hierarchies, it is executed on the host side, where it can get the benefit from those. And if it benefits from reduced latency instead, it is executed on the memory side to have direct access to main memory. And our key attack mechanism offloads attack instructions to a memory side PCU to eliminate expensive cache bypassing steps. Let's look at an overview of the attack. So here, again, we have our shared DRAM bank here, DRAM banks, each having one PCU. And our sender and receiver wants to send some messages using this shared memory structure. So they start by collocating data in the same set of DRAM banks, similar to this one, similar to this picture. Here, they don't share any actual data. They have their own pages, separate pages, but they are located in the same set of DRAM banks. So they share the row buffer instead. The receiver starts the attack by initializing the row buffer states by executing one PIM instruction in each of these PCUs corresponding to one DRAM bank. This practically brings the receiver's data to the row buffers by basically initializing the state of the row buffer. And then after that, the sender can transmit this message. The sender splits this message into m-bit batches, and here is the number of banks that we have in our system, and transmits m-bit at once by using the parallelism. So here we see that each bit is mapped to one PCU, And based on the bit value, the sender either executes a PIM instruction, which then brings the sender's data to the row buffer, or executes a no-op operation, which then results in no change in the row buffer state in the corresponding DRAM bank. After this, the receiver can measure access latency by, again, executing PIM instructions in each of these PCUs and measure the time to do these accesses to understand what the sender is transmitting. For example, in bank 0, the receiver measures high latency because its data is replaced in the row buffer, and then can detect that the sender is sending a 1 bit. And in the last bank, since the row buffer state is not changed, the receiver measures a low latency and then can detect the bit as a logic 0 value. And by using these measurements, the receiver can decode the message. So we basically validated this proof of concept for this attack by sending a 16-bit message using 16 DRAM banks. And here in this plot, you see on the x-axis the message, and you can see each bit. And on the y-axis, we see the latency measured by the receiver in cycles. So these are the measurements. And as you can see, the receiver basically measures high latency where the sender is sending a logic 1 value. And the receiver similarly basically measures a low latency when the sender is not sending, the sender is sending a logic 0 value. And we conclude that the receiver successfully determines the transmitted bit values by detecting the row buffer conflicts in these banks. We then evaluate the communication throughput using one sender and one receiver process using, again, 16 DRAM banks across increasing LLC sizes to show basically the impact of LLC sizes. And we basically observed that impact processing near memory provides a high communication throughput of 8.2 megabits per second by eliminating expensive cache bypassing steps. And this does not depend on the LLC size because the attack processes can bypass the caches. Now let's look at the second covered channel, which is based on a processing using memory architecture. So for this covered channel case study, we assume a processing using memory architecture that provides user space applications with row clone, which enables bulk data copy and initialization operations, and can copy ranges in selected banks. So we already covered row clone a lot, but let me refresh your minds. So let's see how DRAM operates. Let's say that we want to access a data in the source row. We first need to activate that row, which brings the content to the row buffer. And then to access another DRAM row in the same bank, we first need to pre-charge the first row, and then basically this results in writing the content back to the cells. And then we need to activate the destination row, which will again brings the destination's content to the row buffer. Prior work show that if you skip the middle step, if we activate source and then activate destination row, we can first copy the content of the source row to the row buffer and then write back to the destination row, which is practically a copy operation from the source row's content to the destination row. And we assume 2 copy operations are available in the system, and we can exploit parallelism by copying ranges across all banks, which says that basically, let's say that we have this copy operation from range A to range B. This is translated into multiple copy operations, each corresponding to one bank. And in the second version, we assume that we can do a selective copy operation with a mask operation. Then we give another mask vector to this copy operation, which then translates copy operations to multiple copy operations corresponding to this mask. The attack overview is, again, very similar to the one we discussed, even though the underlying architecture is different. After the receiver initializes row buffer states by executing PIM instructions here, row clone instructions here, the sender issues a row clone operation that is performed on the selected DRAM banks based on the message bits. And doing so allows us to leverage the intrinsic parallelism of the processing using memory operations and set the row buffer states according to the intended message. And we can do this at once. And then the receiver measures the latency of performing row clone in each of these banks and decodes the message. For example, we see that in bank 0, the sender would be changing the row buffer state, and then the receiver would be measuring a high latency compared to the other ones that the sender did not change the row buffer state. We again validated this proof of concept by sending a 16-bit message using 16 DRAM banks, and this is very similar to the results that we discussed. And here again, we conclude that the receiver successfully determines the transmitted bit values by detecting row buffer conflicts. We again evaluated the communication throughput using one sender and one receiver process across 16 DRAM banks, and we show that impact processing using memory provides a higher communication throughput of 14.8 megabits per second by exploiting intrinsic parallelism of processing using memory operations. And this is again irrespective of the LLC size. Next, we compared this cover channel throughput to different attacks, basically. On the x-axis here, we see the increasing LLC sizes. And on the y-axis, we see the leakage throughput in terms of megabits per second. So for this comparison point, for this comparison study, we evaluated the state-of-the-art main memory-based timing attack, which is DRAMA, with different cache bypassing methods. We used a CL flash-based cache eviction method, and then basically having the second version is basically having a lot of evictions by sending many requests. And we see here that DRAMA-based attacks have basically a decreasing throughput, leakage throughput, when we go to higher LLC sizes, because the eviction gets more costly if you have higher access and higher eviction latencies. Next, we evaluated an attack, again, a row buffer-based attack, but this time it uses a DMA engine to bypass the caches. And these are the results. As you can see, the throughput is consistent across all LLC sizes. Again, it doesn't increase, the cost doesn't increase for this, but the throughput is low because with the DMA engine, we are subject to high OS-related overhead. So the software stack dominates basically it reduces the attack throughut. And these are the leakage throughput results for impact processing near memory and processing using memory. And as you can see, the attack leakage, the leakage throughput is consistent across LLC sizes, and it is very high compared to the other ones. And we also observed that impact processing near memory and impact processing using memory outperforms all state-of-the-art main memory-based attacks across all LLC sizes. We also compared the two different impact attacks to each other, and we basically looked at the latency of each of these attacks. And we basically show here a breakdown of the sender and receiver routines. The first one is the latency of the sender routine, and the second one shows the receiver routine's latency. And the difference really comes from the parallelism that we exploit in the processing using memory attack. So since we are able to send the receiver copy operation at once, which translates into multiple requests that are going to different banks, we are able to execute it much faster, which then gives us more leakage throughput. And this is why the impact processing using memory's sender routine takes less time. Now, let me move on to the last case study, which is a processing near memory-based genomic privacy attack. I will only give you the highlights in the interest of time. In this case study, we looked into DNA read mapping, which is a fundamental task in genomics. And basically, we have some DNA fragments, and we have a genome that we want to basically construct with these fragments, but we don't know the order. And this is very useful for many applications like biological research or forensics or drug development and so on. And as you can imagine, DNA is one of the most privacy-sensitive data that is out there. We don't want to lose the information of our DNA to attackers. And basically, the application itself, it uses a lot of methods use hash table-based methods. And this is basically very good for processing in memory, such that we can parallelize all of these tasks and accelerate it with processing in memory architectures. But this also creates an opportunity for an impact attack. And in this case study, we show that an attacker can successfully leak characteristics of the DNA sample with low error rate by leveraging the PIM operations. Lastly, let me talk about the mitigating impact. Again, we discussed several mitigation directions, showing that we basically evaluated 3 existing mitigations, showing that they are restrictive and are highly costly. And we proposed and evaluate a new mitigation to reduce the channel capacity instead of basically eliminating the timing channel completely. We also show that basically after all of the analysis, we observe that it still induces a high performance overhead to reduce the attack throughput a lot, and a better mitigation is needed for future systems. So mitigating impact incurs high performance overhead, and more research is needed to find low-cost solutions. There are many more analyses and results and details in the paper, starting with the operational details about the side channel attack. And we also evaluate the throughput and accuracy analysis, accuracy of the attack. And again, more details on the mitigations for impact, discussing and evaluating 4 countermeasures. We discuss other potential PIM attack vectors, and we discuss what would happen basically if it's a good solution to this attack to restrict the access to PIM operations and so on. And you can find all of those in the paper. Impact is open source and artifact evaluated, and you can check it out and try it and let us know if you encounter any issues. And now let me conclude my talk. So in this work, we made the key observation that PIM architectures create opportunities for critical main memory-based timing attacks due to 2 main reasons. First, these architectures provide direct access to main memory, which is a key building block for high throughput main memory-based timing attacks. And second, defenses against these attacks are either highly costly or they're not applicable to PIM architectures. We introduced impact, which is a set of high throughput in memory processing-based timing attacks that leverage direct and fast main memory accesses enabled by PIM architectures. Impact achieves high throughput by eliminating expensive cache bypassing steps used in many main memory timing attacks, and it also leverages the intrinsic parallelism of PIM operations. We discussed 3 case studies demonstrating 2 covered channel attacks with high throughput, and we showcased the side channel attack that leaks private information of concurrent learning applications with low error rate. We lastly discussed and evaluated 4 different countermeasures against impact, eventually concluding that mitigating impact incurs high performance overheads and more research is needed to enable future robust systems. Thanks a lot for listening. I would be happy to take any questions.
Any questions? Surprisingly, we are early this session, so we're on time. And let's get back at 4 p.m. Thank you.
So.
Yeah.
Yes.
Let's
try this now. Yeah,
No.
it's
Oh,
let
thank
me
you.
introduce you. Okay, welcome back to the last session for today. So, next presenter is Mutlu. Did I pronounce it correctly? It's how it's Mutlu.
경무구.
Sorry.
I think.
From INM University. So he's going to talk about informing overcoming bandwidth and capacity inefficiency based on context inference systems. He's a second year PhD student in the integrated MS PhD program at INM University, advised by Professor Jumo Cho, and member of the AI Hardware and Algorithm Lab. He received his bachelor degree from INM University, and his research focuses on optimizing PIM-based memory-centric systems with an emphasis on system architecture and end-to-end performance efficiency.
Thank you. Hello, everyone. My name is Kyungmo, and today I'm excited to present our work on PIM-based acceleration for long-context LLM inference. This work is a collaboration between Hanyang University, SK Hynix, and KAIST, and it explores how we can better utilize PIM processing in memory systems under emerging long-context LLM workloads. In this talk, I will first introduce the motivation behind long-context LLMs, then discuss why existing PIM systems struggle in this, and finally suggest PIM-friendly, our solution to address these challenges. LLM has evolved beyond simple text generation. They can now analyze a lot of information and do more reasoning. And when an LLM is trained to reliably handle many words and sentences, we called it a long-context LLM. In practice, these enable applications like code assistants that analyze large code bases and multi-document Q&A. More recently, reasoning LLMs has become a big topic since last year. They repeat their thinking process and run longer through test time scaling, which lead to better performance. If you look at the figure on the right, you can see that when the model generates more tokens during its thinking process, it tends to solve math problems better. Overall, these applications push LLMs to handle more tokens. If you look at the LLMs being released recently, the context window, which is the maximum number of tokens a model can handle, has grown a lot. As early as last year, the Llama 4 Scout model already pushed it to about 10 million tokens. To get an intuition, OpenAI notes that 100 tokens is roughly 75 words. So at this scale, a model can take in something like 10,000 news articles or around 1,500 research papers in a single context window. Before we discuss efficiency for long context LLM computation, let me briefly review how LLM inference works. LLM inference has two stages, prefill and decoding. In prefill, the model processes all input tokens in parallel and stores information. In decoding, it generates output tokens one by one based on the processed input. If you zoom into decoding, each token is turned into a vector and passed through multiple decoder layers. Inside each layer, there are two main computations, FC, which use the trained weight metrics, and attention,
which use an accumulated matrix of KV cache vectors from previous and current tokens. In both cases, the input vector perform a GenV with a matrix. And GenV is widely known to be memory bound because the matrix has low reuse. On GPUs and similar processors, we usually run batched inference to improve efficiency. In serving, for example, GPUs process multiple users' requests together. Then the FC part becomes a gem because different users' input vectors share the same weight matrix, and that helps reduce the memory bound issue. But for attention, each user has their own matrix, so it still runs as GenV. As the context length grows, the attention workload and the KV cache footprint grow proportionally. That lowers the overall arithmetic intensity, so the memory bottleneck gets worse. And it can also limit the batch size. These challenges have driven prior work toward PIM-based solution for bandwidth and capacity limitation. Previously proposed PIM-based system fall into two main types. One is a heterogeneous system that uses both a processor like a GPU and PIM. And the other is a PIM-only system. A representative example of the first type is NewPIMS. It schedules FC on a NPU and attention on PIM. For the second type, there is send. FC and attention run on PIM, while other operations like normalization run on processing in near memory. Before I explain how PIM executes computation, I want to quickly walk through the hardware components. On the left, you can see a prototype PIM card, AMX, developed by SK Hynix. And on the right is a high-level architecture overview. The PIM hub include multiple PIM controllers and an instruction sequencer and a shared general-purpose register file in SRAM. Each PIM channel contains multiple banks. In each bank, there is a processing unit and an output buffer, and all banks shares a global buffer. This architecture enables near data computation, but it also introduces unique scheduling and memory management challenges. Now here is how a GenV runs on PIM. Input vectors is in SRAM, and the weight matrix is stored in the memory banks. First, a write input command copies input vector into the global buffer. Next, a back command performs GenV inside the bank level processing unit and write the result to the output buffer. Finally, readout command brings the result back to SRAM. These commands are issued sequentially by the PIM controller. To keep the operation correct, we need proper intercommand timing. When controller tries to run MAC right after write input, MAC cannot start until write input has fully placed input into the buffer. Similarly, readout cannot start until MAC has fully finished it and the output is in the output buffer. So we must control the gaps between commands based on their execution time. With PIM-based LLM inference, attention latency still increases as the context gets longer. What we found is that under long context, prior PIM systems suffered a big drop in PIM utilization. In this plot, as the attention overhead increased by about 3 times, the computation utilization drops to roughly half. This suggests that prior PIM systems are not taking full advantage of PIM in long context LLM inference. From our analysis, we see three main bottlenecks in prior PIM systems for long context inference. First, PIM channels are underutilized because long context aren't mapped in parallel efficiently. Second, static command scheduling as unnecessary stalls, which directly limits PIM throughput. Third, static memory management wastes capacity by reserving space for worst-case context lengths. Together, these inefficiencies make PIM utilization the new bottleneck as context length grows. To address this utilization drop in long context inference, we propose Symphony with three key techniques: token-centric PIM partitioning, dynamic command scheduling, and dynamic PIM access. TCP maps context tokens across channels to maximize parallelism, but since I want to focus on what is most relevant to this workshop, I will skip the detail today. Instead, I'll focus on command scheduling inefficiencies and memory capacity waste and show how DCS and DPA address them. In existing systems, the host or the compiler generates the PIM command stream for a target GenV. In this example, we need 3 consecutive write input commands to store input tiles in the global buffer. Then we run 3 MAC commands to compute on 3 matrix tiles, followed by 1 read MAC to read back the results. If we repeat this once more, we finish the computation for 6 weight tiles. So overall, the compiler generates 11 commands and send them to PIM controller. And the controller then executes them in the same order they arrived in the command queue. And it applies intercommand timing based on each command's execution time to preserve correct GenV functionality. For simplicity, I will use shortened names for each command based on its type and the order it appears. For example, the first write input command is called W0, and the MAC command that is included first is called M3. These slides show a timeline of PIM command execution. After W0 finishes, you can see that the input data has arrived at entry 0 of the global buffer. So M3, which uses that input, is ready to run. But in practice, it cannot run until W2 finishes, and that creates a stall. This happens because the static scheduler enforces fixed intercommand timing between write input and MAC, regardless of data dependencies. The same thing happens here. At this point, M7 is also ready because its input tiles is already available, but it still waits until R6 finishes, which again creates a stall. Since the static scheduler executes commands in a fixed order, it does not issue MAC commands even when they are ready after I/O transfers, and this directly leads to PIM underutilization. These plots show the fraction of stall cycles as a function of GenV input length. Compared to a fully connected layer, QK transpose, which is part of the attention computation and involves frequent output transfers, show a much higher stall ratio. This inefficiency aligns with our earlier observation. As long context inference increases, the dominance of attention, PIM utilization degrades even further. To address this issue, we introduce dynamic command scheduling or DCS. To reduce unnecessary stalls, DCS changes the PIM controller in 3 ways. First, it uses 2 command queues, one for IO transfer command like write input and read out, and another for MAC commands. This allows the controller to run IO and MAC commands out of order when possible. Second, it adds 2 small tables. A dependency table tracks which command must happen before another. A status table tracks which command is currently holding the global buffer and the output buffer, and until when. Third, each command includes an ID, so the controller can distinguish one command from another. It also includes dependency information, so the controller knows what it must wait for. Here is a simple example of in-queue time. When M3 enters the controller, the dependency table already has the information that for global buffer entry 0, W0 is the last command that must finish first. So M3 is tagged with W0's ID, which is 0. Then the controller checks the status table and issues M3 only after the dependency is cleared. In this way, DCS can execute out of order while keeping correctness. For more details, please refer to the paper. With DCS, once W0 finishes, the controller knows that M3's data dependency is resolved, so it can issue M3 right away. And at this point, it can also see that M7 dependencies is resolved, so it can run M7 before R6. So overall, DCS schedules commands based on data dependencies, not conservative timing. It overlaps IO transfers and MAC to remove stalls and keep the pipeline busy. We compare DCS with conventional techniques, ping-pong buffering. Ping-pong buffering splits a buffer into 2 regions and then alternate between IO transfers and computation on each region. So the 2 can overlap and improve efficiency. Let me use an example where the global buffer has 64 entries. If we split in half, we get 2 regions with 32 entries each. I will visualize a sequence of write input operations on one region as a single parallelogram. In ping-pong buffering, each region is used by write input and MAC in turn. So if the next MAC needs to use gbuff0, it has to wait until the most recent write input on that region finishes due to fixed intercommand timing. Similarly, if a write input wants to use gbuff32, it has to wait for the most recent MAC on that region. After both operations on a region complete, write input and MAC switch to the other region and continue. This repeated switching creates switch overhead, which leads to stall. DCS behaves differently. It does not split the global buffer. As soon as write input for gbuff0 finishes, it can immediately run the MAC for that entry. This keeps write input and MAC pipeline continuously and removes stalls. To compare 2, we measured on utilization on attention workflows where IO transfers are frequent. Across different attention operations, we observed up to 1.4 times performance improvement with DCS. Next, we focus on improving capacity utilization. To motivate DPA, we first examine why existing PIM systems use memory capacity in a static and wasteful manner. PIM instruction sequences for LLM attention are constructed by repeating command pattern per token. However, existing PIM systems lack control instructions, so they must explicitly unroll commands for an assumed number of tokens. As a result, systems conservatively allocate memory and generate commands for the worst-case context length, Tmax. In practice, most requests do not reach this maximum length, leading to significant memory capacity waste. This problem becomes more severe under long context inference, where token length variation is large. To address this, we introduce control instructions that encode token repetition and virtual address access. DYN loop instruction encodes token-dependent instruction repetition, and DYN modi instruction encodes token-dependent virtual address access. With DPA, PIM instructions are dynamically decoded at runtime based on the current token count and VA to PA mapping, enabling true dynamic memory usage. In this slide, we explain how DPA instructions are decoded on module and at runtime. The left side illustrates the on-module dispatcher, which performs DPA instruction decoding and instruction dispatching entirely at runtime. The configuration buffer stores per request metadata, including the request ID and the current token length, tcur. This information is used to specialize DPA instructions for each active request. The VA to PA table maintains the mapping between virtual addresses and the physical addresses where the KV cache is actually stored. This allows instruction to be written using virtual addresses while still accessing the correct physical memory location. DPA encoded instructions are stored into the command buffer, where the DPA command decoder expands DPA encoded instructions into per request executable instruction sequences, and finally dispatched to instruction sequencer. We show how a DPA encoded instruction sequence is decoded step by step for a specific request with example of request 2. Since request 2 has a current token length of 300, the loop bound is decoded as 3, causing the lower 3 instructions to be executed 3 times. During each iteration of dynamic DYN loop, the coefficient T in the DYN modi instruction starts from 0 and increases monotonically. The DYN modi instruction is then decoded to write coefficient values to the target addresses, which are assigned as contiguous virtual addresses. These virtual addresses are then translated into the physical KV cache locations by consulting the VA to PA mapping table, where the KV cache is stored. This DPA mechanism enables per request instruction sequence generation and dynamic memory management at runtime. When new KV cache is allocated to memory, only the VA to PA table needs to be updated without modifying any other component. The animation shows that dynamic memory management can accommodate more requests. Across diverse long context benchmarks, we achieve on average 2.1 times improvement in capacity utilization. In conclusion, DPA improves PIM capacity utilization and enables larger effective batch size. Before jumping into the results, let me quickly go over our experiment setting. For models, we use Llama class 7 billion and 72 billion, and we evaluate both with and without GQA. For workloads, we focused on two long context benchmark, LongBench and LVEval. Also, LVEval has much longer context on average, roughly 3 to 4 times longer than LongBench. And context length varies widely across requests within each workload. So we evaluate under non-uniform context lengths. On the system side, we consider two platforms. First, a PIM-only system based on CENT. Second, a heterogeneous MPU plus PIM system based on UPIMs. Finally, we scale the system memory capacity with the model size. We use 128 gigabyte for 7 billion model and 512 gigabyte for the 72 billion model. With that setup in mind, I will move on to the evaluation results. On this slide, I report the throughput results for the PIM-only system on LongBench and LVEval using both 7 billion and 72 billion. Overall, PIM-friendly improves throughput by up to 11.3 times over the baseline PIM-only system. Among the three techniques, DCS contributes the largest gain. We also see a clear trend that the benefit grows with longer context lengths because the baseline becomes severely underutilized as attention gets heavier. So PIM-friendly's utilization improvements translate directly into higher throughput, especially in long context setting. Here, we move to the heterogeneous system. We still get a large improvement up to 8.4 times end-to-end throughput. One interesting difference is that DPA behave differently from the PIM-only case. In this setting, the MPU handles FC. So when DPA increases the effective batch size, it can directly boost MPU throughput as well. The main takeaway from these end-to-end results is that we need all three techniques to get the full benefit. This figure makes one point clear. PIM-friendly improves throughput across both system scale and context length.
for now, and then we'll figure it out. I think this is okay, right? Ismail?
Yes.
Okay.
So I don't need this?
Yeah.
Huh? Okay, yeah. So what I was saying before is that these sequencing machines extract these smaller fragments of the original DNA, and these are called reads. And genome analysis then later works with these reads, right? So one of the key important steps is read mapping, which is the first step in many genome sequence analysis applications, which aligns reads to these potential matching locations in a reference genome. And for each matching location, the alignment step finds the degree of similarities and differences between these compared sequences. And actually this similarity or difference can lead to various medical or biological implications. But the problem is that it's a very computationally intensive step because it relies on approximate string matching fundamentally, right? So the problem, therefore, that we face in genome sequence analysis is that we need to perform expensive computation in large amounts of data, and therefore we are facing computational overhead and data movement overhead from the storage system all the way to the computational units. So what is metagenomics? Metagenomics refers to the study of sequences of diverse organisms within a shared environment. For example, like human blood, ocean, soil, etc. And it overcomes the limitation of traditional genomics because it bypasses the need for analyzing individual species in isolation, which is something that is not possible in all scenarios. And because of that, it has led to groundbreaking advances in precision medicine, understanding microbial diversity of an environment, and discovering early warning signs of communicable diseases. And because we don't know what are the species that are present in a metagenomic sample, metagenomic analysis typically involves these key steps in high level. One is preparation of input queries. Basically, what it does is that it extracts some k-mers, which are sequences of length k from input sequences. And then by looking up these k-mers in a large database containing information on many species, it figures out what are the species that are present in the sample. And these databases actually can be really large, and their size keeps growing as we discover more species and also add more samples to it. So anyways, at the end, there are many optional steps. For example, one common thing is to figure out the relative abundance of species that are present in the sample. Basically, that's all the genomics, or let's say metagenomics background we would need for this talk. So don't worry if you don't know more details about these fields. So the problem that we have with genomics and metagenomics today is that we have these specialized, very fast machines to generate the data, but then relying on general purpose computing systems for analyzing this data is very ineffective because it leads to a lot of performance and energy overheads and challenges. And because of the importance of the field and also the computational challenges that we face, a lot of companies and also academia have tried to look into developing specialized hardware and other means of accelerating these applications in this domain. And there's been, therefore, a lot of contributions in developing faster heuristics, specialized accelerators, or specialized filters. And they have led to large contributions in lowering computational overhead, but we still suffer from the data movement overhead from the storage system. So the case I want to make in my talk today is about storage-centric systems for genomics and metagenomics and what they can enable. I'm going to very briefly talk about some of the works we've been doing in this direction by talking about our storage-centric design for genomics called GenStore, for metagenomics, which is called MEGIS, and in some emerging areas in genomics and metagenomics, grains and Mars, and also efficient analysis and compressed genomic data, which is our work stage. So let me talk a little bit about what GenStore is. So the key idea of GenStore is to filter reads that do not require expensive alignment operation inside the storage system, so that we only send the reads that require more heavy computation to the computational units outside the SST, like SST here in the case, that's the storage system we evaluate. So yeah, we only basically send what really needs to go through expensive computation. And examples of reads that can easily be filtered with minimal computation are exactly matching reads, because they don't need approximate string matching. And non-matching reads, basically reads that do not have any potential matching locations and can skip alignment altogether. And of course, there was a lot of challenges that we had to address to enable this design. And it was the fact that the read mapping operation can exhibit vastly different behavior based on the information encoded in the genomic data. And the other point is that there are limited hardware resources in the storage system. So by addressing these challenges, our designed GenStore, we proposed GenStore, which is the first storage processing system designed for genomics, and we showed that it can, therefore, by basically filtering reads inside the SST, alleviate computational and data movement overhead significantly, and provide large speedups and energy reduction when it is integrated with software and hardware mappers. And you can find many more results and details in our paper. Now let me talk about our work MEGIS, which is a storage-centric system for metagenomics. Here you can see the overview of metagenomic steps that I've talked to you about. So because metagenomics requires accessing this large database, we perform a case study on metagenomic analysis tools with various types of SST configurations, and observe that compared to an idealized scenario with no I/O overhead, both performance optimized and cost optimized storage systems, the I/O overhead stemming from accessing data from them leads to significant performance overhead. And we also observe that I/O becomes even larger overhead in systems where other bottlenecks such as main memory and computation get alleviated. And actually alleviating and addressing this I/O overhead, or like completely avoiding it due to accessing large amount of low reuse data is very challenging. And one might think that, okay, we can do some sampling techniques to make this database smaller, but that actually leads to accuracy loss to levels that will be unacceptable in many applications. And specifically because these applications are used in areas that for which precision is very important, such type of, let's say, techniques to necessarily shrink the databases for sampling would not be effective, right? So the other potential solution might seem to be keeping all data required by metagenomic analysis completely and always in main memory. But such a solution is energy inefficient, costly, unscalable, and unsustainable because of two reasons. First is that the database sizes, which I already mentioned, are very large, increase in size rapidly, doubling of almost every few months. And the other point is that different analysis need different databases. So it would be very expensive and energy inefficient and unscalable to perpetually keep all the possible databases that we might need in possible analysis we want to run in main memory. So motivated by these points, our goal is to improve metagenomic analysis performance by reducing large data movement overhead from the storage system in a cost-effective manner and with high accuracy. And of course, it is very beneficial to analyze this data directly within the storage system. So it can be a very promising direction to achieve our goal. But the problem is that none of the existing metagenomic analysis tools can directly run inside the storage system due to SST's limitations. For example, long latency of NAND flash chips, limited DRAM capacity inside the SSD, and limited DRAM bandwidth inside the SSD. So in this work, in our work MEGIS, we present the first in storage system for end-to-end metagenomic analysis. And the idea behind it is to have cooperative and storage processing for metagenomic analysis, which is enabled by hardware-software co-design between the storage system and the host system. So to leverage and orchestrate the capabilities of both systems, MCCSys includes hardware-software co-design in 5 directions, and I'm briefly going to talk about them. One is task partitioning and mapping, such that each step executes in its most suitable system. I'm not going to talk about the details of it, but I invite you to check our paper if you're interested. The second step is data and computation flow coordination, such that now that we are taking advantage of both of these systems, we don't want data movement between them to kind of amortize our benefits. So we need to reduce the communication overhead between these things. And the third aspect is software-aware algorithms, which enables efficient access patterns in the SST, and then some software optimizations that we would have in let's say compute-centric systems or in CPUs would not actually be effective in this storage-centric way of computing. So we needed to rethink the algorithms in that sense. And the fourth direction is lightweight and storage accelerators to minimize SRAM and DRAM buffer spaces needed inside the SSD because it's a more constrained environment. And finally, is data mapping scheme and flash translation layer specialized to the characteristics of metagenomic analysis. We have many results in the paper, but I wanted to just very briefly summarize this one particular result, which I think can nicely show what benefits storage-centric computing can provide to this domain. So I'm going to show results in 2 systems. One is a cost-optimized system with a cost-optimized low-bandwidth SSD and 64 gigabytes of DRAM. And the second case is performance-optimized system with a performance-optimized SSD with high bandwidth and 1 terabyte of DRAM. And now on the x-axis, so we're seeing the performance-optimized and accuracy-optimized metagenomic tools that run in both subsystems. And MCCSys running on the more cost-optimized system. And when we look at the results, we see that when all of them are compared on the same type of systems, of course, like MCCSys provides large benefits. But when we observe that MCCSys outperforms the baselines even when running on a much less costly system. So yeah, we hope that actually such type of system design would enable better, let's say, wider adoption of these metagenomic analysis applications by lowering system costs significantly and not relying on, let's say, massive systems. There are a lot more details in our paper, which I invite you to check. And I'm going to also briefly mention our other works in some emerging areas in genomics and metagenomics. So one of them is related to large-scale genome graphs. So as opposed to having linear input sequences, graph-based representation is more powerful and efficient representation of genomic databases because it has greater expressive power and is more compact representation of this massive population scale databases. So our work GRAINS is a first in storage processing system for large-scale genome graphs, and is enabled by more friendly analysis via specialized execution flow and scheduling. And we further improve performance, energy efficiency, and cost effectiveness via in storage and in flash processing. And we show that it significantly improves performance and energy efficiency of the system while having a very low cost design. There is also the other direction that we work on, which is raw signal genome analysis. And so this is a conventional view of the end-to-end genomic workflow. So we have some raw signals generated from the sequencers. Through a process called base calling, they turn into ACGT characters that we typically work with. And then we have this read mapping process. Raw signal genome analysis tries to basically skip some steps and do this more direct analysis. And it can contain richer information than bases, and it provides opportunity for more efficient analysis with better scalability and portability in some scenarios and some use cases, important use cases of genomics. Our work Mars is first in storage processing system for raw signal genome analysis, and is targeted, it has, of course, again, software modifications targeted to optimize this domain for in storage paradigm, but also it leverages processing in memory within the SSD to accelerate raw signal genome analysis. And I invite you particularly to check this paper because it tries to leverage the rich substrate that modern storage systems are and leverage various modes of near data processing to accelerate this important domain. And yeah, you can you can check a lot more details in the paper. So before I conclude, let me briefly talk about our work Sage. So this work also is going to be presented in the Tuesday session, like last session on Tuesday. So if you're interested, you can also attend that to hear more details. But I'm going to talk about a little bit like high-level overview of it, basically. So because of the important role that genomics and metagenomics is playing in many fields, and because of the significant recent drop in sequencing costs, what we observe is fast growth in genomic data volumes. And because of that, there's been a lot of effort to accelerate genome sequence analysis, as I have talked about some of them in this talk, but also many more works and efforts in this direction. But also at the same time, there are a lot of efforts to store genome sequence data in highly compressed formats. So the problem that we look into in this work is data preparation bottleneck, where genomic data is decompressed and formatted first before an accelerator can even start operating on it. So let me talk about the impact of it in a very high level. So consider here a simple baseline pipeline that data preparation and analysis are happening on different batches of genomic data. And a second case, I'm showing a scenario where analysis is significantly accelerated. It's not drawn to scale because it will be very difficult to see, but anyway, you get the point. And the third case is an idealized scenario where the analysis step is no longer bottlenecking the end-to-end pipeline. So by considering the first and last scenario, we can see that there's a lot of benefits in accelerating genome analysis. But by comparing these two cases, we see that the large part of this benefit actually gets lost due to data preparation bottleneck. So our work Sage aims to address this by proposing an algorithm architecture co-design for highly compressed storage and high performance access of large-scale genomic sequence data. And the key insight we have is that information encoded in genomic data follows the specific properties. And actually, we can take these properties into account to co-design a lossless compression decompression algorithm, a very lightweight hardware for decompression with simple operations and efficient access patterns, and storage data layout and interface command to access data. And we show that by integrating Sage with genome analysis accelerators to prepare data for them, we can significantly improve the performance and energy efficiency of end-to-end analysis pipelines. We basically enable unleashing the potential benefit that these acceleration efforts can provide by more efficiently preparing data for them. While ensuring that we still provide high compression ratios comparable to state-of-the-art genomic-specific compressors, and having a very low overhead design, which enables us to integrate Sage with genome analysis systems, even when they're implemented in resource-constrained environments, such as near data processing systems implemented in main memory or storage systems, some of which I already talked about earlier in my talk. And yeah, for more details, please check our paper or attend the session on Tuesday. But to wrap it up, I hope that I could make the point that storage-centric systems for genomics and metagenomics can provide large benefits by improving performance, energy efficiency, and cost effectiveness. And while I didn't talk about it exactly in this talk, they can also improve robustness, security, and privacy. And we hope that such type of designs would make accurate metagenomic analysis more accessible for their wider adoption. Before I finish, I also want to hijack this workshop by talking about our own workshop. So that was yesterday anyway, but this is the ongoing initiative that we have in our group. We have had our second iteration of the workshop here in conjunction with HPCA. Previous one was with Micro, and for the next ones, please stay tuned. We will have next iterations of it lined up. But basically, what we're looking into in this Arc for Health initiative is that recent biotechnological advances enable high throughput, low cost, and accurate biological data generation, such as genome sequencing, which I talked about, continuous wearable sensing, medical imaging, etc. And this wealth of data enables unique opportunities for advancing healthcare by enabling and facilitating precision medicine, bedside personalized care, discovering early warning signs of communicable diseases, continuous physiological tracking, enhanced diagnostic capabilities, and many more. But a problem we have is that efficiently analyzing such large-scale biological data poses significant challenges for conventional computing systems in terms of performance and scalability, energy efficiency, privacy and security, and cost effectiveness. So the goal we have in Arc for Health initiative is exploring the key computational challenges in health-related applications and the vital role of computer architecture in overcoming them to advance and accelerate important areas in healthcare. And some of the example areas are computational biology, neuroscience, wearable systems and biosensors, medical robotics, mental health, medical imaging, agent-based simulation, and many, many more. This was our agenda yesterday. We are the organizer, so that's the first one will be me. Then we have Konstantina, and who is a postdoc in our group, and Professor Onur Mutlu, who leads our research group. So yeah, more information about the workshop. The workshop is also recorded and it's on YouTube. So if you missed it, you can also take a look at it in more detail. This is also what we had in Seoul, so in Micro. So if you're interested, you can also watch it and check our website. And if you or anyone you know is interested in such directions, please reach out. And yeah, that's it. That's my talk.
Any questions? Can I ask one question? So
what's a K-mer?
No, I'm not there yet. So this is storage-centric, as title says. So is there an opportunity for other memory technologies? I know that the data is huge, that you need to use storage. You need to have storage in order to have all of these. But is there an opportunity for other memory technologies? As I remember, like CAN-based systems for this string matching, right? So can we have a pipeline of memories that can offer this, let's say, computation, lower latency, and higher throughput, but can operate on less data? So do you think it is possible to have like a pipeline-ish part that's storage, DRAM, RAM, I don't know, like some emerging neural technologies?
Yeah, that's a very good question. So the first point I want to clarify is that one of the benefit of a storage-centric systems is, of course, it comes, one aspect is that it is like storage provides lower cost and higher density in that case. And if the volume of the data is larger, you can more easily rely on it. But a more fundamental benefit is that if you have low reuse data, which is originally stored there, then the earlier you get rid of it, the better, right? So regardless of data volume. So that is why the angle for computing inside the storage would be helpful. So I wanted to clarify that. But other than that, having like, let's say, pipeline or like, let's say in a sense, computing everywhere would also be beneficial for sure. And various memory technologies, of course, provide different benefits, and there's a lot of work, as you also mentioned, in string matching and CAN-based structure or other memory technologies. I definitely think that we should leverage, let's say, what we would benefit from in different parts of the system for different operations, and they can be integrated together. Actually, in one example would be in GenStore. We also evaluate a case where GenStore is integrated with SRAM-based genome analysis system to show that how they can collaborate in performing different parts. And like GenStore basically filters some very low reuse data inside the storage system, and the rest of it can go to other, let's say, PIM-based or other types of systems that perform genome analysis.
Thank you.
Yeah, sure, thanks. I was already.
Okay, thank you very much.
No, it's fine. I'm just. I see. Okay. It's good. Stay close here, it would be great because
okay, so let's continue with the last talk of today. Last talk is Rakesh's talk, and Rakesh is a fifth-year PhD student in the software research group at ETH Zurich, advised by Professor Mutlu. His main research areas are heterogeneous memory and storage systems, new data processing, and machine learning in computer architecture. Before joining software, Rakesh worked as a senior staff engineer at Samsung Semiconductor Research Labs, and he has obtained a master's degree in electrical and computer engineering from the University of California at Irvine.
Thank you so much, Nisa and Ismail, for giving this opportunity. So today I'll be presenting this work, Conduit, which it's a sneak peek of our talk tomorrow, which is at 12 p.m. In the near data processing session. And this work is called Conduit, which is a programmer transparent near data processing framework using multiple compute capable resources in solid state drives. The idea is to kind of pick up on where Nika left in the Mars work, where we show that SST is a rich substrate with multiple heterogeneous compute resources. And the idea is to leverage all of them in a general purpose manner to accelerate a broad range of workloads. So this is the outline of my talk. I'll start with a bit of background and motivation. So here's very high-level overview of a modern SSD. So an SSD has an SSD controller, which is the brains of the solid-state drive. It has multiple embedded cores, which basically run the flash translation layer or the firmware. And there are multiple flash controllers, which interact with the flash chips via shared channels. There's also a DRAM component inside the flash, inside the SSD, which is basically used to store recently accessed data and also part of the mapping table. Now, as I mentioned, solid state drive is a very rich substrate with multiple these compute resources. So we start with ISP, which is a near data processing paradigm, where we use the embedded cores to perform some computations. A large body of prior works have shown that these embedded cores can accelerate complex tasks like filtering, aggregation, encryption, and search, and so on. Now, there is also this DRAM component that I mentioned, which is capable of performing bulk bitwise operations and arithmetic operations. And these are performed using the DRAM's intrinsic operational principles. And we have discussed these works in the morning, like AMBET, SIMDRAM, and MIMDRAM, which enable these bulk bitwise and complex arithmetic operations entirely within the DRAM chips. Now, if we move to flash chips, we can perform computation by exploiting the flash chips structure. We have several kinds of techniques like Aries flash, which enable arithmetic operations inside the NAND flash chips by controlling the latching circuit of the page buffer. Then we have Flash Cosmos, which enables bulk bitwise operations within NAND flash chips by simultaneously reading multiple pages. Now, if we look at the trade-offs of these NDP paradigms within an SSD, if we look at ISP, ISP supports a broad range of computations, but the flip side is that the embedded cores are wimpy and they provide limited performance. Processing using DRAM enables highly parallel computations within the DRAM chips, but in the context of an SSD, we need to transfer the operands from flash chips via the bandwidth limited flash channels. IFP eliminates data movement overhead significantly compared to the other two approaches and also provides high computation parallelism, but the operation set is quite limited. So these are the questions that we try to address in this work. So is a single NDP paradigm good for all the workloads? Do we need to combine these NDP paradigms? And which is the most suitable NDP paradigm for each computation? Now, to analyze this, we performed a case study where we examined the performance bottlenecks by hand mapping parts of the workload to multiple SSD computation resources. So in this case study, we evaluate the host CPU, in-storage processing, in-flash processing, and combining both ISP and IFP. In this case study, we did not include the processing using DRAM paradigm because the data movement overhead of PUD is very similar to ISP because the data has to be moved through the flash channels, and the compute capability it lies somewhere in between ISP and IFP. For this case study, we evaluated hybrid workloads where these workloads involve both computation and data movement like aggregation and sorting. And then we also include IO intensive workloads where these workloads are dominated by data movement like databases and bitmap indices. We also have more workloads in the paper, and I'll flash the link to the paper later. So if you look at the experiments that we conducted and the results, we see that for hybrid workloads, combining ISP and IFP gives a significant performance improvement by up to 40% over IFP itself. And this is purely by reducing data movement and mapping computations to the most suitable computation resource. So in hybrid workloads, combining different NDP paradigms make sense. But if we look at IO intensive workloads, here if we naively combine ISP and IFP, we observe a reduction in performance by 15%. And this is because we need to intentionally move the data to ISP, which actually incurs additional data movement and reduces the benefits or negates the benefits of offloading to different resources. So some of the key takeaways that we got from this case study is that no single computation resource consistently performs well across different workloads, and the performance bottlenecks are workload dependent and vary across different execution phases of the same workload. And offloading to multiple SSD computation resources provides benefits, but it also it works only when we do it judiciously. So we look at the limitations of prior SSD-based NDP techniques, and we see that these techniques map computations to only 1 or 2 NDP paradigms, and they fail to exploit the SST's full computation capability. Then they lack generality across a wide range of applications, which means that they are customized for specific use cases and workloads. And they're also not programmer transparent, which means that the designer has to spend a lot of time in changing the storage stack to include these NDP paradigms. So we looked at offloading techniques. There are unfortunately no prior works which propose application transparent offloading of computations across different SSD computation resources. We looked at main memory-based offloading techniques, which explore partitioning and mapping of application code segments between host and NDP units near main memory. And we categorize these works into 2 offloading models. The first one is bandwidth-based offloading, or BW offloading, which makes offloading decisions based on bandwidth utilization of the host and NDP units. And then we also have data moment-based offloading, which makes offloading decisions to minimize the data moment between the host and NDP units. So we adapt these offloading models for near data processing in an SSD. So when we look at the effectiveness of these prior offloading techniques, we compare them against an ideal approach, which So this ideal approach is basically making several unrealistic assumptions. So it assumes that there is no data moment across, or the data moment latency is 0 when we move operands across computation resources. It selects the best computation resource all the time. And then it also assumes that none of these computation resources have experienced contention. So with this, we show the performance here of these 3 offloading policies, and we normalize the speed up over CPU here. And across these 6 workloads, which also include LLM training and inference, we see that the best of the 2 offloading models, DM offloading, still has a large gap in terms of performance, 2.5 times gap compared to the ideal approach. And this is because this DM offloading model prefers a single computation resource to reduce data moment, and this causes queuing delays and resource contention. So our goal in this work is to enable programmer transparent near data processing in an SSD that effectively utilizes all the computation capabilities within the SSD, and makes workload and system aware offloading decisions, and improves performance and energy efficiency of a wide range of applications. Now, I'll move to the key idea or the key mechanism of Conduit. So Conduit is our proposal. It's a general purpose programmer transparent NDP framework that dynamically offloads computations at instruction granularity to multiple heterogeneous SSD computation resources. It has 2 key steps: a compile time pre-processing step to identify offloadable code regions in an application and transform them into wide vector operations, a runtime offloading step that takes these vectorized instructions and then maps them to the most suitable computation resource based on application and system characteristics. Now, let's look at compile time pre-processing. So in this step, we take the application code, perform loop, run a custom compiler pass to identify offloadable code regions. It involves loop auto vectorization, which transforms scalar instructions into wide vector operations that match the SSD's internal parallelism. And then it also leverages partial vectorization, because loop auto vectorization doesn't work all the time. So we partially vectorize code regions, and hopefully it can benefit from parallel execution in an SSD. Conduit then basically extracts lightweight, during this pass, it extracts lightweight metadata like operation type, the location of these operands, and then element sizes and vector length for each vector operation. It embeds this metadata with the intermediate representation, that is the output of the loop auto vectorization, to reduce runtime scheduling latency and preserve programmer transparency. So Conduit then converts this optimized intermediate representation to an executable that is capable of running on the ARM cores, which are the embedded cores in the SSD. and it transfers the ARM executable to the SST by repurposing the NVMe admin commands for firmware updates. So this is basically what we do in the compile time preprocessing step. Now we move to runtime offloading, where during the execution of the application, we basically determine where the instruction has to be mapped. So in runtime offloading step, we basically perform dynamic offloading of in the SST controller to preserve programmer transparency and avoid changes to the storage stack. So why we do it in the SST controller is because this has real-time knowledge of the current state of the SST computation resources, like how these resources are utilized, what is the contention in the shared channels, and so on. So in this runtime offloading step, there is an SST offloader that is running in the embedded core, and it basically maps each vectorized instruction to, in the ARM executable to the most suitable SST computation resource. That is based on a cost function. So the cost function is the brain which decides where to offload the computation. So let's look at what this cost function does. So this cost function basically looks at application characteristics and current system conditions to evaluate the cost of offloading an instruction to each SST computation resource. So we look at several factors like data movement latency, which is if the operand is in, let's say, the DRAM, and we need to move it to the flash, then what is the data movement cost to move it to the target computation resource? Then we look at the expected computation latency, which is the estimated instruction execution latency on a specific computation resource based on the operation type. Then we also look at data dependence delays, which is the delay for operand availability, and then resource queuing delay, which is the delay caused by the number of pending instructions in the computation resources execution queue. So basically we add all these delays, and then we get the total execution latency for each resource. And then we do this for all the resources available in the SST, and then take the minimum among the three, and we get the offloading target. So it basically selects the computation resource with the lowest execution latency. Now, after the cost function decides or determines where to offload, we need to transform the vectorized instruction to the native ISA of the computation resource. So in this process, we have an instruction transformation unit that is also running on the embedded core. And this transforms each vectorized instruction to the native ISA. So if we decide that the instruction has to be offloaded to ISP, then we basically transform each vector operation to the ARM Cortex ISA and schedule the instruction for execution. If we have to offload it to the processing using DRAM substrate, then we use ISA extensions from prior PUD works like SIMDRAM, MIMDRAM, Proteus, the works that we saw in the morning. And we then transform these instructions and then offload that to the computation resource. For IFP, we have several works like Flash Cosmos and Aries Flash, and we use these primitives for instruction transformation. So we have a lot more details in the paper. Like if we have these heterogeneous computation resources, then we need to look at data coherence, which is an important problem. Currently, we have a lazy coherence mechanism because we want to reduce the write amplification on NAND flash chips. So we try to avoid writing frequently to the NAND flash chips. We also look at how we move the data among these resources and how we map the data. We also have the host to SSD communication modes. We have two modes which we currently which operate in a regular mode or in a computation mode. Then we have failure handling, how we handle transient failures and permanent failures. Then we look at Conduit's extensibility, limitations of auto vectorization, and many more details. So this is the link to the archive version of the paper. I invite you to take a look and provide feedback if you have. So this basically concludes the mechanism of Conduit. Now we jump to evaluation. So to to basically leverage all these computation resources within the SST, we had to develop an in-house event-driven simulator because none of the existing simulators have these capabilities in the basically in the SST simulator. So what we do is we inherit some of the core SST functionalities from MQSim, and we also add a DRAM component that is based on Ramulator, and then we model the shared resource contention and the performance models for all the 3 NDP paradigms. Our SST configuration is based on Samsung 980 Pro SST. We evaluate 6 data-intensive workloads from different sources. AES and XOR filter are light in computations and with low data reuse. Then we have Llama training and inference, which have complex computations. So it's a broad range of workloads. And then we also evaluate all the policies that I already mentioned, including Conduit. So if you look at the performance analysis of these offloading policies, we again show the speed up over CPU, and Conduit, which is in light green in this figure, provides a performance improvement of 1.8 times compared to the best performing prior offloading model, which is DM offloading. And this is purely by making holistic offloading decisions. And it also provides 62% of the ideal offloading policies performance without making the ideal approaches unrealistic assumptions. Now, we also analyze the energy consumption of these offloading models. And then we observe that compared to DM offloading, we reduce energy consumption by 46.8%. And this is by exploiting all the available computation resources and reducing resource queuing delays. We provide 68% of the energy efficiency of an ideal approach. Then we look at how Conduit and other offloading models exploit the computation resource capabilities of SSTs in terms of how these resources or paradigms have been utilized for different workloads. So we show the fraction of instructions which are offloaded to different compute resources. So for several workloads, we observe that the ideal and Conduit actually perform very similarly in terms of how it offloads to different computation resources. So, and this is again, as I mentioned, Conduit doesn't make the unrealistic assumptions of an ideal approach and still tries to make the best decisions possible. So then we look at overhead analysis and the storage overhead. We first look at storage, and then we see that to store the cost function features that I mentioned, we require about 17 bytes in the SST DRAM. We also need 1.5 kilobytes of the SST DRAM to store the instruction transformation mapping. So we basically map all the types of vector instructions and the native ISA. So that's the storage overhead. In terms of runtime latency overhead, we need to do this feature collection, which is used for the cost function analysis and also the instruction transformation. So this takes around less than 4 microseconds on average for each instruction. And we don't add any, Conduit doesn't add any area overhead beyond that of the prior techniques that it leverages. So our evaluation also has more detail. We also have more experiments in the analysis. There is tail latency evaluation where we see significant benefits because we reduce resource contention, and this gives us a performance improvement, tail latency improvement of up to 22.3 times. We also show how these computation resources and the workload interact and how the different, at different phases of the workload, what computation resources are preferred and so on. We also provide more detailed analysis of the overheads and workloads and so on. Again, this is the link to the paper. I would like to invite you to check out this link. So in summary, Conduit is the first general purpose programmer transparent NDP framework that enables fine-grained computation, offloading across multiple SST computation resources. Conduit improves performance by 1.8 times on average. For the best performing prior offloading model, we observe significant energy benefits over the most efficient prior work. And all these benefits come with low latency and storage overheads. So that concludes my talk, and I'll be happy to take any questions. Thank you for your patience.
Are there any questions for Rakesh? Maybe I can ask.
Yes.
So can we use this key idea for some other, let's say, systems, not just computational resource and solid state drives, but maybe some other components that we have hybrid memories that have different trade-offs?
Yes. Yeah. So we also looked at accelerators near all these components and try to include them. But again, we in this iteration of the work, we are mostly looking at the inherent capabilities of the SST. But yeah, it is definitely possible to look at more broad heterogeneity in terms of resources available. But the main challenge is how do we where do we run this offloading mechanism, and how do we track all these application and system characteristics that we need for making better decisions? So that's the challenge that we need to think about in those cases.
Thank you very much.
Thanks.
Thanks a lot.
Yeah.
This concludes the workshop for today. Before we leave, I would like to again remind you that we will have the 5th edition of this workshop in 1.5 months. So the website is on, and if you would like to give a talk or discuss your ongoing works, you can submit using this QR code or with this link. And if you cannot make it, don't worry, we have another one. There's a 6th edition, and again, as I mentioned, this will be a different one. For these ones, we had invited talks, but for this one, we will have extended abstract submissions. So, and it will be in the same proceeding as the ICS. So feel free to submit your ongoing work or things that you're working on. So the website is, I guess, will be on today or tomorrow for this one, but for this one, it's on. So feel free to check out and reach us if you have any questions. And thank you very much for your attention and all your questions and everything. Hope to see you in the next iterations. Thank you.